Hi. All right, I think we are ready to go, folks. Welcome, welcome, welcome to Punch 4. Very excited to have this meeting here and to have all of you here. Let me give you a few logistical notes before we get started. First of all, importantly, the bathrooms are over there in that corner. Second of all, the Wi-Fi is UCAR visitor and there is no password. Thirdly, the way the format of the talks are going to go is we have 4 15-minute talks followed by 30 minutes discussion. So for that reason, we are going to hold the questions till the end. Now, we realize you may have questions as you go. So we have something called Slido that you may have seen before, and you can see the QR code right there. You can scan it with your phones. It works really well with your phones. You can either scan that QR code or input the number, which is up there, 8926961. You'll find it in various places around on the posters and so on. And the nice thing about Slido is you can type your question in. It will go into a queue that the moderators will be able to look at and make sure we get to those questions during the discussion. And you can ask the question when it's fresh in your head. Also, you can upvote questions that other people ask. And we don't have a two-way kind of virtual interaction in this meeting. We do have streaming, and some people are watching. They can also enter questions into the Slido, and that's how they can interact if they like. Other than that, yeah, the discussion. Also, yeah, there's also a big QR code on this you can find at the front desk. Carrie Dawn, are you in here with us? Everybody say hello to Carrie Dawn. She is our wonderful organizer, and so she can answer a lot of questions. She's here at the front desk. And one of the things you can go and talk to her about, this afternoon we have an excursion to Fiske Planetarium on CU campus. And Sherilyn, do you want to raise your hand back in the back? There's our Punch outreach leader. This is going to be a really fun interactive session where you get to play with some of the outreach activities we have, and I believe there will be some performances of some sorts or another by various people in this room, in fact. And the way that's going to work, we have Fiske basically from 5 till 6:30, kind of easing. 7 is the hard cutoff. I think they have a night event, so we have to be out of there by 7. So at 4:30, when this meeting ends, we're going to carpool. So Carrie Dawn has a list, and if you at the break or at lunchtime can go and talk to her. If you need a ride, tell her, she'll get you on the list. If you have a car and you have some space, we'd really appreciate it if you could tell her you have 3 spots, and then that way she will do the matching. And this will all happen, the actual excursion going out there will happen at 4:30. Driving over there, that is. Now, we do not have a dinner plan tonight. And Fiske Planetarium is on CU campus. You can walk down to Pearl Street where there's lots of wonderful restaurants, or you can go into the hill, the University Hill. So we're just assuming that you're going to kind of, after this excursion, go off and do what you want and make your own way back. If you have any questions, talk to Carrie Dawn and she can relay them to me. Now, tomorrow we do have a dinner which is here. It's going to be a reception. We're going to have our talks, we're going to have a poster session, and we're going to have a great reception just out here. So do stick around for that because it's going to be a lot of fun and there's going to be some very tasty food. Speaking of tasty food, there is also going to be lunches on both days. And there are tables in the North Auditorium. Who knows which way is north? Thank you, Carrie Dawn. That one. So you can get your food and you can go sit in there if you want, or if the weather's nice, which I don't know what's happening these days in Colorado, but if it's nice, you can go out and there's a really nice atrium out here that you can sit and eat outside. I think that is it. what does this say? Oh, the agenda. You have an agenda. Yeah, I already did the wireless. The agenda is on the back of your name tag. You can scan it. It's a Q code. Any question? We have 2 minutes in this thing, so did I miss anything, anybody? If not, we're going to give 2 minutes to Craig, who is going to start us off. Forward, backwards, yeah. Oh.
Excellent. Thanks. Hi, everyone. Wow. This is our 4th one of these. That's pretty exciting. This is our first science meeting that's more than one day, and it's our first science meeting where we took contributed talks. So, wow, what a great team, and thank you for all the new folks who are here. Give yourselves a hand. Hello, our project manager. He had some medical issues that have kept him away, but he has a recorded message, so I'm going to start off with that. So let's see if this works. Go. There it is. All right.
Hi, this is Ronnie Kilo, your Punch Project Manager. I wanted to welcome you to the summer 2023 Punch Science Meeting. I just wanted to leave this message with you and let you know that, of course, all of you are the reason we're doing what we're doing on the engineering and management side, which is trying to put together the best Punch mission we can so that you guys will have some great solar science to do. So welcome to the science meeting. Hope you have a great meeting, and sorry I couldn't be with you.
So Ronnie's doing fine. He'll be back in the saddle shortly, but he wanted to make sure that you guys all saw that and that he actually cares about the meeting. I'm going to move forward into why we're here, right? Many of you have seen this slide many times, but some of you have not seen it yet. This is what we're for. We're trying to unify solar physics and heliospheric physics. And we're at a crazy time, right, when both methods of studying the plasma that surrounds us are available to us. And traditionally on the left, we have solar physics has been done by remote sensing, and heliospheric physics has been done in situ with sampling material as it sweeps over a spacecraft. And of course, right now we have Parker Solar Probe. I think Nuruddin Rafi is in the room. I don't see you, Nur. There he is. Hey! And that's carrying in situ analysis into the corona. So we can actually sample what's happening in detail in the features that we see through coronagraphs. And of course, Punch is going the other way. We are bringing the global and cross-scale pictures from the corona out into the heliosphere by imaging the solar wind itself at its origin point or origin region. So that's what we're doing. I will be very fast here because all of you have seen this before, I think. We are 4 small sats. We're going to launch into sun-synchronous orbit at about 620 kilometer altitude. And there are 4 of us, or 4 of our spacecraft, because they have to look in all directions. We'll come back to that. We're right now in assembly, integration, and test. If you've ever been on a mission that's undergoing assembly, integration, and test, you know that it is a hair-raising time to be involved. There's a lot going on, a lot of things breaking because we're doing a lot of things, and a lot of things being fixed. And so it's just wonderful to see the team has had a chance to knit and are really doing what they need to be doing. Our next milestone is this September as pre-environmental review. That will be after we integrate our first complete observatory and we get ready to do environmental testing on it. So pretty excited about that. We're aiming for April 25 or March 25 launch out of Vandenberg Air Force Base on a rideshare with the SphereX mission. This is our science. I know you've all seen this, but I do want to recognize the people who are involved. These are our main science objectives or science questions, and they're organized into working groups that are tackling each. So 1A is the wind flow. That's Barbara Thompson and Raphael Addy are leading that. Can you guys raise your hands just so people know who you are? Awesome. Atier, excuse me. We have 1B, solar wind microstructures and turbulence. And we have Nikki Weil in the back there raising her hand. Thank you. We have 1C, the Alphane zone. That's drawing a blank. Steve Kramer. Thank you. Steve, raise your hand. Okay, in working group 2, we have CMEs. That's Dave Webb and Anna Malonushenko. Can you guys raise your hands? There's Dave, and I don't see Anna, but she's here. She was here yesterday. And we have this co-rotating interaction region formation and dynamics is Kurt DeKoning, who I believe is remote right now. I haven't seen him yet this morning. And shock dynamics and morphology is Heather Elliott and Mihir Desai, who are in the back. And Heather is also our in situ liaison, so she's great for talking to you if you know about in situ physics or in situ measurements. Just a reminder of what we're doing. This is the transition at the top of the corona, where somewhere in this field of view is where you would say the corona ends and the solar wind begins. And we're tackling this region with matched instruments so that we can form a seamless field of view instead of the seamed one from stereo. You've all seen this many times. Just to remind you, our field of view will cover from the outer corona, basically the LASCO C3 field of view, if you're familiar with LASCO, which you should be, all the way out to 45 degrees from the sun. So as you talk to people outside our small insular community, remember, we are not a telescope. We are a wide field imager. We're observing plasma as it sweeps over us across the solar system. So what's new? I want to remind us what is new here. We have a continuous field of view. We've engineered our instruments, and thank you to the instrument leaders who will be talking next. We're going from 5 to 180 solar radii with a continuous, seamless, virtual instrument that's composed of instruments that were built to match each other in spectral and spatial characteristics. They're operated at the same time. We have about a 30 times improvement over the legacy instruments. That's stereo and LASCO. Our high resolution is up to 20 times improvement compared to legacies moving out into the solar wind. Our high cadence is 4 minutes throughout the mission. And I call that out as 3 to 30 times improvement versus synoptic legacy programs, which is true. But in one area, we are much better than that. In measuring solar wind speed at all latitudes, Ulysses did that once every 6 years. We'll be doing it once every 6 hours. So it's a significant improvement. And of course, we're bringing polarization to the wide field, which hasn't been available outside the LASCO field of view until now. So very excited about these new measurements, which are going to give us lots of new grist for understanding this system. I want to call out why we care about low noise, which is that it affects resolution. These two images down at the bottom here are examples of the same piece of data, one with high noise, one with low noise. And you can see that the effective resolution is much better. And so punch images are going to look much different than you're used to from looking at existing coronagraph and wide field images. We will have much lower noise, and as a result, we will resolve structures in the same way that the right-hand AIA panel here does. You can get a taste of that, and have gotten a taste of that, I'm sure, with the low noise campaign data that we took with stereo. These are our instruments. I probably should be showing photos, and at the next meeting I will show photos instead of these diagrams. The spacecraft are designed to be interchangeable, and each one has an instrument bolted to it. We have a coronagraph on the left. Robin Colanino, who will be talking next, is leading that effort. And over on the right, we have the wide field imagers, which are heliospheric imagers that are deeply baffled, and Glenn Laurent, who's also here, will be talking about that. This is how we merge our images together. You'll be hearing about that. It turns out making a movie like this is pretty easy, but actually doing it is hard. And so our SOC team have been working tirelessly to make this happen properly, and you'll be hearing about that as well. Here are just some examples of things that we had to overcome in developing the SOC. I'm just going to tease them. We've made new inroads into the 240-year-old dialogue on how polarization works, new forms of analysis in order to do our background subtraction properly. We've developed ways of regularizing the point spread function of a telescope. I like to point out in Marcus's paper that just came out, he cites Kepler as somebody who also had a problem with coma in telescopes. Of course, we're now producing forward model mosaics. I won't steal Dan's thunder on that, but they're here and you'll see more of them. This is our calendar. We are aiming for a fiscal year 25 or spring calendar year 25 launch. We are in phase CD. The blue line in the middle is where you are right now. We're coming up on the pre-environmental review. That's the PER to the right. We have a pre-ship review next August. And then we go into storage for a couple of months to synchronize with the Spherex schedule. We revive everything in February and take it off to Vandenberg to be integrated and launched. We have a 2-year Phase E. Phase E starts 90 days after launch. We have a long checkout period, including a 30-day science test sequence that we'll use to shake out all these new marvelous processes in the SOC. And then a 2-year Phase E. We have Phase F on the calendar, but of course we hope to keep operating as long as humanly possible. We have a Punch outreach program being led by Dr. Sherilyn Morrow, who's in the back of the room. You may be getting these public engagement newsletters. They are phenomenal, and I hope you'll come and marvel at some of the products that the team has produced. It's really first class. I'm very proud of them. Here's some pictures from a couple of months ago of UNify AINT. I didn't want to steal Robin's thunder with more recent ones, but the coronagraph is coming together and it is phenomenal. I think you guys just got into thermovac, so pretty pleased about that. Here's some pictures of UNify. These are different UNify instruments because we have 3 of them, but that's what they look like in person. They are deeply baffled. Glenn will tell you a little bit more about how the whole system works. That aperture there is, you can just see the optical train behind. And the optics, of course, have a pupil that's matched to that hole rather than inside the optics, as you may be used to. And of course, there's the door on the left covering the instrument. This is STEAM. This is, again, an old picture of STEAM. I didn't want to steal anyone's thunder, but STEAM is being furiously integrated for delivery this summer, and we're pretty pleased to have them on board. That's our student instrument, which is an X-ray spectrometer, and Mary Hansen is leading that. Was leading that, brought it through almost to where it is today. And of course, we have Amir Caspi as mentoring the students. Amir, you're in the back of the room? All right. We have a microsat. This is an actual picture taken not very long ago of one of the microsats undergoing integration. We recently turned on the ADCS, successfully passed the smoke test. It's doing fine. Anyway, just to show you that there are lots of plugs and harnessing and lots of things going on. So in terms of our status, I've already mentioned we are in AINT. The instruments are nearing delivery. Let's see, and I think I have a typo in here. FM1 is nearing Vibe and TVAC. The other 2 are a little bit behind it for the UNify instruments, but you'll hear about that from Glenn. We have subsystem integration in progress on the spacecraft. We're really pleased with the progress on the SOC. We may actually be able to fulfill the promise of turning on and having data flow on day 1 when we reach Phase E. So pretty pleased about that. And we're aiming for a 25 March launch. So go Punch.
Thank you, Craig. Thank you so much, Craig. I realized I also wasn't doing a very good job with my introductions. Of course, a man who needs no introduction, that's Craig DeForest, the PI of Punch. And I'm Sarah Gibson. I'm a project scientist on Punch. Okay, let's move on to our next speaker, who is going to be Robin Cullinino, who is the instrument lead for the Narrow Field Imager, or the UNify. It's backwards, and then if you go like this, you can actually put a thing. Oh, that's great.
All right. Hello, UNify instrument lead from the Naval Research Laboratory, where we've been doing all of this work that I'm going to show you. Hopefully most of you have seen at least some of the coronagraph. That is the UNify coronagraph. We will have a field of view that will go from probably it'll be usable at 6 arsun, but it'll start imaging at 5.7 arsun and go out to 32 arsun. So it's kind of like an over-occulted C3, not that anybody uses C3 that close in when there's C2 data on LASCO, but we are the center in that center spinning trifoil. Trifoil? Is Shamrock, I like to call it a shamrock. We're the center, and we will also be spinning. You can't really see that here in the data, but our data will also be spinning similar to the way that the WIFI field of views are spinning as well. As Craig already said, we're going to be providing superior, all things better resolution, better temporal resolution, better spatial resolution, compared to our predecessors. So this is just the diagram of UNify. It is a compact coronagraph design. The compact coronagraph was developed for the NOAA missions. It is the compact coronagraph that's going to go on the NOAA platforms. NRL has delivered one compact coronagraph to NOAA for the GOES program. Then there'll also be one on the SWIFO mission, and then there'll be one also on the ESA, what are they calling it now? For Vigil mission, that's what they're calling it now. So this is a very similar in optical design, but has a different form and function for the camera that we're using, which is a common camera for punch. So here's just a physical block diagram of all the subsystems, and the point of this one is to show that we are developing an observatory. As Craig said, this was designed purposely to match the WIFIs so that all of the data can be integrated together to create this one seamless field of view and create the largest imager in space. But you can see we're just an optical instrument with a similar camera in the back, so hopefully when we get it up in space, it'll all go back together quite nicely. And as for our observing plans, we will be taking triplets of images, and these will be lined up with the WIFI. Again, in the whole point of doing to integrate all the data together in the end, we'll be taking 3 images that will be summed, similar to what we do on Core 2, and that just to increase the dynamic range that we get in the CCD. And we'll take 3 polarized images, 1 clear or unpolarized image, and then another set of polarized data at each stop in the orbit. And there are 12 points in the orbit as we kind of tick-tock around the Earth. So let's get into the subsystems. We have some beautiful footage here of the item itself. So this is the stray light assembly. This is where all the magic happens to prevent the solar disk light from getting into the optical system and causing us not to be able to see the corona. So the main player here is the occulter. Here, this is the flight occulter. It has 9 disks on it, and that is what the first disk actually blocks the solar light, and all the subsequent disks are there to block the diffraction. So diffraction is really the enemy here, and so we're working hard to prevent blocking diffraction and scattering the interior baffle. You can't see that there are baffles inside there. It's quite black, and that's the way we want it. So there are baffles inside of there, but you can see, it's weird pointing over here. You can see the occulter with the pylon here at the front, and then this is all black in the back, and then the front A0 aperture, which is this kind of starburst pattern. And this will be our vignetting function that is based on all of this hardware here in the front, the vignetting, and that is where we overlap. The main thing is where we overlap with the WIFIs, we will not be vignetted, so we will have a good resolution there. Okay. So this is the optical system itself. It's a pretty simple optical system. It's just a lens. It's a very simple telescope with a lot of stuff in front. So this is our flight lens barrel here during an inspection, and then you can see it here actually integrated with its thermal hardware onto the back of the baffle. So it's a lens that we designed at NRL to give us a good field of view and to give us a superior imaging quality at the plate scale of the CCD itself, and we did find that we are at the optical limit of the CCD with our lens when we tested it after integration, so it looks really good. And then our passband is also matched to the Wi-Fi passband at 450 to 750, and that's similar to the LASCO C3 passband. So that's a fairly wide white light passband. Okay, and then we have the heat rejection mirror, which Craig showed earlier, that is here sitting on the bench. This is both an optical and a thermal component. It takes all of the sunlight that is coming into the front of the aperture that's not going into the optical system, and then it focuses all of that light out here, out through the front. And I actually have a picture of it doing that. So it takes all of the light and brings it back out so that it's not scattering inside of this baffle tube. And then that's also not only light in the visible spectrum, but it is heat in the infrared spectrum, so that we can keep the hot side hot and the cold side cold, because we want the CCD to be nice and cold for good imaging. And then this is the common Wi-Fi camera here, or common punch camera that for the NIFI. This is our structural tube here, and then the camera, and that pretty much constitutes all of the instrument except for the door. You can see here with the camera, we have all of the thermal components already installed on it, and then this is our structural component here, which is constitutes the body of the instrument itself that everything gets attached to. And that's all aluminum, and then with some titanium mount points in there to help thermal isolation. Then we have the NIFI door. Oh, I don't know how to make it. This is a movie, so I think I don't. Thank you, whoever did that. Thank you. So this is the door with a very nervous mechanical engineer standing next to it. Her hand is in the screen. So this is our one-time door with the pin puller, paraffin pin puller actuator. That's why it takes a little bit of time for it to actuate there at the beginning, because the wax actually has to heat up before it pops open. But so this door will protect us. It's protecting us now during integration, keeping anything out of the optical system. It'll protect us once integrated on the spacecraft and at launch. And then we'll open it up once everything's nice and settled in space, and that'll stay open for the rest of the mission. So, oh, I just needed to push the button. Okay. Okay, this is the common polarizing filter wheel. So it's the exact same filter wheel between the NIFIs and the Wi-Fis, so that we get the same polarization imaging. You can see the polarizing filter wheel here, mounted into the back of the system. This one right here is covering up the lens right now. And you can see we have 3 polarizers. Those are the shiny ones. We have this black one here, which is a pseudo shutter to black out, take dark images, and and also to protect the optical system if need be. And then the clear silica wafer here, which is for taking unpolarized images. And then this is the actuator itself down here, which is the little motor that turns everything. So. And then this is the punch camera. This is a image from RAL. RAL are all gnomes, if you didn't know that. That's the RAL team, the gnomes. They're quite fond of their gnomes. So this is a full frame readout of the CCD itself. It is very similar to other CCDs that you might have encountered. It's a high heritage E2V device, similar to what we're operating on Core 2, STO. So very similar camera, but this is a pseudo frame transfer, so we don't have a shutter. The image gets moved out here underneath this aluminum bit and then read out. So that's different than what we've had on previous instruments, where we've had a shutter usually. So, and then the camera electronics box here, which sits behind the NIFI instrument. All right, so here's some of our optical testing. This is the subsystem optical testing, so this is what we've been doing more recently. Here we have the coulter. This is our a coulter alignment setup so that we can tip and move the whole thing around in all, tip, tilt, X, Y, Z, and to get that occulter aligned into the system, to get everything aligned to the light source. This is this is the lens testing setup where we measured the transmission and band pass and resolution of the lens after we received it from the manufacturer. And then here, as I said, this is actually a test of the HRM, so we're shining a lot of light into the front end of the NIFI instrument, and then you can see all of the light is coming out here in this circle. So it has been focused out the front of the NIFI instrument and is coming out of this little, this is a Melanex cover here to show where everything is. Is being focused out the front of the instrument and being rejected out of the front of the instrument. Okay, so this is our pre-environmental testing. This is the Scotch testing that we do at NRL. This is an NRL unique facility that allows us to, in vacuum, create with a solar simulator. We are able to simulate the collimated light from the sun. So we have, this is the back end of it, but the front end of it is a 10-meter vacuum chamber where we send the light through. It has baffles and it gets collimated so that it looks very much like the light from the sun as much as we can. It's quite bright. If you put a piece of paper in front of this light source, it will catch on fire, which is something we have to tell people. This is the NIFI instrument positioned on the optical bench here and covered up with a Melanex cover to keep it clean while we're getting everything put together. Here you can see it from the side view with some of the thermal components. And then here at the front, this is just a neat little image. You can see the hand of the photographer here being reflected off of the HRM inside of the instrument. So this is what we use to actually measure the optical performance of the instrument before we start environmental testing. So this allows us to check out that everything is aligned and where we want it to be and that we're meeting our requirements for resolution because we have to get the camera quite cold. You have to do that in vacuum to get rid of the scattering from light or the scattering from the air. You have to put it in vacuum. So very important test here, and then we'll repeat this again once we complete our environmental test program to make sure that nothing changed during the environmental test program. So the environmental test program is designed to simulate the conditions that the instrument will see during launch. So the first thing that happens to the instrument is it launches and you shake it really hard. So that's what we do in the laboratory. So the first environmental test is vibration. We shake it independently in all three axes and then measure the response of the instrument. You can see here, this is our shaker. This is actually, this big drum, blue drum here is actually the shaker, and then it's mounted onto a cube here. This is it being installed to go under the Z-axis vibrations, and then here we move this whole blue drum thing down, and then it comes onto this table, and we shake it in the X and Y axis. So we've completed that for NIFI, and looks good. And we are now moving on to the thermal vacuum testing. So once you launch it, it gets exposed to space, and that's vacuum and cold. So this is what, and some of it's hot too, because you're in the sunlight. So some of it gets hot, some of it gets cold. So we are recreating that environment here in the thermal vacuum test chamber. This is this kind of psychedelic photo here is all of the test stand and blanketing material. That's all this aluminum foil looking stuff is actually thermal blanketing material that we baked out in the chamber prior to installing the instrument into the chamber. And then here we have the instrument actually installed into the chamber. So this week we closed the chamber and we just started pumping down. So it is under thermal vacuum now. So in summary, the NIFI instrument is moving along. It's meeting the driving requirements and the science objectives. I think we're gonna create a really nice product. for everybody to use, and NIFI is currently in TVAC. Once we finish, TVAC is going to be 22 days, hopefully. Once we complete TVAC, then we'll go back to verify the performance of the instrument post-environmental testing in the Scotch chamber. And once that's complete, we'll deliver it to the spacecraft for spacecraft integration. So go NIFI, go Punch.
All right, thank you so much, Robin. So our next speaker is going to be Glenn Laurent, who is the instrument lead on the Wide Field Imager, or WFI.
All right, good morning, everyone. I'm Glenn Laurent, the WFI instrument lead of the 3 WFI instruments on Punch. My goal here is just to kind of give a very brief recap of the design and then delve into the current status of the 3 flight instruments. Robin just showed by providing a complete view all the way from the inner corona through the solar wind transition. The WFI field of view is from 5 to 45 degrees with 3 degrees of overlap with NIFI. Both instruments provide polarized images using a rotating filter wheel. The WFI stray light design is based on the stereo high and the solo high imagers. The 3 WFI observatories are equally spaced at 120 degrees, such that full imaging happens every 32 minutes with individual sets of observations every 4 minutes. So this is WFI. So from the field of view or from the life of a photon, the first element is the WFI baffle, which attenuates the 3 main sources of stray light, namely Earth shine, lunar, and solar stray light. A photon then travels through the polarizing filter wheel developed by NRL, goes through an optical lens assembly, and then comes to a focus on a CCD camera developed by the Rutherford Appleton Laboratory. So you've seen the functional block diagram from NIFI earlier. The NIFI is grayed out, but the WFI follows the same general architecture with several common elements, including the polarizing filter wheel, camera housing, and the camera electronics box, as well as the thermal control. And I'm having trouble moving forward. Okay, there we go. All right, so like NIFI, the WFI has a passband of 450 to 750 nanometers, and the field of view, resolution, and sensitivity have a substantial margin compared to the requirements. So this is a snapshot of the baseline CONOPS that we have planned. Graphically, WFI and NIFI are effectively identical with 2 sets of 3 polarized images every 8 minutes with a clear filter in between. The only difference is that WFI takes a single exposure given the dynamic range compared to NIFI, which takes 3 separate images at each polarized location. So this is a cross-section of WFI just showing how the lunar baffle defines both the field of view and the field of regard of the system. And again, showing all of the major subsystems. So the flight instruments will be ready for the Scotch Stray Light facility in a couple months now, just under a couple months. But we did bring the engineering unit to Scotch in order to measure our stray light, cool down the detector to flight negative 65 degrees, and then chopped the beam both on and off of our baffle in order to get a differential signal. From that, you can measure the stray light. Our stray light requirement is quite high, 16 orders of magnitude of the solar flux, and our performance meets that by a factor of 100, which is good. So moving on to actual flight optical results here. Our optical lens assembly was developed by Teleview and requirement of 3 arc minutes. The image on the lower left here shows our actual point spread function as a function of radial distance from the center of the CCD. Green is our requirement, and you can see all the points fall into that. In addition, we have additional points outside of that field of view, which also should be useful. Craig showed this, but this is our point spread function as a function of location on the CCD just graphically. And then for our engineering units, we were actually able to take the unit outside and actually look at a proper star field and measure the point spread function as a function of location on the CCD. So we've been working closely with the Science Operations Center on that in order to help develop preliminary processing. So as far as the transmission itself, our requirement is 92% over the passband. We measured the throughput of all of our optics of all the flight units, both from the vendor level as well as in-house, and all of those meet requirements with a throughput of 96%. Similarly to the out-of-band rejection, we have a passband filter on the first lens of the OLA, and our requirement is to reject by a factor of 100 everywhere outside of our 450 to 750 passband, and we meet that with a substantial margin with performance of a factor of 2 to 3. Our final optical requirement is off-axis scatter. So at 20 degrees, we need to be able to reject stray light by a factor of 100. And we are well above that with laboratory testing of greater than 2,000. One more, distortion. We have a requirement of no more than 10% F tangent theta distortion over our entire field of view. And working with our star field data from the engineering unit, we are significantly less than 1%. And the pipeline team, again, working in order to develop actual flight pipeline development, we are working with them in order to minimize our non-radial residual components on that. And the grayscale here is not great, or the color scale here is, but it's very small. It's significantly less than 1%. So this is an image of the piece of the common element of the camera. The bottom right shows our final flight assembly, including our optical lens assembly mounted on that. In addition, we have our thermal strap here that's mounted here. On the back end, our CCD assembly. This is the camera without the optical lens assembly attached. Then again, our final assembly. So several months ago, beginning of March, we went into vibration testing. Vibration testing was performed in-house. Actually, this is an old slide. I don't know if we have a new one. I'll just speak to it. But this is for the first vibe we did. Since then we did receive our updated observatory model from the launch service provider, our expected loads. Which is higher than the general environmental levels from GEVs. And we did have an issue with two subsystems, both our OLA as well as our door, which I like to call our lessons learned. Here's an image of the actual flight WIFI 1 on the vibe table. So speaking to that, for our two test failures, we had a contamination event of our optical lens assembly where an internal lens was shifting inside our barrel. That was traced to a loss of preload at lens 3. So we, as far as the lessons learned, we moved forward by modifying the optical lens assembly housing by drilling radial holes at 120 degrees right next to the existing vent holes and epoxying the lens elements to the housing. We did perform unit level testing on the OLA itself and was successful with both thermal and vibration testing on the OLA flight spare. And so we've went ahead and applied those modifications to the WIFI 1 OLAs, and the WIFI 2 and 3 OLAs are happening now. The other issue we encountered was on the door latch. Our existing cup cone interface, given the high surface area between that interface, caused some stickage post-vibe, and the door had trouble just getting started. We are confident that would not have been an issue in flight, but to be comprehensive, we decided to add a small kickoff spring, which has a Europa clipper heritage, and we also modified the cup cone interface to be a ball cup design in order to minimize the amount of surface area at that bulk cup interface. That was just successfully tested on our EM door, and that modification has also been applied to the FM unit as well and functionally tested. So we've overcome those challenges, and we're moving forward into getting into revibe late next week, and then 2-3 days later we'll be going to TVAC, similar to the NIFI schedule. So this shows that change that was made. Left here just shows the OLA with the lens. The green holes you see here are the radial holes that we added and injected epoxy there, showing here from the side. These are our 5 flight elements that housing change was made to, and then here is the vibration testing that we performed in order to validate that change. And on the door side, this just shows a snapshot of the latch and the changes we made to it. This is the resulting EM unit vibration testing in order to validate that change. Vibration on the left, and then vertical door testing in both configurations on the right. So just a recap of, I guess, general progress. The Wi-Fi 1 has been, that modification has been made to the housing. We've focused the camera with the spots that you've already seen. This is the door changes that we made to Wi-Fi 1, and those changes are being implemented on Wi-Fi 2 and 3. And looking forward on to Wi-Fi 2, the camera has been, assembly has been completed. That has gone into characterization testing. I had some pictures here, but I don't think they made it in the final slide stack. Just showing us going into the vacuum chamber with an integrating sphere, and that testing is expected to complete in the next few days, after which we'll, in parallel, be moving the Wi-Fi 2 and Wi-Fi 3 through the pipeline and focusing the camera, and then entering environmental testing over the next few weeks. Wi-Fi 3, here is our assembled baffle, including one of our mechanical engineers using a laser CMM in order to take measurements of the locations in order to verify the locations of each of those baffle vanes. And that will be integrated into the rest of the system, again, over the next few weeks. So an overall summary, the EM Wi-Fi test campaign has been completed. All that is currently with the observatory team in order to verify all functionality. The Wi-Fi 1 integration is effectively complete. Vibration testing is happening next week. Thank you. After which TVAC is a few days after that, and then Scotch testing will happen in early September this year. For Wi-Fi 2, the camera characterization is nearing completion. The baffle assembly and testing is complete, meeting requirements. The polarizing filter wheel characterization also complete, meeting requirements. Door integration is underway, and OLA integration underway. So it's just a few weeks behind Wi-Fi 1. And then Wi-Fi 3, the camera assembly is underway. That will be going into characterization testing in about a month. With the FM3 baffle assembly and testing is complete. Filter wheel characterization also complete, and the OLA housing modifications are underway. And I think that was the last slide I have. I've got some backups, but with that, I'll hand it back off to Sarah. Thank you.
Okay, the final talk in this session is going to be Dan Seaton, he is the head of our Punch Science Operations Center, which is the SOC. Everybody keeps talking about the SOC. It's the Science Operations Center. So here comes Dan. You got forward, backwards, and hold, and kind of wait, and you'll get the...
Okay. A quick overview of to develop the Science Operations Center and the data products and the task we have to actually make data, which is complicated. I really want to acknowledge the whole team that's working on this, and I will try to point out a couple of opportunities to see in depth what I don't have time to talk about in detail today. If you check out some of the posters and talks that folks who are working on the team are going to have later in the meeting. So let's start with just an overview of the data processing, and this is what we're trying to make. Integrated mosaics from 4 sets of observations a new one every 4 minutes, covering sort of both the inner, see if we can get that to work, inner and outer field of view from 5 to 180 solar radii. And then by making several of these and putting them together, we can make full mosaics with all these little corners filled in 3 times per orbit at a cadence of, I think, 32 minutes. To get there, we have to do a lot of work. It's pretty complicated. I will walk you through this slowly, but just to sort of summarize, first we have to calibrate the individual observations up here. That makes our level 1 products. Then we have to merge observations down here. We have to get them into a sort of uniform basis and polarization. That's level 2. We remove all this background stuff that we don't care about, the F corona, the star field. That makes level 3. And then we make a whole bunch of products, which I will tell you about down here. So let's zoom in. We start with level 0, just the raw output from the camera and a lot of metadata, what's going on the spacecraft. And we start by performing a flat field, a complicated multi-term flat field to deal with nonlinearity in the detector. We remove cosmic ray hits, and then we have to de-streak things because there's no shutter on the camera. We read in shutterless mode, so as the frames are read out, actually, they continue to be exposed, and you get these streaks that have to be removed. We've made a lot of progress on this part of the pipeline. We're able to de-streak. We're able to do the flat fielding. We're making good progress on the cosmic ray despiking. After that, we have to remove stray light. We have to remove, or rather not remove, but make the PSF uniform. You've seen a little bit of snapshots of the PSF. I'm going to talk a little bit more about that in a second. And then we have to actually make sure that the pointing is just right so all the individual panels fit together. We finished the de-streaking, we finished the PSF deconvolution section, and then we're working on the alignment section where we actually make sure that the registration of the images is just perfect. I want to highlight these 2 things because these 2 things are generally applicable to many problems, not just punch problems. And so these are 2 of the packages that we've developed in the SOC that are going to be available for the community to use on whatever projects you want very soon. So the punch PSF is not uniform across the field of view. On the left side, you see these sort of measured PSF in different parts of the field of view. And you can see that it has this tail that points in a different direction depending on where you are. Now that makes it very hard to use the data across the field of view because it's all smeared around in different ways, and it makes it really, really hard to integrate these overlapping observations. Marcus Hughes has developed a really cool package called Regularized PSF that takes all of these individual PSFs and deconvolves them out, so you end up with a totally uniform PSF across the field of view. And that's available, I think, very soon, maybe right now, in AstroPi. It's in the process of being approved as an AstroPi affiliated package, I think. So that's something that you can use on any observation that has a non-uniform PSF across its field of view, or even a uniform one to make your PSF better if you want. These are some observations, and never mind the flickering, that's just an artifact of stray light and stuff, but you can see these are observations from a field test we did on UNify where you can see the stars. And these have provided a basis for actually tracking the overall pointing of the instrument. So Marcus has developed this really cool package that can find stars, so it can pick out all these little bright points here. It can compare them to a catalog, and correct and figure out which stars that we're seeing in the image correspond to which stars in the catalog and actually measure the pointing across the whole field of view. And doing this, he was able to measure the distortion. The lens distorts the image just a little bit, and you can see this is a map of sort of how things become distorted, and we can refine the pointing so it's down to a fraction of a pixel knowledge in every pixel. And again, this is something that's going to be available to the community. It's called Refined WCS. And you can use it on any observation where you can see stars, not just punch. All right, let's jump back into the pipeline. After all this, we've made level 1 products. We're calibrated. We know where we're pointed. We jump down here to level 2. Now at level 2, we have to do 2 things that allow us to merge the data together. The first is, we have all these different spacecraft that are oriented in different directions, measuring polarization. We have to take their raw measurements and convert them to a uniform system so they can all be fit together. So we have a tool here that actually resolves the the raw instrumental polarization to something that we call MZP. Again, there'll be a chance to hear about this in depth in a second, so that they can all be integrated. They're all in the same system. Then we mark them if there's any artifacts, if the moon is in the field of view, if there's aurora, and then we finally merge them into these trefoils. And the polarization piece is in development. It's pretty mature. It's not quite finished. And the code that actually makes these mosaics is done. Let me zoom in on the polarization, because this is sort of one of the most important steps for the mission. Ritesh Patel has been developing a package called SolPolPy that can convert between different polarization systems. And Craig and I and Matt West and maybe that's all, have a paper that describes this in detail, and Ritesh is going to have a poster that talks about this problem and how it gets resolved. But we make measurements in a system, this system actually, with three polarizer angles. And there's this tool, what it allows you to do is transform into any one of several bases where you can track polarization. So, looks like my latest version, I had these labeled in the latest version, but I guess it didn't get propagated into the version I'm showing you. But here's the Stokes, here's polarized brightness, here's a radial tangential polarization. We can transform between these, and we can also transform between sort of reference angles over here so that we can merge these things in a common basis. This is an example of the package working on LASCO data. Ritesh is building support to use this with a whole bunch of instruments, LASCO, stereo instruments. We'll support Proba 3 observations when those are available. Probably K-core, eclipse measurements that Amir Caspi is leading. So this will be a general package that's available to the community, anybody working with polarized solar data. And you can see his poster. Now, one of the cool things that happened in this process is it turns out that the field of view of WIFI is so big that light that enters from the sides of the field of view doesn't come in quite with the same polarization angle as light at the center. And Ritesh has been working to track how you manage the polarization so you're working with the correct angles across the field of view. And he realized that this is a problem that actually happens in IMAX movies. IMAX, as you may know, does 3D movies using polarized glasses. And they have the same problem. They have this huge screen. And the edges of the screen, the light entering, is not coming at quite the same polarization angle as at the center of the screen. And so this was sort of Ritesh's inspiration for working this problem out, and he's made a lot of progress. And again, I think this is on his poster, but I love the synergy of seeing an IMAX movie, making a connection, and building this out of a big body of research that actually exists from the IMAX community to be able to show 3D movies, which is really cool. Okay, let's jump back in. So we've made now polarization resolved mosaics. We then move across to level 3. We have to remove the F corona, which requires building up a model of the F corona over a long time. We have to remove the star field, which involves changing polarization bases again, building up a model of the stars as they move across the sky and resolving that. We made a lot of progress on the F corona piece. The star field's yet to be done. And we end up with observations like these, which are resolved into brightness, total brightness and polarized brightness. Let's dive into how this is all orchestrated. We have two tools, one called punch pipe and one called punch bowl. This is a really complicated diagram. I'm not going to go through the whole thing, but there's a whole bunch of things that have to happen to make data actually come together. We have to figure out when to run things. We have to actually launch them. We have to keep track of what we're running, and then we have to actually update our files that says what happened and where things went. And in the core here, what we call a core flow, we have to actually execute the science code. So punch pipe is the orchestrator, written in Prefect by Marcus Hughes largely, that does all this orchestration. But what's really cool is that the way we've built this is the core science processing code works the same way in our pipeline as it would on your own computer. If you want to do your own custom processing, you don't need to worry about any of this overhead. You'll be able to just run these pieces on your own system. No need to worry about punch pipe, and it's all seamless. So that's largely built and actually running in our test environment. A little more about these. We're using Python. We are using the punch bowl to do You can use it for yourself to make custom data if you need a special product with a special polarization basis, whatever. It supports the polarization analysis. It'll have all that PolPy functionality that I was telling you about. And it will also build support to simulate data from models. And I'm going to talk just briefly about that in a minute. And then there's a data handler that makes it easy to work with our data products. Our products are complicated because they have multiple different polarization measurements within single FITS files, but we have a data handler, which we call the punch data object, which is being built by Chris Lauder, largely. And that allows you to work seamlessly with the data in really simple ways. It carries all sorts of visualization functionality, file writing functionality. You don't have to build your own. We actually are building products right now. We're trying to make them very transparent. We're trying to have metadata that's really thorough, really clear, so you can understand exactly what's in the products. We are making them FITS4 compliant so that you can work with them in whatever FITS reader you want. They should play nicely with it. And we're using multidimensional capabilities in FITS so that you can have all of your polarization data represented in single files, but in really straightforward ways. And this is a snapshot of what the products look like over here. The headers look like. What's really cool is we are now actually making data products, and these are available for you right now. I really strongly encourage you to pull out your phone and scan that QR code right this minute so you can go and get these products. We would really like you to play with these sample products. We are generating these using the Gamera simulation. You can see that there's CME progressing across the field of view. The image I'm showing you is a level 3 trefoil product. So it's not the ones where we've fully filled in the field of view. And you can see how the field of view is rotating as the event progresses, as the simulated spacecraft, each one represented by a color, are progressing across the field of view. We have some other products here. You can type in this tiny URL link. You can scan the QR code, but go and get them and open them up, try them out, give us feedback. I'm running out of time, so let me just zip down here. Ultimately, we're going to have all of these products. We're going to have solar wind speed maps. We have the products I just showed you, also a full resolution NIFI product here, and then ones where we do some additional processing to remove noise and integrate the whole field of view. And that's the one I just showed you. Okay. We are trying to support space weather. Don Schmidt tomorrow is going to talk about how we are making products for what we call the Quick Punch project, which are complementary to and provide a backup for NOAA's own space weather capabilities from SEACOR, which is going to go on SWIFO and goes U. And I'll leave it to Don to fill you in the details, but these are going to be low latency space weather oriented products. Matt West has a really nice poster talking about how you can use the scattering, the polarization ratio and the scattering of light from objects throughout the heliosphere to actually measure their propagation distance, and a sort of a future way to track CMEs along the line of sight. And again, I'll leave it to Matt to fill you in the details, but I really encourage you to go see his poster. It's really cool stuff. Okay, what's next? We've got to get back to work on the things that are left here. We've made some progress, but we've got to build this whole pipeline. You can see some things are done, some things are in development. We're going to be starting work on the things that aren't started yet really soon. There's a lot to do. We've got to finish our data product definitions. We're going to do that with your feedback. We're working on this SimPunch package to make more synthetic data like I just showed you. We're setting up a data server where you can actually, that'll be like the real server where you'll be able to access data so we can do some interface tests. We got to deal with unpacking the stuff that comes from the spacecraft. That's not a simple job. And we're going to keep working on analysis tools and polarization tools. So in summary, we've got a pipeline. It's not all the way done, but it's working in our test environment. Key community tools are ready or soon will be. We've made really important progress on the polarization, resolving, and manipulation. That's a key function that we need. And the data's there now. Go there. Check it out. A lot of detail I had to gloss over is in other people's posters. So please go throughout the meeting and check in with Marcus's, Ritesh's, Matt's, and see Don Schmidt's talk for all the details that I did not get to cover. And I just want to make sure that you have our contact information. You can get in touch with me or Matt West about the data, about the pipeline, about your needs. If you try these products out, you run into problems, you can ask us for help or you can give us feedback and we will incorporate it. And thank you very much.
All right, thank you, everybody. So could I have the four speakers come up to the little panel? Craig, Robin, Glenn, thank you. And Barbara's going to moderate the Slido. We have the Slido up here. I encourage you all now to take your phone out and take a photo. And Craig, do you want to describe it, Barbara, how it works? And while she's doing that, just one comment about the posters. We do have the posters out. Where are the posters? Out there. And they'll be available to look at during the coffee breaks and the lunch. And we have a dedicated poster time tomorrow.
Great. Thanks, everyone. If we didn't make it clear earlier, we are handling our questions. We are prioritizing the Slido questions so that the online audience gets equal opportunity to ask questions. And so we do have, let's see, I will start with the one of the, there's two people that asked about the NIFI aperture, the star pattern. Is it just because you like stars, or is there an optical reason for that?
Yes, so there is an optical reason for that. It should be, I will say all of the coronagraphs currently in operation have that same starburst pattern front aperture, and you've probably never noticed it because it should be transparent to the data user. What it is, there is any edge that you have is going to diffract, and so what we're doing with that starburst pattern is that the angles are specifically designed so that that diffracted light does not go into the entrance aperture. That aperture is outside of the field of view of the instrument, and so that we're just have those weird angles so that none of that light is going directly into, or we're trying to reduce the amount of diffracted light that's going directly into the aperture of the instrument.
Great, thank you. Let's see, the next question, Dave Webb asks, so NIFI has no provision for H-alpha images. Are you talking about H-alpha in the bandpass or a separate filter? So no H-alpha?
There is no requirement on Punch to collect H-alpha images. Therefore, we aren't doing it.
Should have spoke up 3 years ago. Let's see. The next, Subhamoy Chatterjee is requesting to know more about the micro roughness of the lens surfaces on NIFI.
Micro reference. I'm not real sure about the particular details of the lenses. Micro roughness. We are getting very good performance. These are all highly ground glasses. We have reduced the scattering to what we need it to be in the lens assembly, so they are all AR coded. So it's something that was designed. I'm not sure. I don't have the details on it off the top of my head.
Okay, well, it's in Slido. If you have anything to add, you can also comment on that question. Gilly, you asked a question about the shutterless, and Dan addressed that a little bit. Do you feel like that was addressed well? Also, Ritesh had a question about how the CCDs handle blooming effects, if there's any protection for that or anything that handles that. And I think that's for both NIFI and WIFI. So.
I can speak to that. There is no protection on the CCDs. They will bloom. We do expect some blooming to happen. Unlike every other mission that's flown, the blooming won't have a fixed position on the scientific image plane because we're rotating the instruments every orbit. So there will be occasional dropouts from blooming, but there'll be 1 8-minute period long because the bloom will move to a different place.
Great. We have one more question from Bill Matthews saying, Craig, is the descriptor flocculation now disparaged? Do you feel
Is the descriptor flocculation now disparaged? I like that word. It's reminiscent of the surface of a sheep. I've had people complain about it. Those people have retired, and so I'm sticking to it.
All right. And then we have... Oh.
I was just going to say, we use it all the time in our papers, but you didn't mention it, but you should start using it again. I don't know why it was criticized.
We do use it in scientific talks. I just didn't cover it here. Yeah.
Wait, there's another online, just a couple of online comments first. Again, we're going to prioritize the online. There's two comments from team members that I want to share about the SOC. Gilly wrote a SunPy Fido client, that's the data fetch client, that also downloads the sample data for Punch. And so if you're used to obtaining your data through the Fido, your imager data through the Fido client, it's already compatible, and so you can just go ahead and use that. And Matt West has been talks a little bit about how the FITS files are fully FITS compliant, and astropy.fits is opens it fine, but there's a little bit of an IDL issue that they're working out.
So Gilly was going to comment.
Oh, thanks, Gilly.
I just want to say I wrote it yesterday, and nobody else has it but me. So if you want to use the SunPy Fido thing, I'll try and give it to the actual SOC people soon. But I just sort of have it. Come talk to me.
Okay, you ready to move into the room? Yep.
I can do it. Thank you very much. This was really awesome to see the progress where we are. My question was fascinated with Dan's presentation, removing the star field and its application to all the other data sets we have, and I kind of would like to, during maybe poster session, how we can jumpstart that into other data set that we already have. I have a specific question about the removal of F corona. I'm just posing this as a question right now, but maybe during the poster session we can have a longer discussion. Is it model-based? Can we take like observations which we are taking and automate it with AI, whatever, right? Kind of do daily subtraction. There are all kinds of cool things possible today that wasn't possible 30 years ago.
Yeah, so we have a strategy which is basically to look at the background, sort of minimum background over a month's time, spanning 2 weeks before and 2 weeks after the observation, and remove it. And that's sort of the traditional way people have done this for LASCO and the stereo core and high instruments. But there's lots of other things that we could do, and this is a particular challenge for the space weather observations where you can't wait 2 weeks to build up your F corona model. So I think we're open to supporting other methods within our package, and then users who want to try, using an AI thing could use an AI module. And I think we can, we have a sort of requirement we're working to, but we can be flexible and try some cool experiments. And hopefully, if we're successful, then these could be fed back into other projects. I think we are trying to make this package as flexible as it can be, so people who have specific needs can process the data in their way and get the best results that suit their requirements.
Maybe I could add to that. We are trying to support the teenage hotshots of the world, right? We are producing the data products we produce, but we want to make sure that the crazy people who want to do their own have the tools that they need without having to write them from scratch.
Yeah, I have a quick follow-on to Lika's question, because you're going to be the first time you're getting polarization on the F corona outside of the LASCO C3 field of view. So in addition to observing it, you're observing it for the first time. So that's a challenge, and it's going to be a great benefit to the community. I just want to mention that.
Yeah, and I guess people who are interested in the F corona, you can reverse the process and observe the F. If you separate the F corona out from what we think is the K corona anyway, the residual would give you the F corona. So if you want to see how that's evolving, we could support that. I mean, I think that we're trying to be as flexible as possible. So we're going to make the data product with the F corona removed, but if you want to study it, you can put it back in, or you can take out the K corona or whatever.
Would you guys mind, since we've got a fairly broad audience in here, including a lot of our outreach colleagues, could you define K and F corona?
You want to take that?
A quick reminder, the F corona stands for Fraunhofer, and that's the Fraunhofer spectrum, which is the dark lines in the spectrum of the sun, if you're looking at the photosphere. And so the F corona is made by dust that's orbiting the sun. It's a bright cloud in the sky. It extends out and becomes the zodiacal light, if you're an astronomer. And that light has the dark F lines in its spectrum. The K corona stands for Kontinuierlich, which is German for continuum. And
Say that again, please, Craig.
Continually, I think. The electrons are moving so fast that the spectral lines are Doppler broadened. They see the sun Doppler shifted and they scatter that Doppler shifted light. And so the F spectrum, the Fraunhofer spectrum, is washed out. So the K corona is the electrons. That's what we like to see. Thanks for the reminder.
Lovely. Okay, so we have a couple more online questions. Tom Berger's back. Tom is asking about the impact. Have you modeled the impact of the South Atlantic anomaly? Especially for the high radiation hits and things, right? Oh.
Yeah, it was a real pain for Trace, as you recall. So just wondering if it's been taken into
We did
account.
consider that. That was a big topic during our site visit, as you might imagine. One advantage we have over Trace is we're using back-thinned detectors, and that helps a lot. The best way to avoid radiation interacting with your detector is make sure there's no material there. So we thin the silicon, and as a result, there isn't very much to interact with. We will see the South Atlantic anomaly, of course, but we won't be washed out in the same way that Trace was.
Can I say two more things? So because of our shutterless readout, actually spikes that occur from energetic particles are differentiable from the actual data in a way that's more straightforward than it was for an instrument like Trace, because they don't leave a streak. And so we actually have a method to separate those things out. Additionally, most of the observations are actually made out of multiple observations. And if we combine those intelligently, the spikes, which are transient, right, those will disappear as we merge the data and get down to the actual focus on the science data. So, I think that you guys have done a lot to protect the detector already from spikes, and then in the processing, I think we have some advantages over Trace too. So.
Great. We also have a question from Noor about fuel margins. I think the question is, are there, first of all, what is the anticipated fuel margin, and when are there times when the spacecraft, what are the factors that might influence the fuel margin while on orbit? Is that right? Okay.
We use the fuel to maintain. We have a small rocket motor on board. It hydrolyzes water and then burns it to make propellant. And that's used to trim the orbital spacing. So maintaining the 120-degree spacing is something that requires active thrust. It's a very small amount of thrust. If I remember right, we have about a factor of 4 margin on the conservative delta V estimates we made. So we anticipate being able to run for at least 8 years, and given that there's always hidden margin in the orbital calculations, probably more like 15 to 20.
Nice. Hey, go ahead. Did you have a question over here?
Yeah, and then Bernie.
Hi, John Keller, Fiske Planetarium at the University of Colorado Boulder. I'm pretty confident, I wanted to confirm that you plan to do polarized mapping out to 30 solar radii. I'm curious about whether that limitation of 30 solar radii is based upon sensitivity beyond that, or if there's other physical constraints limiting the ability to deconvolve three-dimensional structures beyond 30 solar radii.
So I probably was not clear. We are the first people to go beyond 30. So the widest field coronagraph flying right now is LASCO C3, which has been up since the 90s, and it does polarization out to the edge of its field of view. But nobody else has flown a polarized instrument that looks farther from the sun at the Thomson scattering.
And how far out do we go? In radii.
Oh, in radii, we go out to 180. But we're far enough out that you got to think about tan versus angle. Yeah, right.
Yeah, I had a couple of questions. One for Glenn. Did you simulate the lunar brightness in the tests that you did with the experiment?
Yeah, for the engineering unit, we did do laser testing at a range of positions, simulating the lunar light and calculating what our attenuation is at various positions, and we meet requirements.
Because that will provide stray light into the instrument, and that's a worry.
Yep, we have a two-stage conical baffle as our lunar baffle in order to mitigate that.
I have a similar question for Robin. I saw the external occulter shiny around the barrel, and I wondered if you worried about that scattering light from some sort of periphery into that and then back into the instrument.
So you can't really tell in the images, but the beginning of the occulter and the pylon are all in the same plane as the A0 aperture. So those are all designed to be ahead of the baffling system so that any scattering is out of the light, outside of the baffle. So that's part of, both for thermal and for optical reasons, that's why those elements are shiny, and they are as forward as we can get them in the instrument.
Yeah, but they would scatter back into the...
There is scattering back into the, off of the pylon, but we've designed the pylon shape such that that's minimized and is not any brighter than the occulter.
I want to jump in on the lunar stuff. The moon does get in our field of view, which it doesn't from L1, so that is something we have to deal with. The moon will not contaminate significantly the NIFI images. We actually looked at heritage images from SMM? Solwind.
Solwind had the moon in it, yeah.
So you guys will see, NIFI will see the moon, but it'll be dark when it comes through as a new moon. UNify is affected by the moon, but it doesn't blow the whole field of view. When the moon is either waxing or waning crescent, it'll pass through the field of view, and a portion of the overall science field is contaminated for about a week per month, but not the whole field. Even when the moon is in the field, it's not there for every angle.
Well, let's see. So Tom Berger has a question about the orbit and eclipses. What's your altitude? And also, what are the eclipse periods, and what happens during those eclipse periods?
Let's see. So we initially you may have seen materials that talked about 570 kilometers. That was limited by the particular launch system we designed to in the proposal. We're on the much more powerful Falcon 9 now. We're ride sharing with SphereX. And our estimated orbital altitude now is 620 kilometers, which gives us a much longer hang time. It also means that we maintain the sun-synchronous precession for longer because the orbital decay isn't as fast up there as it is down at 570. Does that answer the question? Oh, the eclipse periods. We do have eclipse periods. NIFI can probably operate during the eclipse periods. UNify will operate during the eclipse periods. The moon will be visible in the NIFI field of view. It will not be visible in the UNify field of view.
So
sorry, the Earth, excuse me.
On NIFI, we will have eclipse periods, and the biggest issue with the eclipse periods will be Earthshine.
Yeah.
So as we get closer to the Earth, I think we do have blackout dates with a combination of the Earthshine will swamp the stray light in the images, so that'll be seasonal. It's a lot more interesting orbits when you're around the Earth than it just sitting nicely at L1.
Biannual, a week or something like that?
A couple of weeks.
A couple of weeks per year, yeah.
Is that good, Tom? Great. All right, somebody got a...
So, is there any possibility to appoint one or more spacecrafts to observe the geocorona? And it's possible, is it?
All things are possible in the fullness of time. During the primary mission, we will run no campaigns.
I had another question. How long does it take for Dan? Long does it take to get from the images to the final product, level 3 or so? And what sort of computing system do you need to do this?
So there's a couple of bottlenecks. The first one is to get the images from the spacecraft to the ground. We have one pass per spacecraft per day most of the time, maybe two occasionally. So that's a day, up to a day. We can get really quickly to level 2. The goal is to do it within an hour. The requirement's like a day or two, but I think we can do it quickly. We've got a pretty powerful computer. Level 3 is more complicated because we have to build up the coronal, the background models, the star field and the F corona. The goal is to do that within 2 weeks. So as soon as you have accumulated the data required to make the model, we can process it. There's a couple of really processor-intensive steps in there. Some of them can be executed on GPUs, and that speeds them up enormously. So the computing system is powerful, but not it's not a supercomputer or anything. It's just a good server rack with lots of memory and lots of storage. The space weather products, what we're going to do is we'll just time shift the background models so that instead of running sort of with the observation in the middle, they'll run with the observation at the end. That'll degrade their quality a little bit. You'll get a little less clean subtraction, but it should allow us to get latencies down to an hour or two after the data reach the ground. And so that for the space weather products, if we had to, if all other space weather assets died, and there was no way to observe the corona, I think we could run at latencies of a couple of hours, assuming we build in a lot more passes. But that's not foreseen. We're just doing sort of demonstration of what is achievable from low Earth orbit. We won't actually make low latency data. Don's going to cover that, I think, a little more tomorrow too. Do you want to add to that?
I do, actually. Just if you've been around for a while, you remember we used to get quick look data and then real data, and Punch will be that way, right? The quick punch will serve that role as quick look data that you can see right after it's downloaded. All the data will be made available to everybody at the same time as the science team. I'm really big on that.
Yeah, the one thing is that by request from NOAA, that there's a slightly different field of view for the space weather quick punch data, but it's okay.
All right, and we have some follow-up questions on data. Thor Metzinger asks, will the data also be available in voxel or point cloud formats that facilitate, I guess, different computational platforms?
The plan is to make FITS files, to make FITS4 compliant FITS files. If people want them in other formats, I'm happy to entertain conversations, but that's not going to be our baseline. It's hard enough to make the FITS products. Yeah, I've thought a lot about more advanced data formats and why it might be beneficial to Punch and other solar missions, and I'm happy to have some conversations, but we'll do it on a best effort basis, not on a requirement basis. Yeah, Craig is shaking his finger at me. This
is an example of a good community thing, though. If we have users in the community that have especially if they have a vision of what they'd like, if they're willing to provide the code for it, could be useful for a lot of people to repackage the data in formats that are native to other applications.
Yeah, I mean, I'd be happy to help people work with our data to repackage them if they have their own formats they want them in, or to try to implement something on our servers once we actually get the thing working, which is in and of itself a challenging task. But yeah, let's talk. Come find me, and I'm happy to talk about it.
And it'll bring me to a question that I had, and it's kind of related to Gilly's comment about Fido too. Usually, you release the software on, you say that people can contact you or Matt with questions, but often the way you facilitate that is through a Google, a GitHub user chat and Q&A, and so that the community can see your responses and they can.
Yep.
It's more integrated. Do you have a time that you plan to launch that? I assume you're going to do something like that.
We have a GitHub organization for Punch, which is pretty empty at the moment, but we're going to populate it, and I think maybe already we've gotten a couple of pull requests from people. And I think we will also be SunPy affiliated, so we'll be available through SunPy channels. We're going to build really robust documentation. So it'll be, if you're used to working with SunPy, it should be similar with examples and clear documentation. And then, yeah, I think we'll definitely set up something. I don't know exactly what or when. We're not ready for that quite yet, but I don't know. Marcus and I, we can talk, and maybe we can get something spun up in the next month or two.
If anybody has a good example of a well-curated discussion page on GitHub, contact me or Dan, and we'd love to at least have examples.
Yep.
That it? Any final questions in the room?
Quick question. Is the way the data will be collected fixed once and forever, or there are some degrees of freedom? In terms, say, can you reach a better cadence by sacrificing something else like signal to noise ratio? And if so, can the community contribute to maybe formulating special campaign during the mission?
All things are possible in the fullness of time. We are not running campaigns during the primary mission. In particular, there's a good reason for that I'll expand on, which is that this background accumulation that Dan is talking about requires extreme uniformity of data. And so campaigns interfere with that. So we really want to get the best synoptic data set we can. In an extended mission, we might look at that, but it would have to be something really good.
But I will say that the way we're going to process the data gives you sort of one box with time and spatial resolution, whatever. But we're making these tools so that if you want your own custom processing, I think you could have a higher effective cadence in custom processed data. I think you could have a different field of view in custom processed data. So some of this can be achieved with the data processing itself. We're not going to make those products for you, but we will certainly make the tools that make them available.
Okay, before we thank our speakers, I have one quick announcement for speakers going on. Kelvin, can you raise your hand in the back? Kelvin, here you can go and talk to and make sure your slides are all set up. They were all downloaded today, but do be aware if you make last-minute changes on the Google Drive, you need to tell Kelvin so he can bring down the latest. So at the breaks, before your talk, do go check and make sure everything's cool. And so now, let us thank our speakers again. And
All right, it is 10:30. Let's go ahead and get started for our next session. All right, we have another 4 talks for this session. Both Robin Colanino and myself will be chairing this session. Our first talk is by Raphael Ati from George Mason University. We'll be discussing mapping solar wind flows with punch.
Thank you. So yes, I'm Raphael Ati. I'll talk about mapping solar wind flows with punch. So why do we want to map the solar wind flows? Well, from my perspective, it is to understand the interplay between the corona and planetary environments. And by expanding as the solar wind flows outward, relatively small changes near the sun's surface feed planet-wide space weather effects. And measuring that flow is necessary to relate the dynamics in the environment of Earth and the other planets to what has happened upstream. And there's been so far a critical lack of flow maps in the solar wind, and that will be addressed by punch by delivering solar wind flow fields with quantifiable uncertainties. And I will talk some more about uncertainties in a few slides, because originally it was not in the basic requirements for delivering solar wind flows that are produced by NASA. We are spending some time to actually deliver that on top of the basic requirements. So how do we do that? So far, I have been training the main algorithm that I've been using with the Zero Core 2 data processed by Craig with the deep exposure compiling. And so most of you are familiar with these movies. And I'm going to get back to those data after I've reviewed a little bit how we measure flows in general in the heliospheric field. So the basic algorithms that have been out there since the 1980s are the optical flow techniques. And the qualitative definition of it is simply quantifying motion of brightness patterns across a time series of images in a sparse or dense flow field. And there are many different qualitative definitions, but this is the one I like to use. And there are several methods for it, and I'll mention those that have been sort of more or less applied to image theories in heliospheric observations, whether in solar physics or outside the sun. There are differential methods, which are simply, the formal definition is this equation called the optical flow equation, which are using the gradients of the images in the space and time domain. There is one optical flow equation there, but we still have to solve for the 2 components of the motion, U and V, in the image frame. And so in reality, we have noise, and the optical flow equation is more like an error term that needs to be minimized. And that's still just one equation. And so on top of that, usually the problem becomes a minimization problem with a second criterion, second error term to minimize. For example, Horn and Schunk in the 1980s introduced something they called the smooth gradients, or the smoothness constraint, to simply avoid sharp transitions. And there is a big caveat in these techniques is the fact that you can see an upward motion, and it seems to be going in a certain direction. But here in this DIY experiment that I did at home, what I've been doing is simply I pushed this piece of paper from left to right, but when you process that with these basic differential-based methods, it will give you a motion that goes upward. The reason for it is because when the image has locally no gradient in either or both direction, well, the motion vector simply cannot be determined, and that's known as the aperture problem. And this is really the source of many uncertainties in these methods. So I just wanted to know, I wanted you to be aware of those qualitatively. Some implementations exist to circumvent this problem. Numerical schemes can fill in the gaps, and there are also hierarchical pyramidal processing, but these have not really been tested in the context of the punch images. This is an example of application of these differential methods. It's an ongoing work by Bea Gallardo-Lacour for tracking auroras. And we'll see that kind of data also with thanks to the wide field of view of punch. And so on the bottom right, you can see one of these dense flow fields derived from these differential-based optical flows. So we usually need additional constraints for that to work. But in the case of punch, we can do very useful assumptions. For example, if you assume a radial flow, then suddenly you have one of those terms that vanish, and well, it makes it, in the end, these differential methods for punch-like data, well, they're worth their shot. So I plan to actually test that and compare that with the other methods that I'm going to talk about. So the basic data products that we'll be probably using is correlation-based methods. I've put them in feature matching methods because simply a correlation-based method is simply about having a metric of similarity that tells you how much two features across time are look like each other. And there are also frequency-based methods. They've been developed a lot in the medical field to analyze the displacements of bacteria or different cells in petri dishes. And it's simply the equivalent of the optical flow equation in the space-time domain, and they simply do it in the Fourier space-time frequency domain. And I haven't seen that applied yet in solar wind images. And that is something that I also intend to try out, simply because we see a lot of periodic density structures in the solar wind, and these Fourier-based method makes sense. There are also physics-based methods that we need to think about for punch data. An example that I like is for photospheric flow fields is the method developed by Pete Schock called DAVE, which using magnetic field measurements, he accounts for the magnetic induction equation to track the velocity of magnetic foot points in the photosphere. And so they are supposed to be more accurate than correlation-based methods. So if we if there are some theoretical developments made to port physics model into the punch images, then these methods could be also developed for having accurate flow maps with punch data. So punch takes polarized brightness. There are Thomson scattering physics there, and so using additional physical constraints, using that, I think we could obtain very, very good algorithms. There are also neural nets. There are two kinds of neural nets that I'm seeing very useful for punch data. The supervised neural nets are trained with MHD simulations, where a network is presented input observations, like synthetic granulation in the case of the photosphere, and an output ground truth. And the neural net creates a mapping between mapping functions between the input and the output. And this example is a flow field derived with that method on granulation images with a simulation, with a Murem simulation. And I think it's something that also could be, these are interesting projects that could be thought of for punch. A caveat on that is that these methods may not generalize very well if the systematics or the lack of simulations of physics make the real observations deviate from the simulation used for training. We also have, I think, the next big thing are, I think, going to be physics informed neural nets, because they are unsupervised method, and where the forward propagation of the neural net is still using the observations as input. But instead of having a ground truth flow field at the output, we are using physics equation that drive the forward backprop minimization that describe the mechanism that believe is at play. So the advantages of this method is they can be very efficient PDO solvers that can learn nonlinear relationships. The disadvantages, though, is that they still carry the uncertainty on to what extent the physics equations describe the observations, which is still sort of a human-based choice that restricts the discovery space. The method that I've been actively developing for punch is the magnetic ball tracking method. It is a method that I've developed during my PhD in 2015. And it's about tracking in the Lagrange reference frame the moving magnetic features on the photosphere. And it output a sparse flow field. So that means we output motion vectors for a set of moving objects. Here, in that example, these are moving magnetic fragments in magnetograms. And it also can output feature characteristics, lifetime, sizes, etc. So with Punch, I've been working with the Core 2 data for stereo. I've been adapting that method to track the little plasma density structures in the brightness images of the Core 2 data. So here on the left is again the movie I showed earlier from Craig, and on the right is the temporal unsharped masked data that allows to reveal the density structures that we are trying to track. And so when you do this temporal unsharped mask, you obtain, and you unwrap that azimuthally, you obtain this time series at the bottom, where the gray and black stuff are the plasma density structures. Magnetic ball tracking is applied to track them, and using a training set that I illustrate later, then I can fine-tune the magnetic ball tracking algorithm. And I end up, I'm able to build then a map of the radial flow. And here is what I came up with. And the interesting thing is that we actually have interesting error bars. And because we can have so many balls able to track the features in narrow angular bins, then the statistics becomes significant. And so here is a sort of Ulysses-like plot of the solar wind. Thanks to that. Thank you. There is one caveat, however, to that method, is the fact that we're still tracking things in the image frame. And as you probably already know, the 3D location and distribution of these density structures is not really straightforward to transform to convert the coordinates that we have in that image frame into 3D space. There's a lot of uncertainty on that. So what I'm hopeful is that the information that the balls carry in their own dynamics when they track each individual density structures is that we can work out also where they come from, in what direction they're coming from. But to get these accurately, it's important to have some sort of a ground truth. And to be able to say whether or not the tracking of the balls is accurate, I actually manually, semi-manually tracked the density structures all the way across 10 solar radii. I did that in a semi-automated manner, having a way to fit all the different density structures and having a centroid for them, and manually then select a statistically significant sample to actually have also a sort of a ground truth flow map that I can compare with the ball tracking results. These training sets are going to be available as well through Helionauts. The training sets must satisfy a few things. They must provide density and velocity flows used as ground truth. They are necessary to tune the algorithms, evaluate performance and uncertainties. They must be statistically significant for separating training, validating, and testing, because you need also to avoid overfitting. For example, when you are testing your algorithm in different pre-processing of the images, it has an impact also on the result. And so what's currently available for the training sets are the manually tracked density structures with quantified uncertainty from Stereo Core 2. We also have synthetic data sets from Valmir, and please come to Valmir's talk as well. It's going to talk about how we create the synthetic data sets. What's planned also is to have imagery simulations of jets and jetlets from Peter Wiper, gamma simulations of CMEs. So you're going to see the talk from Anna Malanchenko and Elena Povanikova to learn more about that. And there's an interesting pipeline to transform that into punch-like observations, and that's going to be covered also in, I think, in Sarah Gibson's talk. So my conclusions on all that is that there are many, many different methods. They all carry their own uncertainty. And so having these training sets is the #1 priority to see how good or how bad we're doing, and having really reliable error maps. Thank you.
Thank you, Raphael. As Raphael mentioned, good lead into the next talk for Valmir Filho from CUA at Goddard to discuss those synthetic data sets of SynCom. Thank you.
Hi everyone, my name is Rami Moraes Filho, and been working with Vajim and Barbara and Craig on developing this synthetic data, which I'm going to be explaining to you just now. So, an overview of the talk. I'm going to talk to you how we came up to the idea of creating this data set. Then I'm going to explain to you like what SYNCOM is, and after what data set we used, and what the solar parameters are, like what inputs are we using to create the training set. The flow tracking challenge, we're missing one bullet point there, but there's a section for forward, which we have been working with Sarah this past month, and some next steps of what we're planning to do. So for starts, in preparation for Punch, we developed this training set together with the idea that because we are working with the flow tracking group and we have noticed that there's no ground truth and we do not know the exact velocity that we are looking for, we decided to create a training set to help fill that gap. So basically, we're creating a training set with a fixed velocity, a fixed frequency parameter, and this will help validate and compare the different flow tracking techniques. So what SYNCOM is? A quick overview. It is a data-driven statistical model which will be used on testing flow tracking techniques. And the biggest idea here is because it's empirical, it's faster than a first principle model and imitates the dynamics of the solar wind. We're not interested in doing a one-by-one comparison of the solar wind with the model. We want to represent the dynamics and the frequency that it carries with the solar wind. So to prepare the flow tracking methods, we are providing the model with a target velocity, control environment for testing accuracy, and this will help us choose what the best method, and not only for testing the tracking velocity, but also for different conditions. And the building blocks for the model are the radio brightness, the periodicity of the features, and the target velocity of the solar wind. I have here on the image for you a simplified version of what SYNCOM is. Basically, we take the observed data, we do some data analysis, and then we create the image using Gaussian waves. So basically, as I said, Gaussian waves are the main agent for this model. We will take the observations, do some basic statistics to obtain the velocity, the frequency, and the radio brightness, the radio decay. So to simplify with the image, the idea here basically is that in blue, we are obtaining everything from the data. In red, we are getting everything that we obtained from the data and using that in the model, which will output an image that it's similarly to you see on the solar wind. So here's a side-by-side comparison of stereo and SYNCOM. This is a distant time plot, which is a projection of the radio flows, is a snapshot of the radio flows over time. We fixed the position angle, so that's why you're only seeing this snapshot. And the good thing here is that visually, you can see that the incline lines on both plots, they are similar in inclination, which that represents the velocity. The amount of features, which is how many times you see a feature, is the frequency, which also it's very similar on both cases. And the radio decay of the brightness is also represented in this image. So as an overview, SYNCOM uses Gaussian wave fronts with fixed parameters. These parameters are derived from re-observations, and it is statistically similar to the observed data. Like I said, we're not trying to represent one by one the solar wind, but get the dynamics with the statistics from the data. And we want the SYNCOM to be serving as a calibrator of flow tracking techniques because it has fixed parameters. So now I'm going to show you a synthetic image, which we have been developing since last year, which is a polar image with radio and position angle, which is similar to stereo type of coordinates. The control parameters here are the frequency, which will control each position angle, the radial velocity and the standard deviation, and the size of the features. The synthetic images have similar velocity and frequency. And this video, I have tweaked a bit of the contrast to make it more visible due to the radial decay. You can see now the features that are moving, they are more impaired with the actual image of the solar wind. The flow happens with a similar velocity and with similar frequency. And because of the contrast that I moved, you can see that we also have them like finishing about at the same height. Okay, so how I did it. The data set that we have been using is the data set that Craig prepared, which is a special campaign done in April 14 to 16, 2014, which is the deepest exposure of unpolarized images, which has a 36 seconds exposure once every 5 minutes over 72 hours. The altitude range, it's from the 4 to 15 apparent solar radii. The bottom pixels were cut due to the intensity. So it's like Raphael said, about 5 to 15. In practice, when you do all the pixels, we have 9.6 solar radii. And these are a set of raw unpolarized long exposure chronograph images that were prepared by Craig, which went under a coordinate resampling, smooth background, and stars removed, and the blur reduced by Gaussian filter. And this type of image is flow friendlier. The type of image that we have been using is the one on block C, but the instrument returned A, the coordinate resampling happened on B, then after all the preparation that happened with the images, we have the product that we have been using, which is on C, but to do the data analysis, we did another transformation, which is we changed the perspective of the data cube into the snapshots of the flow. So basically, you have the distant time plot type of figure. So the first solar wind parameter that we have is the radial scaling, which is observed. The observed data shows that the brightness will decay with distance, and we have averaged the entire range of positions in time in the radial component to obtain a trend. This trend is a power law decay, which the index can be measured with linear fit in the log-log scale. And we obtained a behavior of 3.04, but in the flow tracking workshop, Craig told me that should be 3. So the next parameter that we have is frequency. Is the frequency of the quasi-periodic flows. They're not specifically periodic because we're dealing with nature. So we are trying to get something that will resemble the frequency quasi-periodical. So the idea here is to search for the frequencies that will characterize the data, and we are looking at the lowest altitude, which is at the bottom of the image, which is represent about 4 solar radii at all times and position angles. The sampling time is 300 seconds for these images, and we have detrended the signal to make easier to extract the power spectrum. So the signal that we have on the image that you saw before, it's portrayed in A. Then we detrended that signal, which is in panel B, and then we obtain the power spectrum in C. Those power spectrums, we are interested in looking for the second peak because it carries the frequency information. We are assuming that these power spectrums, they have a similar idea of an amplitude modulation. That's why we're looking for the second peak. The frequency of the CMEs of these images were removed. One of them was characterized in the Craig's paper of 2018, which said that it was from 37 to 80. So that's why you see on panel B. And we are going to remove those frequencies and obtain the estimation with the detrended power spectrum. So the idea of getting the detrended power spectrum is thresholding the detrended power spectrum to a point to get a characteristic frequency, which is about 5 hours. The solar wind frequency can be possibly modulated by CMEs, because the possible CMEs that we saw in the data, if we remove them, the frequency would increase. So for the velocity now, we're using cross-correlation of 1D profiles, and we are using a brightness E-scale distant time plot. So basically, we are getting that image of distant time plot, and we're scaling it with brightness and obtaining the profiles for those and doing a cross-correlation. So basically, we're looking for the peak of those profiles. And we're going to do a time difference of an hour to obtain the velocity due to the lag of those peaks. For SYNCOM itself, this velocity, it doesn't matter because SYNCOM can receive any type of velocity input. So I could get the velocities done by Raphael and input on SYNCOM, and it will still work the same way. So in July, that's wrong, I'm so sorry. But in June 2022, we launched a challenge for the flow tracking, which in this case is to help the community to see the data and to have the input of other flow tracking techniques. So if you are an enthusiast of flow tracking, please go to the website and try the data in order for you to see if your code is working and for us to fine-tune the model. And we have been working with Sarah over this past month on implementing SYNCOM on Ford. And the idea basically is that we had to see the different way of how the blobs were implemented. And we had to use density as the accumulated brightness of each feature in specific position angles. So I have here a video over a certain time, and every time step, it's about 2 hours. And you can see that the density and the blobs are expanding outward after the time period that happened. It's still under debugging because we were able to make it work on Friday, and we're still getting all the bugs possible, but we have something working. The next steps are to try to implement an angular velocity because we know that after a certain height, the solar wind does have a movement on the angular direction, the variability with frequency, and also implement acceleration in a better way. We want to debug forward at least by the end of this month. And we are working on a paper to show, to actually put SynCom published, and hopefully by the end of the summer. And thank you so much for listening.
Our next speaker is our own Sarah Gibson, NCAR HAO, who will be discussing polarization, localization diagnostics, and forward modeling. Sarah.
Great. Thank you so much. So I'll be talking about the and we've talked about it as being a new capability that lets us localize structures in 3 dimensions, and indeed more generally look at the distribution of density in the corona and heliosphere. So I'm going to get right to it and talk about how this all works. So consider an object. Here's my blobby object, okay? And here is the observer at the Earth, this eyeball, and we're looking along a line of sight through the object. This is the sky plane. We're going to use Cartesian coordinates today, x equals 0. And generally speaking, you know where the object is in the YZ dimension just by how it shows up on that sky plane. So the trick is, how do we figure out where it is along the x-axis? Now, that brings us to polarization, because polarization is part of what happens when photons from the sun hits the object and you have scattering. And the scattering happens in a way, oops, there we go. The scattering happens in a way where, there it is, you have an angle of scattering which is directly related to how much polarization there is. And so when Punch observes polarized brightness, and it gets this ratio, we can directly determine the angle of scattering. And then from there, it's very straightforward to get the position in 3-dimensional space. It's just basically solving triangles. Now, I want to comment here that what you're seeing here is what's called the Thomson surface. And this is an important sphere between the sun and the observer. And it is the place where the scattering is maximized, because it's where the scattering angle is basically 90 degrees. Okay, now to really get into this, let's go use forward modeling. And this is a forward model based on a twisted Poisson model. So it's basically a shell of density with a twist. And this projection, now we've got the observer down at the bottom looking along the x-axis, and there's the Thomson surface. Now, if you integrate along the line of sight what you would expect to see in white light, polarized brightness and brightness, and take their ratio and solve those triangles and get out the position along the line of sight, this is what you get. And the cool thing is that it really works. What I'm showing is on the right, this is a model, so we have a ground truth knowledge of where the center of mass of the material is. And I've changed my viewing angle, so now we're viewing from the Earth, so 90 degrees from this view. And blue is basically in the back, I think, and red is in the front, and this is because you've got this Poisson sort of at an angle. So this is the ground truth, and this is what we get when we just take a ratio and we say, where is the position? And again, I'm plotting the position from the plane of the sky, x equals 0, so blue and red are in front or behind. Now, here's the problem. You notice this word back, okay? The problem is that in solving those triangles and solving that scattering angle, there are 2 solutions. We have an ambiguity of sign, and so we will always have 2 solutions for that position in front and behind the Thomson sphere. So if I had chosen, and of course I chose the right one, because this is a CME that's going off to the west like that. It's 100% behind the Thomson surface. I chose the behind solution or the back solution, and it looks absolutely beautiful. If I had chosen the other solution, it would have looked like this. So actually, blue is in front of the Thomson sphere. So you can see that if I had chosen the other solution, it would have always been positive x, and it would have looked very different, and it would have been wrong. So let's dig into this a little bit. So now we're looking from the point of view, there's our observer down here. Okay. This is a line of sight. And here, let's think that we're looking at a CME, and the CME is moving out along this purple line. So this is the trajectory of the CME apex. Still, let's think about a localized structure right at the top of the CME. Okay, so there are two solutions that we get for this first line of sight. The orange one is the right one. The purple one behind the Thomson sphere is the so-called ghost. And when you're really close to the sun, the Thomson sphere is basically co-located with the x=0 plane, so they're going to be one on either side. Now, as the thing moves out, so it's moving along this purple thing, there's the next orange dot of the apex, we have another line of sight. Notice they are not parallel because we are looking at a wide field. And so you can see here's the solution of the true solution, and then the back solution back here, the purple one, is wrong. Same a little bit further out. Now we've got a very steep viewing angle here. And again, we have the true solution here and the back solution. And here I want to point out something important, which is that when I'm talking about a position from the x=0 plane, the solution is symmetric about the Thomson surface. So once you get up here in the curvy part, you can have the back solution actually positive x. Now, what you can do is very cool, is you can show that if you were to map this apex and you were to look at these two solutions, one of them would be fairly sensible. It would be a CME going out radially. The other would be the ghost trajectory, which would be kind of looping back behind the sun in rather odd ways. So this means there is a possibility to get information about the trajectory and eliminate this ambiguity of whether it's in front or behind the Thomson sphere by looking at the time variation. Okay, so now let's take a case. That was a blob, a localized blob, and it's relatively straightforward. But of course, CMEs, these structures that are moving out, are more kind of, they have extent, they're more sheet-like. So let's take that Poisson model again, something which is more like a more distributed structure, and see what happens. Okay, so once again, down on the bottom left, there's the observer, there's the CME. If you squint, you might see there's a tiny little CME that's actually drawn in there, a little crescent, but you probably can't see it. But the point being that the front of it is, again, symmetric about the Thomson sphere, which right now is the x=0 plane. So now if I synthesize white light along the line of sight, the polarized brightness and the brightness, take the ratio, figure out the x solution, get my answer out, this is what I get, these two views. These are the front and the back solution. Blue meaning in front of the Thomson sphere, blue in this case meaning in front of x=0, and red meaning behind x=0. The point is they look identical because they're flipped about the x=0 plane, because the Thomson sphere is very close to that, down low near the sun. And you would not be able to know which one was right unless you had other reasons to know whether the CME was coming at the Earth, okay? You wouldn't be able to tell from this one picture. But look what's happening when it starts to move a little bit further out. So as it moves out, the blue solution really hasn't changed very much. This is the front solution. It's a little bulgy down here. That's because this CME is a little closer on the bottom to my eye, right? But what happens is we're starting to get that situation I mentioned where some of it has moved in front of the x=0 plane, so the back solution has a little bit of blue in there. And more to the point, I'm talking about here, the front, the apex of the CME, but what I'm actually showing you here is the integrated distributed structure. And if you were actually talking about a center of mass, it probably wouldn't be right here at the front. It would be sort of where this orange dot is, okay? And that's when things get weird. If you continue to let this structure go out in space, what starts to happen is that center of mass has moved behind the Thomson sphere. And now your ghost solution, which used to be behind the Thomson sphere, is in front of the Thomson sphere. And it gets a little complicated to analyze this. But really what I want to point out is that my front solution has been behaving rather sensibly, just staying blue, right? Meaning it's in front of the sky. Whereas my back solution has been doing something weird to the point that when I get here, I've got this weird Russian doll kind of red and blue type structure. And so this is the point, that even if you might not be able to point by point know which one is front and which is back, if you have a CME coming towards the Earth, the behavior of it, and that's the case we're looking at now, this CME is coming towards the Earth, the front solution to your polarization analysis will always stay positive X or blue, and all the points will get more positive with time. And I've compared this to the ground truth, and most of them are non-ghost. The back solution, the solution behind the Thomson sphere, starts out negative, but then it becomes positive with time. And ultimately, you start getting these piebald kind of structures. And I've compared, and some of the points are the true solution and some are ghost. The point is, even with one of these wide field images, you should be able to choose between a CME that's coming towards the Earth or one that's going away from it. And with the full trajectory, you could solve for the behavior of the surface to try to eliminate the ghosts. And this, just to show you that if it's going away from the Earth, the CME going away from the Earth, it's a much simpler analysis, because if it goes behind, it's always behind the Thomson sphere, right? The Thomson sphere, in this case, is coming out like that. So the back solution will stay negative in blue, and it will never be the ghost, and the front solution will stay positive in red, and it will always be the ghost. So this one, a CME going away, will have very, very obvious behavior in the way the structure moves. Okay, so something else that we discovered as we were doing these analyses was that we have another diagnostic here. So I'm going back to the twisted croissant model. We have a diagnostic of the background solar wind. So now we're looking again, here's the observer, there's the Thomson surface, and this time I'm gonna let that CME go off to the west again. This is now, I'm plotting the ground truth known center of mass position and the position we get from doing our polarization ratio. At this point, I'm not doing the red, blue, x positive or negative. I'm doing a distance from the Thomson sphere, which is an unambiguous, unsigned quantity. And as I already showed, it does a really good job. But what's interesting is, if you put in a radially falling off density background, like R, spherically symmetric is the most important point, but this is like an R to the -2, you end up with your polarization ratio giving you a constant value. And it turns out that it can be demonstrated analytically that a spherically symmetric density distribution has a direct, it will just look at the value of that background and you can get the slope. So we have a way of actually looking for any departures from a mass-conserving 1/r² solar wind density profile. And until now, we've had to do this by taking spacecraft at different points in space and measuring in situ what the density looks like and seeing if they really are following this 1/r². Punch is going to give us a visual on this that I think is a very interesting new diagnostic. And the last thing I want to talk about is chirality. And by chirality, I mean the twist of magnetic field around a magnetic flux rope. Polarization gives us our three-dimensional position, but the direction of the rotation, of the curvature of a structure will tell us that chirality. And essentially, you can think of this, if you look at a screw, right, a left-handed or a right-handed screw, you can see that left-handed chirality means you're going clockwise, this way, clockwise, from back to front. But if it's a right-handed screw, it means if you're going from back to front, you're going to be going counterclockwise. And this is something which DeForest et al. Took into consideration when they did an analysis of a C-shaped structure inside a CME, and they showed that when they did the polarization localization, that when they went from this point 3 to 0, that it went counterclockwise back to front. So they identified the chirality as right-handed, and indeed, when this CME hit a spacecraft later, it was a magnetic cloud with that orientation. And so we've done the forward modeling on this using that same twisted croissant model with a bit more twist. And here I'm showing, again, what I've been showing all along, a ground truth versus a one established by backing out the information from the punch type observable. And you can see it does a good job of basically showing the distribution, but you kind of need it to expand a bit more to see that direction of twist. And here you can see, as I let it expand a bit more farther, that indeed we've got a clockwise rotation from back to front, from dark to light, in the ground truth solution, and it's retrieved by the polarization. So let me conclude that polarization is a very cool new diagnostic, something that we've never had to this extent, filling all the chronographic and heliospheric imagers. We can get the position along the center of mass of a localized structure. We can remove ambiguity of front versus back by looking at time series and get a localized trajectory. I believe that we're going to have to do fits to manifolds of surfaces to really match those more extended structures. But this is something we can use forward models to test. We can distinguish between left and right-handed CME flux ropes, and the key is that'll tell you which way it twists, and then you need to know something about the magnetic field polarity back at the sun, and you have a diagnostic of the direction of magnetic field hitting the Earth, and if you have a BZ south, which is a space weather geoeffective event. And finally, we have a new diagnostic of the power law fall of the background solar wind. Thank you.
Thank you, Sarah. Our final talk is from Bernie Jackson from University of California to discuss further on polarization brightness analyses. Bernie.
There's some people who have helped on this analysis here. I'm going to about the UCSD time-dependent 3D reconstruction analysis that we do currently, and current IPS and SME analyses. And if you've been to SolarWind 16, I apologize. This is going to repeat some of what I said there. The analysis and modification of this is used to provide Thompson scattering pseudo brightness and polarization brightness, and you can use that to do the 3D reconstructions, and that's what I'm going to talk about at the end. The current tests of model and I'm going to talk about current tests of the modeled PB and PB analyses, and then I'm going to mention the what we need to do in the future that will benefit this work. So interplanetary scintillation, that's a ground-based system that's used to provide a proxy for density and velocity, flow velocity. And so that has been used in the 3D reconstructions. And I'm going to go through this pretty rapidly. The little fuzz over here on top of this time series is of a passing structure. That fuzz is the scintillation level, and that gives that scintillation, that is the scintillation of the radio source, and that gives you a proxy for density. The speed of the material across the surface of the Earth provides a speed of the solar wind. This goes around 400 to 800, whatever kilometer a second across the surface of the Earth, and that gives you a proxy for velocity. Anyway, what we do in this is the values of the weighting along the line of sight shown up here, and this down here, the fact that you get a perspective view from the outward flow gives you a location of the structure in 3 dimensions, and you can do that along each length of the line of sight by tracing it back to its surface. And I'll show this. This is for IPS, this is the source surface and the lines of sight that are present on the source surface in a Carrington map showing where the structures you see in 3 dimensions come from in a single view. Here's the second day, and from one day to the next this changes, and you use where that is and tweak the 3-dimensional model to fit a better source surface to provide an iterative system. You iterate back and forth between what the differences are on this surface relative to what's seen in 3 dimensions to get you a best surface model that you invert in a way at the surface to provide the 3-dimensional model. Okay. One of the recent good examples of this was a CME that was observed on March 10th, 2022, and this was seen in forecast. You can see here the ecliptic cut. Earth is here, sun's there, and you can see the CME just about ready to reach the Earth. Here's a view, a meridional cut through the Earth's, and this of course is the CME that occurred about 2.5 days earlier. This is a measurement of the model and ACE data at Earth, and you can see that's a fairly good correlation between what's reconstructed as a model and what's present at here. These are 1 day, so it's a fairly low resolution result, but nonetheless you can watch this material come out. This is a synoptic of Carrington cut at the top of the thing. And one thing to take away from this, the Earth's here, this is the same time as you saw before, but the CME has reached 1 AU. This is a 1 AU map to the west and above the sun. Anyway, this is just to show that, yes, the CME is present. By the way, though, there's quite a bit of the CME that's still flowing outward several days later, and that's not generally shown in most of the forward modeling analyses that are present. Okay. There. Anyway, here's another plot. One of the good things about this event was that Solar Orbiter was in line with Earth, and Bepi Colombo was aligned with stereo. And so you can get the ground truth of what was happening before it arrived at Earth and stereo, and you can see that the reconstruction really did work at that time. Okay. ENLO was used in this too. It gives a different result, and you can see that. It does not show the structure that's present and flows outward following the onset of the event very well. Okay, so I'm going to talk about Thompson scattering analysis. This is the three-dimensional. This is the solar mass ejection imager. It was launched in 2003, ran for 8.5 years. It provided strip images that were put together in a sequence that allowed this. The brightness of the line of sight response is quite a bit different seen here and you have both brightness and polarization brightness. Here, I'm going to talk a little bit about the idea of a traceback matrix. The way this works is to trace structures from one height in the sky to above the sun to another, and that in doing that, you know where every portion of the line of sight is present at the source surface, and you track each element outward and determine what the speed and the density are in that. But with Thompson scattering light, where you had a few, maybe 20 or 30 radio sources it's 200 radio sources in a day. Now you've got, and over a period of a month where you need to deal with this reconstruction, you've got some maybe 2,000 or so lines of sight. Now with the Thompson scattering analysis, you've got several million lines of sight. And this is showing 1/25 of those on the Carrington surface from one day to the next, and how they match and move in a 6-hour difference at the surface in the time-dependent way. This was an event that was seen, and you can see it here. And once you have the analysis, you can do a lot of things with it. You can highlight it and see what the excess mass, the total mass, and the ambient mass is present in this analysis. This was a CME complex that was seen on the 27th and 28th of May 2003. Anyway, this gives you when you do this analysis at the highest resolution, you can get 1-hour cadences from the solar mass ejection imager, and that's shown over here on the left as a time series plot at Earth relative to ACE here and wind data. The analysis gives the dashed line there gives the same values, but actually the ground truth kind of comes in at a different thing. And you'd have to do this over a whole month period, or at least enough days so that you can see the material start to move out all the way until they get past the lines of sight. That's so you can see what flow has proceeded. Anyway, There. One of the things you find at high cadence is that you can see what's pretty much mesoscale structure. The structures in few degrees, as they pass Earth, provide an analysis. You can see a point here, you see another point here, and that point's just shown at the beginning of at 1 AU here that comes out. And it's interesting to see because there's really a lot of structure in what's seen at the CME around, and you reconstruct at 1 AU. This is, of course, an ecliptic cut here, and here's a meridional cut, and this is a cut at 1 AU. Okay, so what about PB analysis? Well, first of all, what I've been able to do then is take this analysis and provide a map, and you can see now what the reconstruction shows as a remote view. This is the same event, and I tried this just to make sure, because I knew this thing pretty well. This is a sky map that's seen. You can see structure here and how it goes back towards the sun. This is an ecliptic cut, and this is a meridional cut, and you've seen those two before. I just showed you that in higher resolution. For expediency, I didn't use the highest resolution I could. But once you do that, you can provide pseudo lines of sight through the volume to see if you really reconstruct from the densities themselves. Can you really reconstruct what you saw as that's the first test. Can you really reconstruct this event with the pseudo lines of sight that come through? And the answer is yes, of course. The lines of sight that are traced through the volume, the density volume, give you back the event as you see it here in these different manifestations, including an ecliptic cut, a meridional cut, and so forth. Well, now you have polarization brightness, and you can make pseudo lines of sight polarization brightness, and you can try that. And so this now is the PB analysis of the same event shown, and you see the structures there that are pretty similar from just the polarization brightness, the different weighting that's present along the line of sight gives you a very similar answer. And then there are caveats to this analysis, but the point is here we've been able to use the polarization brightness as well as brightness in this iterative procedure to provide the three-dimensional reconstruction of this event. The caveats are the analyses show images interpolated at a given instance in time, not how data were actually obtained over a period of a few minutes, with each line of sight different from one another from the IPS or the SME data. To be expedient, I used lines of sight only from the density proxy observations, not the proxy speeds, and I gave these times of the line of sight, not the actual images, and these were made into data files and reread into the program. The images show volumes where data were sufficient to make an accurate 3D reconstruction, but to provide the pseudo lines of sight, each volume was filled completely, and then that pseudo observation used. Future work that I need to do, I need to provide these PV analyses, the intermediate analyses and others with higher resolution and with less smoothing to provide in the analyses. The raster scan volumes in both brightness and polarization at bright punch locations with random outage lines of sight. I need to raster scan the images rather than use the lines of sight that are already present, that were available, and that is another interesting thing that needs to be done. If you could use correlation tracking of velocities, it would be good to attempt from the stereo data, if you can, to compare with inner heliospheric spacecraft or SME pseudo sky maps. And right now we use the IPS to get velocities, but that helps locate the structures in 3 dimensions, because you want to know what the flow is. And then I also want to compare correlation tracking with the IPS velocities when I can get them. Here's another example of data obtained with mesoscale structures. This is the October 28 Halloween storm event, and you can see this is the event that took 18 hours to get from Sun to Earth. Here's a structure about 18 hours later, seen in the data here, and you can see a lot of structure here that's out approximately the distance of Earth, and presumably, although you don't have any ground truth around here, this is the shock seen there and the structure that's seen at mesoscale features. So anyway, I make that a little bigger. And one of the things you can see is this, which is the actual flow of the backgrounds from the IPS that shows that it was very high speed behind that shock front. So it's pretty evident that this is a good there. Anyway, in conclusion, the 3D reconstruction analysis, this IPS and SME white light analysis works pretty well, and the modification to provide Thomson scattering from polarization brightness gives similar results. The current tests of pseudo P and BB analysis give essentially the same results, and so for other enhancements, well, I would like to use multi-node processing and image brightness correlation tracking for this punch, so that will enhance what I'm currently doing. Thanks.
Okay, thank you, Bernie. If we could get the 4 speakers up to the stage so we can have our panel Q&A session. Thank you.
Okay, so once the panel gets empaneled, we can start with the questions. I think most of the questions came from people in the room, so we'll start off with Alphonse had a question. I believe this is directed about the tracking. Do the density structures you track account for the bulk of the solar wind mass? So, Raphael, I think that was a question for you. Others, please chime in. Okay. Okay.
Yeah, so you were showing you were tracking these blobs out in the solar wind, in the heliosphere. Basically, I wonder if the mass flux of those blobs, if that accounts for most of the mass flux measured in the solar wind, or might there be some that's beyond that that's really smooth, for example, and not in the blobs?
There's a button at the bottom of your mic to turn it on. There you go.
Right. So I don't think we can account for all that mass, because I think the way the images were pre-processed by Craig, there's a lot of background removed. So I guess some of that mass is removed, if I can say. So I think it's, whatever mass is staying above that removed background, that's accounted for.
Okay, so at some point it might be fun to know what percentage of the solar wind mass flux that could account for, small or large.
Yeah, sure. Is that actually possible with Punch, Craig, do you think?
Sorry to jump in. The data that we have from Core 2 are consistent with, but do not drive the conclusion that the puffs are the solar wind. Right? They could be, they could not be. With Punch, we'll have the ability to do absolute background subtraction on PB, at least in the inner field. And so we should get a better measurement of that.
Okay. Okay, so Nor has a comment?
I think the answer to that is not conclusive because you have an optically thin corona, you are integrating along the line of sight, and you will have blobs in the line of sight that are fuzzy because they are on the wrong location along the line of sight. So, yeah, you will be selective along your line of sight. That's what.
Okay.
I have a related question. So you are sure this mainly, as Ralph said, is the 2D structures, velocity, direction, and velocity. But for the even for the PV observation, it has a 60-degree coverage in around the planet sky. So can you tell something about the 3D structure if flow is away from the planet sky? For example, if you have use a stereo A and B, when the angle is 3, you could get the flow pattern from both satellite. Then you can see if they're triangle method to get the real propagation direction.
I think it's.
And then you go ahead. I'll go. I think we all want to answer.
I don't know if we can. For the data that I have with the deep exposure campaign, I don't think we have we don't have the deep exposure campaign for both stereo satellites. So it's not an analysis I could do with the track data that I have. I don't think I can compare it. We don't have the data to do that comparison.
And I can follow up on that. So one thing, it's probably a good time to make it really, really clear also that with Punch, we are not doing any sort of stereoscopy. You know, we only have the one point of view, and it's because of that polarization diagnostic we can get some localization along the line of sight. So to the extent we have a truly localized dominant blob moving along the line of sight, we can add that three-dimensional information, or in theory, we can add the three-dimensional information. To the extent we have, I think Nora was saying, a whole set of blobs along the line of sight, it becomes more complicated how you would use the three-dimensional location in improving the flow tracking that you're talking about. For a CME, like a transient event, it's more straightforward to do the three-dimensional trajectory.
Bernie, you need to turn your microphone on, please.
Yeah. The iterative analysis that I do locates structures, whether it's in brightness or polarization brightness, along the line of sight. So you can see where this is just from a single point in space. It has to fit, and that can work even better, at least in theory, with when you have polarization brightness, a brightness to polarization brightness ratio, so that you can use that as well as just the outward flow and other things to provide the analysis. Now, the outward flow really is important here because that shows more or less where structures are, not only close to the Earth, but in the other side of the Thomson sphere. And the iterative system that I've developed actually shows where this has to be according to a model that more or less moves things radially outward from the sun. So anyway, that's how this system works in the analysis, the iterative analysis that I do.
Can I ask Bernie just a really quick follow-up?
Okay.
Really quick, sorry. But you will have the same issues about whether you have like a lot of blobs along the line of sight. You will still have ambiguities just because what you're looking at is intrinsically projected if you're using punch data in
If you
particular.
can follow the blobs, then you'll still be able to discern where they are along the line of sight. It's just that it's not as accurate a way for specific little blobs of determining where you are relative to the Thomson sphere.
So if you can localize them, you can follow them.
Yes.
Also, can I add a comment on that?
The discussion.
Let's
discuss.
There is also an advantage that I want to exploit with the magnetic ball tracking that I'm using. So when you have, regarding this line of sight uncertainty, you can end up with magnetic ball tracking, you're able to really accurately have the dynamics of neighboring blobs. If they are actually in like sort of different plane, you would expect the apparent velocity to be different, but they would be so close to each other. And so being able to actually resolve that and having these dynamics separated, well, you can actually see that. I mean, what I'm hoping to analyze is that with the time evolution of them and the direction, the way they evolve through it over time next to each other, then we can disentangle whether or not they're either in the same plane, sort of moving close to each other in 3D space, or they're actually very well separated in 3D space. And this is kind of the dynamics that I plan to analyze with a fine resolution that magnetic ball tracking allows. That fine resolution is not something you may get with resolution tracking, because, for example, with correlation tracking, because correlation tracking sometimes they have this apolization window that can blurs out a little bit more with respect to magnetic ball tracking.
Yeah, in the IPS, the structures that are viewed in flow are tiny. They're a few hundred kilometers, and you make a approximation of where they are by the actual weighting present along the line of sight in scintillation level. And that's different from the Thomson scattering, where you're measuring blobs, and the blobs though are far larger, and so you hopefully can make a statistical analysis of the line of sight dispersion for the blobs, and sort out whether these are individual pieces side by side moving out, or if it's really along the line of sight. And this is unknown yet, and really something that needs to be experimented with, if you can, right now with stereo, I think.
Okay, that's good discussion on sorting out all these different structures in the solar wind. I have a specific question here for Vladimir about from Craig. Are you yet adding a scale spectrum to Synchron, or are the features all roughly the same size?
What do you mean about this scale of No, it was a different scale.
It looked to me in your slide like they were all more or less the same size.
No, they have different sizes.
Okay.
Because
my eyes were fooling me.
I modulated the size by the wavelength of each one. So basically, I got the frequency of each blob and the velocity of each blob and multiply both of them. But how about the other scale you said? Like, scale of... Okay.
And just to comment that with once he's got this as a density model, which he's talking about, we can test these techniques about the 3D location when you have the blobs of different size and different frequency along your line of sight, and how much you get, it messes up localization.
Yeah, because the thing about Ford is that we had to create three components. So we randomized the components, but now they have a sphere in space, basically. And for Ford, they have the same size. Like, because on SynCom, I kind of did them on the bullet shape. So their position angles, dimension, it's half of whatever they are in radio. But for Ford, it's a sphere. For the moment. For the moment.
Okay, I have a question here from Steve Kramer to Bernie. How close to the sun can the IPS speeds be measured, and what is the overlap with the punch field of view?
The IPS analysis, how close can they be measured? Is
yes.
This, yeah, the normal, they can be measured in weak scattering at 327 megahertz, and this is about 11 degrees, as close to the sun as you can get in elongation and angular distance from the sun. Now, that's at 327 megahertz. At some other observations like LOFAR, which is sort of a lower frequency, the weak scattering starts at about 20 solar degrees, and so that's about as close as you can get. But even so, and that's where you can get flow velocities. But that does overlap with punch.
Yep. Okay. Thank you. Trying to spread it out a little bit over the panel here, but this question's for Sarah from Craig again. Your Russian doll simulation of the CME cores are terrific and give good insight into the geometry. I guess the question here is, how have done the sims on the CME sheath leading edges, question mark?
How has this?
Maybe it's a spell check. Have you started doing sims on CME leading edges as well? Basically the spherical sheath around.
Yeah, no, not yet. And the other thing is, this is a croissant kind of it's a tube, right? And you would probably want to have it denser at the front. And so that's probably the quickest and first way we could try to get at that question.
Okay, let's see. One's from Bill. In the coronal ball tracking with existing data sets, do you ever look at the PDFs of the inferred instantaneous radial speed? And is there a tail of negative values?
So the PDF, can you repeat the PDF of what?
Where you have blobs moving, right?
Yeah.
And you associate a speed with each of them.
Yes.
And I guess if you measure that speed at relatively relatively short times, I'm pretty sure that some of them are going to be moving down. And the question is what fraction are moving down? Michael Bird, the old Michael Bird observation of downward blobs.
So I also track them manually by eye to get a training set. And on all the things that I've manually tracked myself, there were nothing moving down in the data set that I had.
I thought I saw some moving down on the movies.
So you may have seen the red crosses moving sometimes.
I was looking at blobs. I'll show you in the movie. But if you average over a long time, they might all move up. But for relatively short time, certain features.
We can see the movie again together. You can show me that. But regardless, the uncertainty on the individual motion of them from the tracking is larger than the possible backflowing velocity that I could get. I discussed that with Rohit also, because he had a similar question, whether or not I could measure backward moving flows. So I think that would be, the amount of velocity would still be within that error bar. So I would not be really able to catch that systematically.
You do think that some blobs move downwards, or you say that no blobs should move downwards?
No, I think if they do, it would be too slow for me to catch them, given my error bars.
Nor you have a follow-up?
Comment in the question for the line of sight thing. There is one thing, if we can figure out how to do it, is the depth over which we can resolve the blobs. That is, because if we can figure that out, you can let the corona rotate and you can actually come up with an estimate for the solar wind. That quantity is so important, but I'm not sure if we can. The question now, when you look lower down, in particular in the corona, within the same structure, you have differential speeds. I'm not sure if these differential speeds will carry over when these are higher up in the corona. So how can we track these different speeds within the same structure? I'll take, for example, the jets. The leading edge doesn't move at the same speed as the core.
So the capacity in moving different speeds within the same structure, it is a capacity that I partially have. That really depends on how large that structure is. But yeah, I can, like in my movies, I only showed you only a subset of the tracking balls. So you have like an example of, I think, 2 CMEs in that movie. Within the CME, you have actually many balls tracking different parts of it. And that's an example where I can track different velocities within the same structure. So that is possible to a certain way. But again, there are really error bars associated to that, of course. And it really, in the magnetic ball tracking, it still relies on the ability to track local extrema. And sometimes if you don't have a local extremum, just like in lots of optical flow techniques, the ball would be sort of free to move along it, and there would not be constrained, and that's not a real velocity there. That's part of the error bar.
Okay, let's go to another question online. This is from Rashid. This is to Bernie. Is it possible to separate shock and CME leading edge signatures using this method? If so, how well are they resolved separately?
Well, you reconstruct things in 3 dimensions. So the only real handle you have on shocks is, well, you should see an enhancement in the density and behind that a high speed. Now, if you can get flow high speed, and you can see that in the background solar wind behind a density enhancement, then darn, you got a shock if it's at least a high enough speed. Now, what the IPS showed in the last slide, it did show mesoscale structure, or at least structures that were seen that were not a simple thing. So the shock appeared as density enhancements in little patches all the way along, and the high velocity, though it's low resolution, was right at the boundary of that, was right at those pieces. And the pieces, by the way, looked like they, at least in the ecliptic cut, looked like they were more or less aligned with the 45-degree angle of the magnetic field. So it looks as if the shocks there are provided with a, or at least the enhancement is not a continuous thing, not a nice smooth surface. So that's what we got from the solar mass ejection imager. Hopefully that will be borne out with punch.
Okay, let's, another question from Bill for flow tracking. Are the blob sizes to some extent dependent on the threshold imposed on the data analysis? What is the density contrast between blobs and non-blob plasma?
You mean the sizes of the blobs? You're asking if the sizes of the blobs is...
What's the density contrast between blob and non-blob?
Oh yeah, that's actually, I found that it's highly dependent on the background subtraction. And yeah, so the contrast is, I don't need to have a perfectly accurate background subtraction. As long as I have local extrema within the density structures, that's enough for me. So,
like 1,000 to 1 or 10% difference?
Oh yeah, more like, yeah, 10-30%. Between 10-30%, I would say, yeah. It's, well, I don't have a lot of training sets though, I've only trained with this Core 2 data. It's one, I subtracted the background in a Craig-like way. I tried different variations of it, and this is how I could measure the differences that I get in contrasts. It is.
There's 2 different answers to that. One is, if you really meant to ask what the radiance contrast is, it's about 10%, something like that, right? That's what we've all been coming up with, a few percent, depending on the background subtraction. The radiance contrast is order of a few percent. The density contrast is an order of magnitude. And you get that by estimating the excess density in the blobs and comparing to the average density of the solar wind at Earth and extrapolating inward. Right, so you can sort of get a measure, but you don't really know for any one blob.
Okay, let's take a question from in the room. You had a question?
I want to follow up on the problem of the thin corona and how we interpret the 2-dimensional flow maps, considering that the actual flow is 3-dimensional, obviously. And it's going to be very, very difficult to disentangle, the 3 dimensions from whichever method you use. And my suggestion is that it would be important to get a clear understanding of the velocity distribution we should expect from a three-dimensional outflow with a narrow velocity distribution defined locally. Because you will see different velocities on the two-dimensional plane just because of the projection effects.
Yep.
So it would be very important to know how broad this like sort of effective distribution will be just because of the projection effects.
Yep.
That's going to be like a baseline for anything else.
Yep.
Yep.
Yeah, can I comment on that? One thing it's important to point out is that that beautiful Eye of Sauron, gorgeous flow thing we've been talking about and modeling is from a time in the solar cycle when the streamer belt is, the ballerina skirt is flared up. It's more or less seen edge on. And that's really nice for localizing things in 3D because it means that those blobs are all kind of mostly in the current sheet coming out and you could probably get them. When it's more solar minimum type configuration, your current sheet is going to be a little bit flatter, or well, quite a lot flatter, and so you'll be looking through a lot more. So my point being with respect to what you just said is that velocity distribution, we need to think about the solar cycle effects and the orientation of the current sheet in affecting those velocities.
But
yeah, that's fine.
Yeah, but hopefully that'll sort itself if you can see the distribution at one location along the line of sight, and you'll be able to see higher speeds over the poles at solar minimum and slower. Yeah, and as long as you can see the background, then you should be able to determine this. You certainly can with IPS, but whether you can or not with the blob flow, I don't know.
Just an extra comment on Vadim's question is that the error bars that I've seen in my talk, these are only showing the pure precision of the measurement in the reference frame. That does not include the uncertainties related to 3D. So I really want to make the difference between precision and accuracy there. For so far, I am only measuring the precision of the measurement as if I had a ruler and I'm telling you how precise the tick marks are on that ruler. I do not know what is the accuracy of that ruler intrinsically. Yes. Yes. Absolutely. Yeah.
Okay.
I have a question for Sarah. So you demonstrate with the forward modeling, you can get the 3D structure of CME without a background. And finally, you say if assume it's uniform decrease, then you can consider effect of background. But however, consider in the stereo Cohen or LASCO C2 field of view, the background streamer actually has similar PB as CME. So in this case, I wonder how accurate you can derive from single view observations. And if there's a strong effect, and from what distance you can ignore the background effect.
So you're talking about using the polarization ratio to diagnose the fall-off, radial fall-offs of a spherically symmetric background.
Because the background is not uniform. You have a lot of streamers has similar brightness as CME in PB.
Okay. So first of all, we're talking about further out in the field of view, in the wider field of view. So the simple solution is when you get far enough away that you can think of the sun as a point source. So you want to be already out a few solar radii for that. So close to, we're not talking about close to the sun for this analysis. So from what distance you can ignore?
From what distance, how many solar radio, you can ignore the effect of streamers?
Right, so you would want to be observing, I think you put it this way, Craig, you want to look at solar minimum when the streamers are nice behaved and at the equator, and you do this analysis in the spherical sun away from the streamers. Because you're right, the streamers are going to be different in general in the streamer stock. And so this is kind of a background spherically, you want to set yourself up by looking at a time in the solar cycle when things are fairly spherically symmetric to make this analysis most useful. That helps. Solar maximum will be better in other ways. Solar maximum will probably let us trace the blobs and the 3D flow better in some ways. But there really are two completely different diagnostics. One which wants localized structure and one which wants completely spherically symmetric diffuse structures. And they give you two different pieces of information. One is the location of the localized structure, and the other is just the slope of that sort of spherically symmetric background. So they really are kind of different objectives. That's a good question. I feel like Nikki answered it yesterday, or maybe Craig. Somebody answered this yesterday. That we designed the telescope to do this. So it was, how localized does it have to be localized?
There has to be a gradient. But if it's distributed structures all along the line of sight, it's not going to be localized at all. But it only has to be a little bit localized. I mean, you showed it in your CME. So CME is not localized at all. It's actually quite a big structure.
Yeah.
It's just brighter than everything else. And so that's why it works.
Mm-hmm. But we designed the polarimetry such that we could locate compact structures to within approximately 1 degree out of the sky plane. And so, for example, CMEs are not local, but by the mean value theorem, the edges of CMEs are local, right? So you can always locate those, right?
I think that was an excellent discussion, and that should wrap us up on time. And let's thank the panel. And
A question from Craig again, but there were another question from Craig.
there were several questions we
Slido.
didn't get answered, and I would like to remind everybody that you can have a conversation on Slido if your question did not get asked in the room, or if you have other questions, we can continue the conversation online. And I assume somebody knows more about lunch than I do. So
It's now for 1 hour.
None of you are upvoting questions. Even if you don't have a question, please go online and help the chairs determine which questions are the ones that you think will be most useful for the discussion.
But let's thank our panel.
All right, so we are reconvening at 1 p.m.
session's going to start in a minute. All right, so our next speaker is Anna Malanushenko from HIO UCAR, who will talk about interplanetary CMEs and punch. So, we do have an audio recording here. I don't know. Okay. I was not told. Steve will show you a 3-minute sign when you have 3 minutes left.
That sounds good.
Okay.
Thank you. Okay. So, hi everyone, and this is a presentation related to Punch Working Group 2A, interplanetary CMEs and Punch.
Can you step a little closer to the mic, please? Thank you.
Okay, how about now? Okay, so this presentation is related to the activities of the Punch Working Group 2A that studies the interplanetary CMEs. And the reason behind this working group is that Punch will help us address several useful, important questions about CMEs, such as how do they propagate, how does the structure evolves, what can we tell about the magnetic field in CMEs, what is their role in the interplanetary magnetic field, can we study the magnetic reconnection, can we study the association with co-rotating interaction regions, and of course we need to have a better understanding of the shocks and the energetic particles. So those are all the reasons to study CMEs. Well, but Punch hasn't launched yet, so in the preparation for Punch, we do not have the data right now, but we do have the MHD simulations that we can use to mimic data to test our analysis techniques in preparation for the launch. And the data I'm talking about will be done with the Gamera MHD code. And basically, in a nutshell, well, we do have the solar wind, the WSA solar wind, in the volume between 0.1 and 1 AU, and we immerse the Gibson and low magnetic flux rope into it, and as a result, we get a model of a CME in the inner heliosphere, and Elena Provornikova will talk more about that. And I will be talking about some of the things that we can do with Elena's data. So here I'm going to present to you the CME Challenge version 2.0. If you've been anywhere around Punch in the last year, you've heard the conversations about the CME Challenge. This is the version 2.0. And as before, it is a synthetic punch-like data using Gamera MHD simulations, and it has both polarized brightness and total brightness in punch-like field of view and projections. And the idea is that we have simulated several synthetic events. So those are not simulations of any particular CMEs that have actually happened. Those are simulations of some completely imaginary CMEs. And they all have different properties. They emerge in different areas in the solar wind. And they have different sizes, magnetic fields, chiralities. There's a set of properties that will vary. And the reference case number 0 is the case for which all of those properties are given to you a priori. So if you want to simulate, if you want to test your methods for CME reconstructions, you can download this data and compare your results against something that is known. And this does not only apply to the CME reconstructions, but also to flow tracking and whatever else image analysis you might have in mind with Punch. The 3 other events are the validation cases. Their properties are not disclosed unless you ask me to, and the reason to do it this way is to help you strengthen the validation of your analysis techniques. So think of it this way. You can get the reference event and figure out that you can read in the data, you understand the units, and everything is well. And after this is done, you can try and deconstruct the properties of the other several synthetic events blindly. And after you've done that, and you ask me for the results, I give you the correct answers. That would be the fact that the correct answers will match the reconstruction techniques will be a very, very strong validation of whatever method you have in mind. So that is the idea. And this is what some of those, this is what one of those events looks like in the essence and the shape. So this is the reference case, and I'm just showing the volume of the CME as it evolves through the time. The left is the view from the North Pole. The center is the face-on view, as in the halo CME, and the image on the right is the limb CME. So the event is the same. What is different is the position of the observer. So the observer is not exactly the Earth, but again, those CMEs are not exactly a model of any particular CME that had actually happened. So we have an imaginary Earth, and we have an imaginary CME there. But we have real lifelike observations. That's the idea. You heard me talking about CME Challenge, and now I'm talking about CME Challenge version 2.0. What changed is that we updated the way we immerse the flux rope into the wind, the way we did the synthesis of the specifically polarized brightness, the determination of the ground truth parameters, and I will talk more about them later, and also in what kind of data products do we provide. So in version 1.0, this is just a table. In version 1.0, there were 3 events, 3 viewing angles, all the CMEs, all the observers observed all the CMEs on the western limb. I will talk more about the subsequent 2 lines later. Then the storage, I mean, we basically uploaded everything onto the Google Drive, and you had to ask me for a link. And the MHD cube from which we could derive the correct answers, again, whatever you define the correct answers to be, and it would terribly depend on your analysis, but we could derive the correct answers with the density cube, and we didn't store other variables. So this time we did the homework. There are more events, there are more viewing angles. There is something that I will show in the next slide, which is a 4-pi coverage. And the in situ, again, I will talk more about it in a second. We are working with the HAO and with the HAO website to have the data be available there. But again, due to the volume of the data, most punch-like observations will be available just straight off the HAO website, if we can make it work. And the big bulky 4-pi coverage will be available in Globus, but again, the links would be much, much easier to share, find, distribute, and everything. And this time we're storing all MHD variables for comparisons, and not just in the volume, but after the CME had reached 1 AU, we are storing the data on the 1 AU shell, and by data I mean also all MHD variables. So they can be used for validation analysis, and so on. Now, when I'm talking about 4-pi, okay, I'm going to take advantage of the fact that I'm presenting from my own computer, but it is an interactive preview of, in this particular case, the event number 0. Now, imagine that we have an observer that can be anywhere around the sun. So with all my due respect to Kepler, this observer has absolutely no mass. This observer has absolutely no physics in it. It's just a little camera that can be anywhere. And this camera sits put in space with respect to the distant stars. And whereas, for example, what Punch will observe, Punch will be near Earth, and Earth orbits around the sun. And in the punch-like, the normal punch-like data that I produce, that is taken at an Earth-like orbit, the observer is also moving about the sun in a similar way as an Earth does. Now, in this 4 pi coverage, the observer just stays put with respect to the distant stars. But the position of this observer can change. So this is just an example. So this is a view from the South Pole. This is a view from the North Pole. Different longitudes. This tool can be useful for a quick look, but I'm also storing FITS files, and those are of a big volume, so those will be available in Globus. And also for every given observer, this is a synthetic camera that will give us not only punch-like imagery, but also in situ data, if you wish. So it will give us the profiles at 1 AU of the MHD variables, and again, that can be useful for comparisons with the in situ instruments. That is the idea. Okay. Okay, I did say that. I did say all of that. Now, the ground truth data. And what do I mean by ground truth data? Don't I have the 3D MHD cube? Didn't I insert the CME that has the angular width of 60 degrees and the velocity of 1,500 kilometers per second? Well, not quite. The thing is that the CMEs interact with the solar wind. So, for example, for one thing, they slow down. So we can insert the CME at 1,700 kilometers per second velocity, but then it will slow down. It will slow down substantially. And I'm saying slow down is if we track the volume with time, and if we feed the position of the frontal point with time, we can measure the slowdown. The reason why we are also keeping track of that is because this mimics the existing observations. We do not know the starting properties of the CMEs, or at least we don't always do. And when we do the image processing, this is basically what we do, but based on the line of sight integrated data as opposed to the analysis of the 3D MHD volume, which is why I'm calling it the ground truth data. Yes, and the trajectory changes. The CMEs expand not uniformly, as is evident in this very image. And then there is the snowplow effect. And again, when we do the image analysis in coronagraphs, we may or may not be able to tell apart the actual ejecta material versus the snowplow solar wind material. So this ground truth determination is including the snowplow material. So hopefully that kind of helps mimic the observational techniques. So that is the idea, and we also record the shape of the CME volume at time. And here is the current status of the project. The simulations are done, the projections are done, the ground truth is done. The 4 pi is done for one case and in the process for the rest. The in situ is in the progress as of right now. The bulk data can be downloaded via Globus, and we are working to put it to make it available of the HAO website. Okay, and I have a few backup notes that I will skip with your permission because I'm running low on time. But what I wanted to say, well, actually, how about that? I will just go to the very, very last slide because the notes and projections are just fine technical details. So that's a lot of data. It's available. It's not a lot of data in the sense that Facebook has a lot of data. It's not a lot of data in the sense that stellar astronomers have a lot of data, but that's still an awful amount of data. And it's there for you to play with. So thank you very much.
So our next speaker is Kurt de Koninck, who will talk about what we think we know about CIRs and SIRs.
How do I move the slides forward?
Oh, where's the remote? Where's the remote?
All right, so what we think we know about CIRs and SIRs, about co-rotating interaction regions and stream interaction regions. What's going to be said and shown is my work, or is my responsibility, I should say. The work is actually due to others. There we go. So what is a co-rotating interaction region? Well, in its simplest form, a co-rotating interaction region is when a parcel of fast solar wind plows into parcels of slow solar wind. Because they plow into each other, they will cause a bunch in... Is there a laser on here as well? Okay. Okay, and so the fast solar wind will plow into the slow solar wind. Because of the frozen-in magnetic field, the fast solar wind cannot entirely penetrate or interpenetrate the slow solar wind, and so you get this region in between the fast solar wind and the slow solar wind, the stream interface, at which point their deflections, speed or flow deflections occur. So that's a very quick verbal definition. A little bit more detailed is again shown from this paper from Borofsky and Denton, where we do have fast solar wind coming in over here. We have then a region of compressed fast solar wind, as the blue dotted line is the stream interface, followed by compressed slow solar wind, followed by more normal slow solar wind. And again, you can see shown in here that there are regions where the flow is deflected because of the, at the stream interface, because the magnetic fields can't penetrate, or because the plasmas can't penetrate. So what's the difference between a CIR and an SIR? They're both very closely related to each other. Is a SIR, a stream interaction region, a rapidly evolving co-rotating interaction region, or is a CIR a steady state SIR? When I first wrote it up, the abstract and presented it to Vic, Vic took a little bit of issue with the definition that I came up with, which started off with the SIR, and he wanted me to start off with the CIR. So to some people, I guess it does matter a little bit which is which. But at any rate, the important point is, the important distinction is that there is time dependence in this process. Even a CIR is not really entirely steady state. It is evolving in time, it is evolving in space. Wrong one. There we go. So here's a quote-unquote artist view taken from Suratani 2006, showing another possible way what a CIR may look like. This is a CIR that's emanating from a polar coronal hole with a equatorward extension. And so it's intersecting the ecliptic plane, or the ecliptic plane. A more quantitative definition of a CIR, for those that are interested, can be found in a paper from Marty Lee in 2000, in which he goes at least into a relatively simplistic or simple ideal CIR, but it does get more quantitative than what we've just been, the verbal definitions we've just been talking about. Of course, most of what we know about CIRs we have gotten from in situ observations, and there are, beyond these plasma observations, there are of course also magnetic field observations, and the observations are changing from between solar cycle 1995 to 2004. You can see that there are some differences in the way the different plasma parameters are looked. And so again, when we're launching Punch in a couple of years, perhaps we'll be looking more at this type of a solar cycle than the previous one. What is a CIR? Well, from a white light point of view, this is getting a little bit closer to where Punch is at. A stereo was able to observe CIRs in total brightness. Punch will of course be observing it in polarized brightness. But this is a paper, or an image from a paper by Wood et al. From 2010, in which the top panels show what Punch, or excuse me, what stereo saw, stereo A and stereo B, and then in the bottom is Brian Wood's attempt to model what the observations. And that model is based on the following shell envelope of material that maybe what a CIR looks like. One of the earliest reconstructions of CIRs that I found actually comes from Tappan et al. In 1984, in which they used interplanetary scintillation data in order to image a CIR. So again, there have been observations going on a long time, including attempts to get at the geometry, the 3D structure, not simply the in situ observations. So a lot more can be said about CIRs. Like I've already hinted at a little bit, there's information about the deflections in the solar wind flow direction at the stream interface. There's the question of where do shocks form, what is the orientation of the shocks, and most of what we know has been learned from in situ measurements. And then if you're really interested in going into detail on what we know about CIRs, take a look at the most recent review paper is by Ian Richardson in Living Reviews of Solar Physics, published in 2018. So if you really want to know more of the nitty-gritty detail, especially the in situ observations, that's the paper to look at. Punch is going to be approaching CIRs in a slightly different way, or in a much different way, using remote sensing. And Punch will measure then, using the remote sensing technique, will measure really the scattered brightness from a line of sight integral or a line of sight integrated mass. And we're going to try use this information then to do a reconstruction, a 3D reconstruction of CIRs in the sense that Brian Wood showed. But one of the questions that is going to arise is, since it is a line of sight, observations from a line of sight integrated mass, is are we looking at a simple structure? Are we looking at a complicated structure? How much is in the foreground? How much is in the background? How then do we really interpret what we're seeing? And one way to get at that question is to use a technique that I came across looking into backgrounds, papers from Vic Pizzo, in which he basically back in the 80s and possibly into the 90s as well, really did a lot of groundbreaking work on how to model, understand CIRs, looking at the flow parameters, the in situ observations, and he started off with a whole series of idealized or of ideal simple coronal holes, propagated the material outward, and then asked what are we going to see at in situ observations. Well, we want to do the exact same thing, except instead of asking what are we going to see in situ observations, we're going to be constructing synthetic images of PB and total brightness and polarization ratio and see what are we going to see. And then based on these ideal coronal holes, can we interpret then what we're seeing in the real world images? So here, this is an example taken from one of Vic's papers in which he's looking at a very simple circular equatorial coronal hole with a certain speed profile from slow to fast, looking straight at the equator. Possibly the observer is looking down on the sun, or the polar coronal hole is somewhere in the north. The coronal hole is in the north, or maybe it's a polar coronal hole. So we can make all sorts of variations, of course, and just see how do these variations impact what we're seeing in polar or in brightness, in total brightness and polarized brightness. Here, Vic has changed the width of the coronal holes, greater north or south width, and then we can change the side structure of the coronal holes. If we put structure on there, would we see this kind of structure in polarized brightness, or is it going to get washed out as the solar wind as you integrate through everything that's in front and behind? But again, that's the questions that we want to look at. And then here is an example of a coronal hole, a polar coronal hole with an equatorward extension. Again, these are the kinds of things we can look at. And then also the standard tilted dipole coronal hole. So I messed up on in the next part. Dushan tells me that he did send me in synthetic images, even from equatorial coronal holes, I was not able to find these images. And so all I have to show you is a synthetic image that Duchamp prepared from a tilted dipole, in which we're seeing total brightness over here, polarized brightness, and the brightness ratio over here. And as Duchamp pointed out to me just before, during lunch, these images are a little bit harder to interpret than stuff coming from a nice circular coronal hole. So that would have been nicer to look at, but like I said, I seem to have lost those images. So sorry about that. But this is then what we want to do. We want to look at these images and then ask the question, how does that compare to what we see in reality? And does it look anything like what we see in reality? And if it doesn't look like what we see in reality, is there something perhaps that we're missing in our understanding of CIRs? And that's really where of course, Punch is going to come in, and where even in the lead up to Punch, where we should be not just in the CIR community, but in the entire Punch community, we should be throwing out our predictions of what we think we are going to see, and then be able to validate those, our understanding against these new observations. And that's the best way in which to make sure that we understand our material, is to actually make a prediction before the data arrives, so that we can't skew our prediction to what we know we're going to see. And that's what we want to be able to do with CIRs. And then the question is, will Punch confirm our understanding of CIRs, tweak our understanding of CIRs, or revolutionize our understanding? And that's it. Thank you. I should have read the schedule.
Our next talk is Philippe Hess from the NRL about outflows, big and small, remote sensing observations of solar eruptions with ranges of sizes
I apologize
and
for
energies.
the size of the title.
Sorry.
Hello. So for those of you who don't know me, I'm on the Whisper and Solo High Science teams, and I'll talk more about those in a minute. But so this talk, I was graciously asked to come here and give a version of a talk that I gave last year at the COSPAR meeting in Athens. That was really focused more on much smaller scale things than what I'm typically used to looking at, because I'm generally more of a CME researcher. But when we first started with Parker Solar Probe data, we didn't really have many big CMEs, but we still had a lot of really interesting small scale features that I think are worth talking about. Now, fortunately, I don't think I need to go into much detail of why these things matter, because based on the discussion we had before lunch, you all already think they matter. But basically, these are small things, they're little blobby things, they're not space weather effective, but they are very important in terms of how that structure goes from the closed low corona out into the solar wind. So I'm going to be talking basically what we talked about in the discussion before lunch, but from a very different perspective, literally, because I'm going to be talking about images from the Whisper white light imager on board the Parker Solar Probe and the Solo High imager on board Solar Orbiter. I also want to get into some definitions, because at least I know I'm guilty of, I see something kind of amorphous and ugly looking in a coronagraph and I say that's a blob. And I think there's a lot of that, but really the streamer blobs, if you go back to the papers, Neil Shealy was writing, they're a very specific phenomenon. And that's, you get a helmet streamer, it gets somehow sort of enhanced or starts swelling, something pitches off at the top and it erupts out into the plasma sheet. And then you have these streamer blowouts, which are just kind of ugly CMEs, which you have a filament or a cavity or something low down in the corona, usually near or beneath the helmet streamer. It sort of somehow gets destabilized, goes out into the plasma sheet, and not with enough force to sort of reorient the corona around it, it just kind of gets channeled out. And then lastly, the pseudo-streamer eruptions, which I don't really have as much to talk about. I added them in here because I know we have the session tomorrow about jets, and all these things is essentially large-scale jets that still kind of look like blobs in the coronagraph, but really are something very different. So this goes back to one of Neil's and Yiming Wong's papers from 2007, where they really started talking about blobs with a lot of in-depth observations. And basically, you've got a lot of different events here. there's the question of sort of the inner and outer parts. That's what this is, where you had a reconnection happen about here, something collapsed and something else is going out. And some of these look very small and narrow, some of them look wide. I think a big question about this is still how much of that is, these are things at different scale sizes, and how much of that is just sort of the angle at which you're looking at things. If you look at the height time data in one of these JMaps, this is where the reconnection was. It's not enough there to really see because they need to pile up some material around them. And you see this very clear outward part and this downward part that probably has a speed of about 50 to 75 kilometers a second. So then when you get into blowouts, this is a paper Yiming and I wrote a few years ago where we saw some of the same phenomenon, except again, you don't have everything forming and pinching off out in the corona. Instead, what you're really seeing is a very gradual rise of a filament. It just gets pushed out into the plasma sheet, and here's where it reconnects, and you see this sort of stalk behind it and all of these collapsing loops behind it, and you can still see some of the inflows. On this next event on the right, it's really the same thing, except then the streamer blowout, I think, kind of forms some small streamer blobs behind it because that open field gets pushed apart and then comes right back together and reconnects very quickly. So then the last one is this paper this is just a shameless plug that doesn't really have much to do with anything, for a paper that should be out sometime in the next few days that Yiming and I wrote about pseudostreamer eruptions, where we're seeing these sort of very collimated, bright, but very narrow features in the coronagraphs. And when you track them back to if they're on the limb, you always see this very clear pseudostreamer structure behind them. And as I said, these are big jets. And I know there's a lot of more interest in jets now. If you look at the cartoons from the pseudostreamer eruption papers and the cartoons from the jet papers, it's all the exact same thing. It's just that here, you need a much larger multiple to actually get, the force to generate them outward, so they're far less frequent. But when they do happen, they're brighter and a lot easier to see. So then this also came up in the discussion earlier, where it's sort of the importance of perspective. So this was one of the events we looked at that we thought had more of like an L-shaped source region, where down here, we had what we called an inflow stream, where you just saw a bunch of narrow things sort of collapsing at a bunch of different position angles. Meanwhile, up here, you had a streamer blowout that goes out, and then behind it, you see this sort of arcade behind it with these loops falling down on top of it. Our argument was, this is the exact same thing, you're just seeing it from two different angles. And when you're looking along the arcade, you see the loops that are, at various depths on your line of sight, sort of falling one after the other. When you're looking at them from the side, you're seeing them all sort of collapse individually at different locations. Going out, it's the exact same thing as going in. So now we'll get into the new data. So this is Whisper. This event here is from the first event we saw when we first turned the camera on in 2020, a very clear streamer blowout CME. We tracked it from the low corona and saw it get deflected out. It might not be easy to see, but there's a very clear dark cavity feature here, this sort of bright envelope V structure behind it that's pretty common, and the very gradual acceleration profile that we'd expect from a streamer blowout. But in addition to that, we also saw a bunch of these sort of repeated outflows happening over and over again right at about the equatorial plane. And we thought, okay, these all look like the same thing. They're just happening at very different scale sizes. So as we got further into the mission and things got a little more active, but still not quite there, it was a little easier to track some of these things. So I put this LASCO C2 image here just for reference because this is encounter 8 for Parker Solar Probe. We were flying right through here. So the streamer belt looks fairly flat and fairly located in the equatorial plane. So then this movie here, all of these movies are provided by Guillermo Stenborg at APL. The LT movies are his version of a processing that removes the F corona without removing the more stable K corona. So that's where these are the individual sort of streamer stalks that are all for the most part located in the center of the image until you'll see at some point about here, well, actually a little later, or a little as the movie keeps playing, but eventually they'll start to kind of fly to the top and bottom of the spacecraft because we're flying into them. But at first, They're all located in the center of the image. Then if we go to these other movies that are processed more as sort of a running difference type thing, but not exactly that, you see this very repeated outflow happening of these same position angles. And I think a point I really want to make here is to kind of push back on something that was in Craig's slides this morning, where he showed the Core 2 data and then the High 1 data and said, here's where we're transitioning from the sort of well-structured coronal structure that we see in Core 2 out into High 1, where now it's sort of this unstructured mess. And it's really only an unstructured mess because from High 1, you do not have the resolution to see this. And I think what I've learned from years of now looking at WSPR data and also the Solar High data, I mean, these imagers sort of combine the coronal and the heliospheric field of view in a much more homogeneous manner. And I think, to me, I see that structure persists much deeper out until we just kind of lose track of it. And I think no matter what your observer is, you're eventually going to hit that point where you lose track of it. And it's just a matter of figuring out, I think, both scientifically and physically, and then also observationally, how far you can actually track these individual features. So now this is Encounter 10, which I included because now we're flying through here, where there's streamer stalks kind of all over the place. The bright one is down to the south, but there is still some up in the equatorial part. And in the image, there's a lot more sort of position angles where you still see a lot of bright structure coming out. And if you go in now to the more difference-based image, there's also, you'll see more streamer blowouts in here because there were more CMEs. But you don't see that sort of very repetitive black and white banding. I mean, you see it a little bit after the streamer blowout. Instead, you see a lot of activity happening at a lot of different places. And again, to me, this is a very well-structured area. So another way to look at this is, the one on the top left is called the J-map. I'm sure many of you know that. Those have been around for a long time. With WSPR, a J-map, which is an elongation versus time map, is not the most useful thing because your perspective changes so much. So on the right, we've got an R map where we've taken these J maps and converted them into an estimated solar distance. And you can see here how much the field of view actually changes. This last one is what we call a lat map, where we actually take a strip along one elongation in the heliosphere and stack that up instead of doing elongation versus time, this is latitude versus time. So one thing I do want to note is, for a while, these products were just available to the team. We have now started providing them on the encounter summary pages at whisper.nrl.navy.mil. So if you go to a given encounter, I don't think they're all there for the earliest encounters yet, but everything at least from 8 on, you'll be able to find these. But what I really want to mention is, so this is taken at the orbit plane, which is roughly the equatorial plane. And in orbit, encounter 8, where the current sheet is pretty much right in that orbit plane, you just see nothing but continuous outflow going off one after the other. And in the lat map, everything looks very flat, very flat. Then here's where we actually fly through the current sheet, and that's why you see this sort of curving up and curving down. We come out of the current sheet, and again, very flat, very flat. In encounter 10, things look a little bit different. And while you still see a lot of outflow, I mean, some of these are CMEs, there's a lot more periods in here where you can't see any individual structures flowing out along the equatorial plane. And I know you kind of have to take my word for that because this isn't really a quantitative analysis, but it's there. And in the lat map, I think, is where the difference is the most striking of all, because you've got now a lot of structure happening to the north and the south, and you don't even really have the very clean current sheet crossing that we had before. Instead, you just sort of see near perihelion things happening everywhere. So another interesting encounter for some kind of similar reasons is one of the more recent ones, encounter 14, where now we're actually flying through this. So there's a helmet streamer kind of off to the south as we're going through it. And now we see a ton of outflow happening down here along to the south. You still see some up to the north just because the current sheet, you can see it's so sort of off axis. There's things happening everywhere. But this is really the first time that I think we've seen this stable of a very continuous streamer visible in our data from, for an entire encounter that far off the axis. So that's why this is a fairly interesting period for us. So this is an event that I've been working on with a few people. I know Dan Seaton will recognize it quite well. We're finally about to get this paper out, But this is just sort of one of the ways that we're trying to use the WISPR data along with the rest of the HSO and the in situ instruments on probe to really try and track what we're seeing. So what we saw was, and I didn't include the Solar Orbiter EUV observations, but we were able to track a prominence that was on the limb in Solar Orbiter, you can see where that was, that seemed to be erupting straight towards PSP. At the same time, Stereo A was able to see something that just kind of looked very weak and faint and amorphous. And then in WISPR, we had this sort of interesting thing here where we had these loops that just sort of overtook the entire field of view. And I think all of us, when we first saw them, says, that looks like we're flying through something. So we did a lot of analysis on this event. We looked at the in situ data, which has sort of a weak flux ropey structure to it. And we said, all right, what we think happens is this was a streamer blowout of a prominence. It wasn't the most clear signatures in the remote sensing data, but Parker Solar Probe still flew through it. We imaged it as we flew through. And for me, the big question of this event, to bring it back to how long can we track these things, the spacecraft was at about 0.25 AU when we flew through this. So I've always wondered, what if we were at 0.35 AU? Would we still have been able to see it in the in situ data, or would it have washed out? Would it even have shown up in the imaging data if we weren't that close to it? And I think this is sort of the heart of the problem when you're looking at these events now. And what I think came up this morning is this question of how long is this structure really a structure before it just breaks down? So I'd be remiss if I didn't also show some Solo High data, because we've finally started taking some very good science images. These are large events, but I wanted to show them because they look nice and they're a good representation of the data, but also what I was saying before about sort of the blur in High 1. So that this is Core 2 here, and this is High 1, this is C3, and this is the inner part of the Solo High field of view. These things are all projected onto the same heights, and they're all kind of looking in the same direction. And we can just resolve so much extra structure from being closer and from having the short exposure times that allows. And you really see, I think, in this event, how much extra blur gets introduced in the inner part of the High 1 field of view. So this is just another event that's from one of the Solo High tiles, because Solo High is made up of 4 different tiles that are combined together, where we saw these sort of very slowly propagating loops that were going out without seemingly really reconnecting. And so I looked at LASCO, and they kind of showed the same thing, where there were some CMEs, but eventually it takes some time for you to actually see these loops erupt and collapse. So we're really trying to figure out what exactly is going on with these. It's still a work in progress, but I think what we found so far is that it's because the current sheet is so disrupted, you've got big decayed active regions forming this loop structure, and then you got coronal holes on both sides of it with the right polarity that nothing ever reconnects until finally it does. So they just expand out much far higher up than we're used to seeing until you finally see something erupt. So I think that's pretty much it. I think I'm just about out of time as well. I just want to say that we've got this new generation of heliospheric imager data that I think is really able to provide us with a much better view of some of these smaller features. And I think Punch, because of the polarization, even though it's still at 1 AU, is going to be a very good complement to that. These are encounter-based missions. These are not going to provide synoptic images, which is another advantage for Punch. But I think what we found with all of this data so far is it's very hard to interpret what we're seeing when you're flying through something. You need that consistent, good synoptic imaging from well behind you so that you have the context to actually put those local images into perspective. And the last thing I want to hit is this last point, that the complexity of these observations present new challenges, and we need to be very careful how we present and analyze these. Ritesh Patel, who is here, has submitted a paper that shows from one of the recent very big CMEs just how wrong you can be if you just try and sort of use these images as stereo too. These are new missions, and you really got to be careful and ready to think in a new perspective if you really want to understand them. Thank you.
Our next speaker is Shahida Begum Shahi from George Mason University and NRL. We'll talk about the nested rings. Okay.
Yeah,
I'm not allowed to say titles anymore.
Sure. Thank you. Yeah. Shahida Begum Sheikh, or Shahi in short. So I'm going to present about this nested ring CME cavity. observed on 20th January 2021 by Whisper Imager Onboard Parker Solar Probe. So let me proceed. So thanks to Phil, who already gave an introduction of Whisper images and how the images looks like. And we know that it's only imaging instrument onboard Parker Solar Probe, which observes a little bit offset from the sun from 13.5 to 108 degrees. Can I point here? Yeah. So in general, we know that most of the CMEs that we have observed so far have shown a three-part structure as what we see there. So after the reconnection takes place on the sun, we know that the plasma, the plasmoid, or flux rope filament gets ejected and seen as this in white light observations, which has a bright leading edge, cavity, and also bright inner core. So here what we see in Whisper is so that's CME, so which is not very similar to what we have seen so far with the three-part structure, but in other words, it shows, how do I play that once again? Okay, so let me, yeah. So it shows those nested structures within and very faint. And the speed of this CME was around 300 kilometers per second. And now let us see that the same movie in a better processed view. So as we see there, what we have is the CME is almost uniform in terms of brightness. So what we see is the alternating nested bright and dark features. And if you see in the neck with time, I have that just to give you a visualizing picture of that. So previously, there are some studies which have shown how a nested ring can be seen on the top of a filament. So where Sarah, Simon have done a lot of work in showing how we can see those ring-type structures on the top of the filament. And also Yu Hong has done a simulation where if we take the cross-section of that flux rope, we see those nested structures. So these are all on the pre-eruptive stage of the flux rope, not in CME, before the CME. So there are rare observations or rare studies which have seen ring-type structures as what we see here in LASCO observations from Deer et al. As an example. So now looking at this CME, so the CME was happening on the backside of the sun. Stereo and LASCO has the observations of the CME. Parker was right after the perihelion, right there in the orange dot. And on the top, what we have is the planes of sky of all the three instruments. The blue one is basically LASCO. So now we are looking on the top of, from the North Pole. So this is LASCO observation, here stereo, and what we see there in very, very gray color, light gray color is Whisper observations. So why I have this is basically at that time when we have the CME in the field of view, so the planes of sky of Whisper and the stereo are almost parallel to each other. So basically, we are seeing at the same structure of CME from opposite direction, Parker Solar Probe from there, and stereo from this direction. So I'll quickly run this movie just to give an understanding of how the source region is. And we see that some restructuring of the magnetic configuration happening on the backside of the sun as the source region is in the backside. And we see some spiraling structures on the limb. And if we move it forward, let me skip that. So now if you look at the multi-point tube with LASCO, C2 and C3, those are kind of faint because one of the CMEs is on the backside of the sun. So here we see that at the same time where we see the nested CME, there's another CME happening on the other side, which has also the nested structure. So we're not going to talk about that, which is another big story. But for now, let's focus on the nested CME itself. So for this particular CME, I have applied the graduated cylindrical shell model, GCS model. So what we have here is basically stereo observations. I don't know. Okay, yeah, there it is. So this is the CME seen in stereo and LASCO and then Whisper. So we see that the fitting fits very well with all the three perspectives of the same CME, and these are the model images from the model. So now what comes is, what are the questions that we can ask with these nested rings? So first is do we know whether these ring structure is common in CMEs or not? If yes, why it is not seen frequently? And second one is, are the rings one coherent structure? Do they move with one coherency? And the third question is, what are these nested rings? If they are just the flux rope, where within the flux rope do we see these rings? So those are the questions. So let's focus on the first question. So to answer that, I would like to do that in two different ways. One is observationally, another one is physically. So observationally in the sense, do we see those rings by the instrument that we are using or not? So for that, what we have here is the comparison between Whisper on the left side, and stereo on the rightmost side. So this is the default processing where we do by background subtraction, all those things. And what we see here is we don't see those nested structure at all. But if we apply a little bit more processing on that, we start seeing the cavity regions here compared to the Whisper. And also we see the front, but still we see that it's as a very blurred structure which cannot resolve what we see as in Whisper images, right? So now I would say that for the conditions that we need to see such finer structures is one, we need to have a good viewing angle, in the sense, if we are seeing this Whisper, the same CME from some other angle, I don't think we would have seen those rings at all. So it is important that we need to have a good viewing angle of the CME to see such ring type structures. And second one is angular resolution. For example, here in this particular CME, the angular resolution around 0.16 AU for this particular CME was around 30 arc seconds. And for stereo also it is 30 arc seconds. Even though we have the same angular resolution, we are looking at the structures from a very different distances, right? So with Whisper it's 0.1 AU, and stereo is almost 10 times bigger space at 1 AU. So the observing distance also is important, and exposure time and the sensitivity of the instruments. And we also know that from the talk of Sarah this morning, so Thomson efficiency is also important to view the right structures of the CME as what we have here. And white light integrating effects, in the sense, if you see here, even though we are seeing that but same CME, so as we are seeing at the optically thick emission and we are integrating through the front structures and the backside structures of the CME, we are completely blurring them off, and what we see is that almost like a uniform pattern than what we have to be seen. Right? So now coming to the second question, do all CMEs have these nested rings or not? So for that, we can question something like this, where we can say, can the CMEs which are accompanied with eruptive filaments only show such rings or not? Second one is, or is it just the geometry of flux rope? The third question is, are these rings present depending on the size, age, and the formation of the pre-eruptive flux rope itself? So let's talk about the first two questions later. So these two questions. Let's talk about the third one. In order to compare this nested ring CME as seen in inner heliospheric imagers, we need to make a correspondence to the source region. So we don't have a very good, robust data set to make that comparison. So we have a very few examples, like Phil has shown us in Encounter 10. We see those nested structure there. And also a few observations from LASCO have also seen such rings, but we don't have a very good studies previously done to make a very good correspondence between the pre-eruptive flux rope and the erupted flux rope. So now let's move on to the next question of the coherency of the rings. So here I have taken 4 different points on the flux rope, and if we just draw the x distance from for all those 4 points with time, we see that they all follow the same pattern, same slope. So only with little jumps here and there, that is because of the CMA after some point becomes deformed. That's what we see a jump here. And here we see that jump because after a point the CMA unwinds, and this last point basically creates a distance between the third point and the last point. So because of that, we see that jump. But in other words, what we see is all of them have the same slope, showing that they're all moving with one consistent pattern. But all those measurements are from plane of sky, right? So now we want to look at the projected velocities. So I will skip this slide for a moment, but if we look at this diagram, the phi2 minus phi1 is basically the longitudinal extent of the CME. If we measure that from this method, so the difference that we see is much almost comparable with the error that we have in that method, so which is not a right method to use. So now we are working on getting the projected velocities to see whether those nested rings have different velocities and see whether they are coherent or not. So next, third question is to understand what are these nested rings itself. So what I have done for that is previously from in situ observations, we know that a magnetic structure of the flux rope looks like something like that, where inside the flux rope, the magnetic field orientation is axial, and on the outer surface, it's more tangential. So having that in mind, and also in the other scenario, where a three-dimensional structure, in the sense, the two-dimensional projection of a three-dimensional structure looks like that, which can create those rings. So having that, and if we apply the GCS model with those scenarios, what I have here is, instead of having one flux rope, if we take one within inside, something like that, just to recreate that, not physically, but having a representation of that flux tube structure, what we see is in model images, we can recreate those nested rings. And in the second case, still, we can, if we shift the apex of the flux ropes a little bit longitudinally and the backwards, we still see those nested structures. So in conclusion, we can say that whatever we are seeing there in whisper images can be from the cross-sectional or the internal structure of the flux rope itself, plus the projections as what we see here. Right. So I was happy until that, until I saw this animation. Thanks to Sarah for bringing that to my attention, where it gave a little bit more understanding of how the orientation of the flux rope really matters to understand what are the internal features of the CME itself. So if we play that movie, so as we see that it's a simple three-dimensional mathematical flux tube. If we change the orientation of that, at some point there, so this is what I have in GCS where we see a circle, but if we move to some other degree, let me, oops, I don't know. How do I play that? Yeah. At some point, you see that, is there any chance that you can pause it? At 90, yeah, play, yeah, you can please play it. Yeah. At 97 on the top, or 270. Previous slide, please. Yeah. And play that. Yeah, you can stop right there, yes. Little bit backwards, please. Sorry. Yeah, this is good, yes. So what we see here is basically, so this is what we are almost seeing there, right? So so far I was just looking at the nested structure. So if you are looking at this V-shaped structure in the CME, so which is almost similar to what we are seeing here in the modeling. And also the second feature is if we see this herringbone type structure in the backside of the CME here, so those structure basically overlaps of the legs of the flux rope itself, right? And also if I see in the top of this flux rope, so I could never draw a single circle or a clean circle in here. Why? Because here we are basically looking at two semicircles which are overlapped with each other to make that circle, right? So that's what we see, a bright feature there, and we couldn't make a clear circle there. So this is an example where we can see that different orientations as what we see here can show us, mislead us to understand that it might be a filament or it can be the flux rope itself. So answer those two questions, whether those nested rings are from the filament or not. I would say they are from the geometry of the flux rope itself, not from the filament. So now, just to finish up, so relevance with this punch mission is basically, this can be a good example or a compelling example to show that how a three-dimensional perspective of CMEs are important, where the working group 2A of punch is basically working on to understand the dynamic evolution of the transient events, and the 3D view of the CME structure, and to understand whether there is a chirality or the helicity of the flux rope itself, and also the interior details as what we have seen in this example, and also have the polarization effects, where, for example, here, as I see that, so these two different legs of the flux rope can be seen as differently in polarization measurements. So yeah, so I'll stop there. Thank you.
There we go. Okay. I think the earliest question from this session is from Craig to Anna. About the CME challenges. Do people have to reveal their inversion results in order to see the secret ground truth results? You have to turn on your mic.
I would redirect this question to the audience. What does audience think about that? How should we go about this?
Sealed envelope. Yes, you need some sort of skin in the game.
I mean, the idea of blind testing is golden standard in medicine, for example, but the question is how to apply it here. So what do people think?
I'll jump in. I think people don't necessarily have to reveal, but they really ought to have an archive that you hold of their inversion. It can be secret, but you really ought to stick your neck out. And that's okay, we're all among friends, but that's rigor.
Timestamp, a time-stamped archive, an exchange of the sealed envelope with the simulation results for the simulated, for the ground truth answers, and like Craig said, we're amongst friends.
Or maybe some kind of pre-registration, right? In some studies, you have to at least take note that you're going to do something, even if you haven't done it yet, right? All right. Where are we up there? Bill had a question for Phil. He says, you contrasted the appearance of intervals seen in different instruments, but can you clarify the difference in scale when you have the striated versus the more cloudy flocculated structures?
Could you please clarify that? Like, what exactly you mean?
Well, because of the character limitation, I had to make it into haiku. But you showed pictures that had things that looked more disorderly on one side and more striated on the other side. But I didn't understand, I know they were different instruments, but what was the point there? Was it the point that the features were at different scales?
Okay, actually, I did a very poor job explaining that because I was rushing through. Those were the same instruments. Those were both the Whisper and our telescope. They were processed differently. So in the one image where it was more striated, we purposefully left the more stable K corona features in. So that's where you still had that very bright streamer stalk that just sort of persists. then when it gets more flocculated, that's because you still have a lot of transients coming along that streamer stalk that you can image. They're faint, and that's why you'd have to remove the streamer to actually see them. And so that's really the point, is that all of these things are only going out if you can see that sort of bright, striated plasma sheet there.
I have to weigh in on this because this is a different type of processing than we use for high, of course.
Yeah.
But yeah, we all have to be very careful about what we're removing when we remove a background. And so that's a really good point that we should all bear in mind.
Yeah, I mean, it's
morality play, if you will. Go
yeah,
ahead.
I mean, it's really one of the most challenging things with Whisper, because like what Dan was saying, where with Punch you can kind of do the more sort of traditional, we're going to take a month of images and generate a minimum for a background. With Whisper, our scene is too different from image to image, and especially across the orbit. So you kind of have to play with the gradients to bring out different features.
So I guess there's, oh, I'm sorry.
No, I was just going to say, it took me, just make sure people know how to do the upvote to help with the questions. Make sure you organize by recent, and then you do a thumbs up to do an upvote on the Slidos.
Good advice for the session chairs, too. Yeah, there's a couple different questions for Shaheda about the rings, right? How do you really, I think there's two different independent questions about how do you really tell the difference between whether it's a true ring or some kind of illusion or projection effect or whatever else?
Yeah, so the first aim for me to look into this is that question, whether these are real or not. So instead of taking any processing or background subtraction done properly, and if we look at the raw images of that, still we see those nested structures. And there are few other examples also where instead of seeing something like this, where we are looking, line of sight is through the axis of that flux rope, if we are looking from perpendicular perspective, we still see those helical shaped flux rope, which basically shows that it's not an illusion, but it's a physical property of the flux rope, which shows the helicity within. And if we are viewing the same helical flux rope from the other, like slinky, right? So if we are moving in the other direction and make a little bit offset from the axis, we start seeing those rings. So I don't think these are illusions, and we are still working on modeling to see whether they can support these nested structures. Yeah.
Yeah, we're all very concerned about the ways that we could possibly be fooled when punch data start to come down.
Yeah,
so we
that's
want to
right.
always ask these questions.
Mm-hmm.
Yeah. What else? Question for Kurt about the fact that CIRs have a lot of mesoscale structure within them. And the question is, what scales will punch really be able to detect, and how will that be able to help us understand the substructure that might be in CIRs?
I think Craig can probably answer a little bit better about what scales punch can, I think it is. Is it on? And they've got a bright light here. So I think Craig will be able to better describe what scales punch can get down to in terms of a CIR substructure. And of course, the other question that is going to be the issue is what we've just been talking about, is doing a line of sight integration. How much of what we think we see do we really see? So how much is going to get washed out? How much is just going to bunch up and look like something that we think is something, when in reality it's just an optical illusion? And the only way we're going to find that out is by having actual data. I mean, we can probably try get simulations, more accurate simulations, more realistic simulations, but even there, you're only seeing what you're putting in, and even there, I think we can easily fool ourselves.
Any questions from within the room?
For the Anna, I noticed in your synthetic images, the streamer looks like a spiral features, not a radial ray shape as ASCO observed. Does that mean something wrong with the model? Artificial effect? It's just like a Park spiral, the streamers. Oh, Anna.
Sorry? Oh, sorry.
In your synthetic images, I
Mhm.
see the streamer is not a ray shape like Lascaux observed, but shows a spiral features. What does that mean? Is that something wrong?
No, I don't think there is anything wrong, and I do apologize. But the questions about how can we tell whether a flux rope is an optical illusion or not, they really made me think. But so yeah, I apologize for that again. So think of to answer to your question, think a Parker spiral, right? And this is a radial expanding structure, and it has some spiraling structures. Now intersect this Parker spiral with the Thomson sphere, and you get some curve. Right? Now take that curve and apply the fisheye distortions, and you will get even fancier curve. And I think this is what we're seeing.
Dongyang, she's looking from the top down, but also Lascaux is closer to the sun, right? And she's showing images beyond 20 our sun, where you have Parker spiral.
I mean, pretty much all the way to like if the field of view is 45 degrees each way, then you're pretty much seeing the quadrature.
Okay, there's one other question for Shaheda, but maybe it should be generalized to everybody. And the question there is, how might the 3D localization from the polarization be used to help discriminate between the different things that we can see? And the example was distinguish rings from projection effects, but it's also CIRs, it's also different CME structures, it's also streamer blowouts and all that. I'm curious.
To start with, I would say that if not at the internal structures of the CMEs, for now, if we are looking at the, for example, two legs of the CME, one in the front and one on the back, then it will help us to, for example, this example which I have shown, it's basically overlapping structure of both the front and the back legs, right? So if we have that, those measurements, we can distinguish that, no, it's not one leg, it's basically two legs, and we can make a much better sense of the CME structure itself.
Do you think having the chirality, the left or right sense, would help in the interpretation?
Yeah, that's very important, is what I feel. Yeah.
Anybody else has thoughts? Please chime in.
Well, what I would very much like to see before we can even start answering that question is the simulation of two structures. And in one structure, there is a projection effect, and in the other structure, there is no projection effect. And we know that because we're looking at the simulation volume. And if those two structures have similar or similar total brightnesses, similar polarized brightnesses, or similar qualitatively, then what does the difference in the polarization ratio would show us? I mean, before we can even start answering the disambiguation question, I would like to see those two synthetic examples, but I cannot think off the top of my head on how to do that.
Hold on, Bill, one more.
So I think that this rings issue is very interesting. And if you think about it from the point of view of spheromax or reversed field pinches, when you initially set up the system near an equilibrium, the helicity is conserved on separate flux surfaces. As the system evolves dynamically, there should be microscopic reconnections that link them so that at a later time, there's only one quasi-conserved helicity. So if it's real, there's something really interesting about the evolution of CMEs that could be investigated, I guess. But it seems to me that would be worth at least mentioning in that kind of the study that you're doing. I mean, can you tell whether the rings disappear as the thing evolves?
No, they won't. So at some point of this CME, the CME becomes pancaked or deformed. So even after deformation, we see that the rings itself got squished. and they still propagate into the whole field of view of WISPR.
But if it's dynamic, then eventually the rings should just be smeared into one structure.
They get smeared a little bit, but they don't vanish from the whole structure. They really get swished here.
I have a question, if I may.
I have a question for Kurt about the co-rotating interaction regions. I like your slide, the last slide that you showed, like what can we expect from Punch mission, right? We either confirm the previous sort of picture of the physics of these regions, or maybe we can actually find something very different, which will revolutionize our understanding. So can you give us specific examples? What can this polarimetry actually bring into the picture that the in situ observations weren't able to? Considering the limitations and the advantages of this polarimetry mission.
I guess I haven't thought enough about that. Like you say, I'm certainly hoping that by looking at a global structure, by looking at the 3D reconstruction, that we're able to learn something new. And maybe that's the main thing that we're going to be learning, is just what is the 3D structure. I mean, we're kind of assuming these nice smooth structures, I think Craig described them at one point as a snail shell. Is that really what we're going to find when we look at the actual measurements? How well does this 3D structure compare to what we've seen in the schematics or for example, what the model that Brian Wood used in order to match his synthetic images to his real-world images. He assumed something simple. Polarization should enable us to do that kind of reconstruction better without having to, I hope, without having to assume an underlying model. At least that's the way Craig and I were able to do something like that when we image structure within a CME. So we're hoping that we're going to be able to do similar reconstructions with not a model-based reconstruction, but just a data-based reconstruction, as it were, and see what comes out of it.
I want to put Kurt on the spot again. Your talk really intrigued me, especially when you showed this prior work on crinkly coronal holes and what sorts of CIRs they might produce. What kinds of things can we do to resolve that type of structure, or do we need to model them to find out?
How do you mean that we want to resolve in terms of the observations?
Yes, you mentioned that crinkly edges to coronal holes, or by extension, maybe the variable jetty edges that we've talked about, might affect the structure of a CIR coming out of that region. Have you thought about what we might be able to see to discern that?
No, I guess I haven't really. I mean, that's one of the reasons. I don't want to do too much guessing at what we might see. I wanted to do the actual, ask Dushan to do the simulation and see how much we can see, how much is preserved. But yes, I think that'll be a really interesting question. How much structure can we preserve in the CIR images or in the white light images? And then, of course, in reality, what we're going to be doing with Dushan's help is going to be an idealized situation in which we have a very simple background solar wind and a structureless background solar wind. If you put extra structure in there, one co-rotating region behind another, perhaps, as you might get in real-world images. I don't know. Will we preserve those crinkly edges, or will they totally get washed out? And we'll start off by doing simple simulations and see what we see.
Question? Philip, so when you interpret this kind of propagating features as a flow, consider this as a thin white light. It means enhanced electron densities. Do you think those are directly represent the motion of enhanced electron density, or some just because the structure, magnetic structure expanding cause ambient plasma increase the density? For example, when you have this reconnection downflow. So in the EUV, that thing, the dark emissions suggest empty emission density, but you see the brightening and enhanced density. So is that because the compression of background?
I think it's very likely to be compression of the background, but I also think another thing to keep in mind is that we see those things most clearly when we do a running difference. So what you might see as a bright feature is actually like a very dark feature that's going down, and then as you do your subtraction, what's left behind that dark feature that's going downward is a bright feature because it's had less subtracted off of it. So there's a lot going on there. I do think physically the most common explanation is material being compressed, around these reconnection outflows.
So that was an earlier question that I don't want to let go away, and that was from Gabriel to ask about Anna about the CME challenge. The question was, how easy would it be to project these results into other coronagraph fields of view, asking specifically about CCOR, which only gets unpolarized brightness. But is that the same as just the 90-degree Earth-based view, or is there something else to do there?
The projection itself would be trivial. It will be just as little as literally changing a couple of input parameters and running it again. The problem might be in the Gamera simulation itself, because it starts at 22-hour sun. There are no data in the sphere underneath 22-hour sun. So if we go to a very narrow field of view, in principle, all we will see is just nothing. So that is just the intrinsic limitation of those simulations.
Okay, what else? Oh, yeah, Samaya's question. While on this question about the CME simulations, what is the smallest? Where to go? The smallest, the smallest flux rope that you can simulate. Could you do, for example, a standard-sized coronal jet? Or then how big can it go too?
Well, the limitation on the low side, I think, is just 1 pixel size. And Elena will correct me, but I think right now the pixel sizes in longitude and latitude are the longitude has like 256 pixels per 360 degrees, and latitude will have it goes from 0.1 pi to 0.9 pi, and it has 128 pixels. But Elena, please correct me if I'm wrong. Yeah, I'm talking about just the current one.
Yeah, it's a question of the resolution that we're using in simulations, right? So I'll talk about this tomorrow. We are currently capable to run really high resolution simulations, which is 8 times finer than Anya showed. So in principle, it is possible to run smaller scale flux ropes.
And as for the biggest possible size, just to continue just to continue this question real fast, as for the biggest possible size, we are limited by the fact that we don't have a lot near the North and the South Pole. The simulation ends at 0.1 pi around each pole. So if a simulation reaches, if a CME reaches that boundary, it kind of goes away.
Yeah, I wanted to make a comment. With SME, we could reconstruct jets in the data, and the resolution with punch should be much greater. So you ought to be able to see these in the heliosphere. This was above about 20 degrees, and you could actually project them down to coronagraph observations where they showed up there as the jetting features. So and there are papers on that. So yes. The answer is you'll be able to see jets in punch and the manifestation in bright.
And it means that we should be able to simulate them too. Okay.
All right, what else?
One is just a simple clarification one. Annie, what is the field of view of the CME challenge?
In this particular situation, it's plus or minus 45 degrees.
45 degrees, which is in solar radii more or less.
No.
Some people need to know how close to the sun it is.
In
Okay.
equivalent solar radii, it's 180 because we're using solar radius as an angular unit.
Correct.
I would strongly advocate against projecting anything onto a plane because it really screws up the intuition at fields of view this big because nothing is perpendicular to anything anymore and what is the plane of sky plane is a teeny tiny fragment of the celestial sphere, really. So I would say that if we need to know the solar radial extent, why don't we take the what R of 900 arc seconds and divide 90 degrees by 900 arc seconds and define solar radii this way.
I think that's what you did, right?
Is that what you did?
Yeah.
Nice.
And just also to point out that with the movies, it kind of looked like the inner field of view was the disk of the sun, so they looked much closer to the sun, but that was 21.5 our sun.
Right. What else? Hard to figure out which one to choose. More upvotes. Oh yeah, about the timing. Yeah, Phil. For the streamers, the streamer blowouts, the large-scale erupting structures, can you get a good sense of the timing? How much energy? How much time does it take for the energy to build up and be released?
So typically for the blobs, you see that happen very quickly because that's just a very small scale reconnection. But what you will see leading up to that for a period of a couple of hours typically is something sort of expanding upward to cause the pressure that actually sort of launches the reconnection. For the streamer blowouts, I mean, that can be a process. It really depends on how big your cavity or your filament is. I mean, it can take a few hours. It can take even, many hours for that to actually sort of slowly rise up into the current sheet and, eventually hit that open field where you see the instability and it really launches off. But that's what I would say typically. It's for a few hours. And for the large scale ones, I mean, those happen in a course of minutes, if not an hour. But the real difference I think you see is the scale heights where these things happen, where the big ones happen very close down to the sun, and that's why they can happen more quickly. There's a lot more energy. The streamer blowouts, you see the reconnection happen in the core 1 field of view typically, so about 1.5 our sun. And for the blobs, that's out in C2, so that's at like 2.5 or 3 our sun.
So, Phil, your answer just made me want to put Shahi on the spot again here. You gave a really great talk about multiple ring structures, right, nested flux ropes. And of course, I'm interested in how do you know that they're not, how do you know that they are rings, or how do you know that things that look spiral aren't rings, right, that kind of thing. But there's a time scale that Bill mentioned for reconnection, and that just came up again in Phil's answer. It probably would be worthwhile to think about how long those things can last, right? Yeah.
I also have many other questions regarding those. So in those rings, we see like 4 to 5 rings. So my question is, why don't we see 20 rings? Why don't we see very finer rings within inside the core of the CME? Why are we seeing 4 rings? So, yeah, sorry, sir, go ahead.
Yeah, no, I mean, that is a really good question. Why those flux surfaces in particular? When you're down in the low corona, there may be reasons, like in Yuhong simulations, they have to do with heating that happens and density. Certain areas get more dense or more hot. In this case, the heat won't matter, but I mean, because it's white light doesn't care about temperature, but still you can get density structure that occurs, in particular when you have a reconnection at a surface, like at along an X line below, inside a flux rope or just below a flux rope. But the question then is, as it goes out in the solar wind, is it just frozen there somehow? I mean, is it just being advected along and not changing or expanding or blurring?
Or does it start untwisting?
After a couple decades of experience working with people's data, it's almost always because the instrument isn't as good as you think.
True. So on Monday, I have the colloquium, so I would like to discuss with you guys, and maybe we can add more points in that colloquium. Yeah, yeah. So the plans are to work with the UHong simulation also. So that's
It is about 2:30. We should really get our break started. Oh, sure. Yes.
Okay, so we're going to do this differently because people are getting frustrated with all of the vestigial questions here. So they gave me admin privileges. What I'm going to do is, as the questions are answered, I will retire them so that the panel, the session chairs, can view the questions that are only active. But during the break, I'm going to reactivate all of the questions from this most recent panel session so people can chat and see the answers and things like that. And then I'll re-retire them for the next one. And then at the end of the day, I'll open them all up and you guys can have fun. All right?
Let's thank our 4 speakers again. Back at 3 o'clock? Yes.
reminder, we will prioritize the questions on Slido. If you ask a question that is for a particular speaker, please indicate so. That'll help us understand which question it is. Also, if you're not asking a question, if you'd like to review the questions, we can crowdsource it. And so you can say, I'd like to see this question answered. You can upvote it. We do not encourage downvoting, but you can do that. But you know, mostly if upvote if you do want to see the question prioritized in the chat. Alrighty.
All right, our first talk is Francesco talking about magnetohydrodynamics turbulence simulations as testing ground for punch. And just a reminder to all the speakers that when you use the pointer, you can point it directly at this screen and it will show up on all screens as if by magic. Great, thank you.
All right, thank you. So for this collaboration, Delaware, and people from Punch, like Sarah Gibson, Nicky Vial, Craig, and we're using MHD simulations in order to understand what type of turbulence information we will be able to recover using Punch images when they will be available. This work fits into the working group number 1, to understand how coronal structures become the ambient solar wind. You've seen this picture already, so I'll be just going very fast. So especially the tracking feature is also important because using that, we will also be able to understand how turbulence develops starting from the lower corona up into the inner heliosphere. So you've seen this already again, but I wanted to remind you some numbers that will be important. So for UNify and UNIFY, we have a resolution is about 28 megameters and 56 megameters, and the total field of view is going to be about 180 solar radii. Given these numbers, it's almost impossible to have a simulation, an MHD simulation, that has this small resolution of 28 megameters with a total domain size of 180 solar radii, which is about 1 AU. So we had to find a way around this problem. The other important thing that I was mentioning before also is this 4-minute cadence observation that will help us understand the evolution of turbulence in the inner heliosphere. So the resolution that Punch will provide is going to be right here, and I'm going to briefly describe what this means. So in general, a turbulent system can be sort of described putting into 3 categories. One is the energy containing scale. They are the very large scales that sort of contain the energy that is provided to the system, and this energy is then transferred in the inertial range to smaller scales where all the nonlinear processes are more active, and therefore there is this cascade of turbulence from the large scale to the small scales where eventually energy is dissipated. So the most important, well, we are very interested in all of them are important, but we are mostly interested in the inertial range, that is where these nonlinear processes take place and they sort of move the energy from the large scale to the small scales. And Punch will give the right resolution here that is at the beginning of the inertial range where this kind of cascade starts, so where energy starts to be converted. To do this investigation of turbulence properties using Punch images, we have a campaign of simulation. All of them are different, and of course they are MHD, magnetohydrodynamics, because we're not interested in the small physics of what's going on, the particle physics, but we are more interested in the big picture. So that's why we can use MHD simulations. And we have isotropic simulation, that is, there is no mean field, that is probably more relevant to when the turbulent, the solar wind is more developed, far away from the sun. Anisotropic, so when there is a mean field present, that is when the plasma is more magnetically dominated, that is closer to the sun, where the beta is very low. We have shear-driven simulation, that is when instabilities like Kelvin-Amos develop. And we also can use synthetic spectral, so we can see what is the effect of the punch taking pictures of the solar wind on different types of slopes into the inertial range. So as I was saying at the beginning, it's almost impossible to have an MHD simulation that has that small resolution of punch of 28 megameters with a total field of view of 180 solar radii. So the workaround here is taking one simulation, like this one. The quantity that is represented is the density, and here is replicated on the right, just some of the few most denser region highlighted. And since, okay, let me put first the sun somewhere. I know it's blue, but it's the sun. And then, since simulations are periodic, we can replicate this simulation a lot of time in either direction. And so we can fill up the heliosphere in sort of like a Rubik's Cube kind of way. And this, all these cubes add up to the total field of view that punch will provide with the resolution that we want it to be in the simulation. Last step is to actually put punch somewhere. So we have the observer here, and we're going to collect information along these line of sight using the forward modeling tool. So this is sort of like a cross-section of what I was just showing before. So you see all these little cubes. This is the Thomson sphere, Thomson surface that has been mentioned several times. And oh, this is going a little bit straight. And all of these are the line of sights along which the information is collected. And this on the right here is an actual picture that is obtained from this forward modeling using this kind of simulation. So from this type of domain, we obtain a punch-like image like this. Now, as been mentioned already today, punch will provide us mostly 2D information. So, but we have 3D, a 3D heliosphere and 3D simulations. So how do we compare the two things to understand what's going on? So it's not definitely a one-to-one comparison, because if you look at the punch-like image, it's quite different from a one single 2D plane taken from the simulation. So, and there are several reasons for this. I listed just two of them here. There are effects that come from integration along the line of sight, because when information is integrated along some direction, then we, of course, the small structures and the strong gradients are going to be smeared, and so we lose the small scale information. And the other effect is that there is a radial trend into the forward modeling tool that provides this linear scaling. Well, it's not really linear, but there is this trend in the generated figures that is missing in the simulations. So we try and make up for this. So a crude way to integrate along some non-oblique line of sight, that is what forward does, is to integrate the simulation along one direction. And this is especially easy when the simulations are isotropic, so there is no preferential direction, so we can integrate along either direction we like. And we obtain something like this. So we change this simulation 1D plane to this simulation integrated density, which is a lot more similar to this punch-like image. But we still have to get rid of this radial trend. We can do that by just subtracting, where is it? Just subtracting a line that goes from the lower left to the top right corners, and the punch detrended image looks like this, which is again more similar, a step closer to being similar to this simulation integrated plane. Of course, you can see they're not the same, but they have the same spectral properties, as I will show soon. And the fact that they are not the same should not discourage us, because it's like when you take two time series in the solar wind, they do not look like the same, of course, because they're two different time series, but they have the same spectral properties. And this is what we're after. As I was saying before, the integration along the line of sight, or integration in any direction of a simulation, will smear the small scale features. And this is particularly evident and can be quantified by measuring the correlation function, which is defined up here, where f is any quantity. In this case, it's the density, or the brightness when we go into punch images. And the correlation length can be defined as the integral of this correlation function. And you can see immediately that the integral of this red curve is much smaller than the integral of the blue curve. And therefore, it means that the correlation length of the simulation 2D plane is smaller than the simulation integrated plane, which means that the fields are much faster, they decorrelate more faster when the small scale shears are present. And we are interested in this correlation length because punch is going to look at the beginning of the inertial range that can be roughly estimated to be at about the correlation length, so slightly smaller, the scales that are slightly smaller than the correlation scale. One other basic ingredient of turbulence is the second order structure function. It is defined in this way, where f again is any field. And from turbulence theory, we expect the second order structure function to have a scaling as the lag to the third in the vicinity, well, within the inertial range, and especially for what we're interested in the vicinity of the correlation scales that are these two vertical lines here. And you can see that the simulation 2D plane, which is a pristine simulation, in the simulation plane, we recovered this scaling. This scaling, though, is missing, it's different for punch-like and integrated simulation pictures. We're still trying to understand why. Oh, well, we know why, because the quantities are averaged or integrated along line of sight, and therefore we cannot apply the usual turbulence theory to them. But what we were after is trying to understand if we could recover those properties. And indeed we can, because even though the scalings are different from the ones that come from theory, well, the scaling for punch and integrated simulation are similar. So these two curves have the same scaling. That is what we wanted to get to. And in similar fashion, we can look at the equivalent spectrum, and people may have heard probably more often of the Kolmogorov scaling, or k to the minus 5/3, that again we can recover this scaling close to the correlation length, this scaling here, for the simulation 2D plane, but it's missing from punch and integrated simulation. But again, punch and integrated simulation have a similar scaling. So the main point is, even though we cannot still explain theoretically what the scaling will be for punch, we still have a way to recover it by using simulations. We did some other tests. For example, does the dimensionality of this Rubik's cube affect the results? And the answer is no, at least for the moment. So we tried with different numbers of cubes per side, and still the scalings between punch and integrated simulations hold. So they're still different from the theoretical one from pristine turbulence, but the two still are similar together. And we're happy with this, of course. And then the last thing I'm going to show is we tried to change the direction of the observation. So we moved punch around this heliosphere, and since we're using an isotropic simulation, we did not expect results to change, because this should not, of course, since it's isotropic, it should not matter from which direction you look at it. And indeed, they do not change, so we're quite happy with that too. Last, just going very fast on the conclusions, we are using simulations to create this tunable Rubik's Cube corona or heliosphere. And there are several caveats that need to be taken into account. That is the actual resolution of punch. Now we're using something that is a little bit more resolved than punch will be. There are averaging issues. There are trends that need to be removed. There is a density fall-off because of the solar wind expansion that's not taken into account yet. And most important, there are the effects of the line of sight integration that modify the usual turbulence scalings. So we don't have a theory for that yet, but we are able to recover the scalings by using the simulations. And there are several more points that need to be addressed, like using different simulations, investigate the time evolution, understand the anisotropies of the solar wind, and if you have any other suggestions. Thank you.
All right, the next talk is going to be Stephen Kramer talking on mapping the sun's Alfvén surface with punch.
All right, thanks. I just realized that all the speakers in this session have some connection to 5 years out of date, but that's okay. So yeah, I'll be talking about the Alfvén surface, which is the goal of Working Group 1C of punch, right? What are the evolving physical properties of the Alfvén surface? So at the talk, I'll just quickly start by defining what this thing is and why do we care. I'll go over some different existing observational and theoretical guesses about where this surface is in the corona and the heliosphere, and then talk about what punch will do. So yeah, we've been talking a lot about the corona, which is typically something that we observe with telescopes or with imagers. And then we've been talking about the solar wind and the heliosphere, which traditionally has been the thing that we detect by in situ particles. Is there a boundary between these two? Right? I drew this sort of boundary, but in reality, there is no boundary. In reality, the corona expands into the solar wind. But in one sense, it is useful to talk about this thing called the Alfvén surface that effectively defines a boundary between the two, right? The Alfvén surface is the place where the Alfvén speed equals the solar wind speed. I have this sort of model cartoon on the right that shows the solar wind accelerating on the black curve. The Alfvén speed is high in the corona, and then it declines to be less than the solar wind out in the heliosphere, right? 1 AU is at about 215 on that scale. And there's this place where they cross, right? Below the Alfvén surface, the Alfvén speed is bigger than the solar wind speed, so that means that information is able to propagate pretty much anywhere it wants, right? If information is propagating in an MHD system with the Alfvén speed, basically any point beneath the Alfvén surface can communicate with any other point, right? Information can go all the way from 10 solar radii or whatever back down to the solar surface. Above the Alfvén point, it's different because the solar wind speed is basically dragging everything out. It's dragging the plasma and the magnetic field out, and even the inward-going Alfvén waves are being dragged out with the solar wind. So both the inward and the outward waves are moving out. So there's this difference, right? So we often think about the Alfvén surface or the Alfvén radius or whatever we want to call it as sort of the inner boundary of the heliosphere, because beyond it is the point where basically there's no going back. It's all the solar wind. There's the Alfvén surface shows up in a lot of other solar and stellar physics contexts. If you're studying how the solar rotation evolves over billions of years, the Alfvén radius is kind of like the lever arm. If the solar wind is carrying away angular momentum and the sun is spinning down because of this loss of torque, the Alfvén radius is essentially this lever arm that tells you how big the torque is. There's also observational ways of understanding. Is this the thing? Yes. There's observational ways of using the Alfvén surface to measure the magnetic field out far from the corona, which, measurements of the magnetic field are hard to come by when you're out in the corona. So if you can measure the solar wind speed at the place where it equals the Alfvén speed, you can get the Alfvén speed, right? And then you can get the magnetic field strength also. Yeah, so there's a whole range of possible values for the Alfvén speed. Up there I'm showing just sort of 300 different examples of solar wind models, different values of the fast and slow solar wind speed, different values of the magnetic field strength, which makes the Alfvén velocity go up and down. There's also the sound speed in blue. The Alfvén radius is now sort of a histogram in red, but then there's also the Parker critical point, which is lower down, which is where the wind speed exceeds the sound speed. Further out, there's also the plasma beta equals 1 surface that is also interesting for all sorts of other plasma physics and MHD in the solar wind. Yeah, a lot of details to talk about. But the other aspect of why it's interesting, I briefly mentioned that the Alfvén surface is sort of the point of no return for the heliosphere. So it's often talked about as the place where you can't have time-steady coronal loops extending above the Alfvén surface. Actually, though, when we observe coronal loops, they don't go up as far as 10 or 20 solar radii. They only go up 2 to 3 solar radii above the surface. And I think we can understand that from the same sort of physics that helps us understand the Alfvén radius. So the idea is, I hope you can see these little graphs. On the left is just looking at the radial component of the magnetic field, converting that to a magnetic pressure, and then comparing it to things like the gas pressure and the ram pressure of the solar wind. They cross each other at around 10 solar radii. That's the Alfvén radius. That's what we mean by the Alfvén radius. But the definition of where these loops stop isn't so much about the radial magnetic forces, it's about the transverse magnetic forces. Because as these loops come together, it's a transverse pressure balance that knits everything together in the low corona. And if you have a model of the magnetic field, you can follow the transverse or horizontal magnetic pressure. That crosses these other things at only 2 or 3 solar radii. And that's, I think, the explanation for why the loops don't go much past that point. So it's the same sort of physics that causes the Alfvén surface, but it's a different component of the magnetic field that does it. All right, now where is this Alfvén surface? So I think the earliest guesses were from simulations and models. Weber and Davis talked about it in the 60s, and there's been a whole line of other simulations and models that have tried to come up with a good prediction. In the next talk, we'll see some more details about how that works. I've got 2 examples, the black histogram and the blue one from Rohit, who you'll hear next, have 2 different predictions for where the Alfvén surface falls. They're a little bit different. But yeah, models can be tuned in lots of different ways, so they can come up with different predictions. What we want is observations, of course. The in situ data, which are the other 2 histograms, the lower down ones there, basically you can take the plasma and field quantities measured, say at 1 AU, and extrapolate them in, right? If you have the solar wind speed, you can figure out, if you know how the solar wind accelerates, you can trace that in, and then if you have the Alfvén speed, you can trace that in and find the place where they meet. And you need to know things about, say, the plasma density and how that varies with solar wind distance in order to do that. But you can do that. The lower black histogram shows data from the Omni database at 1 AU, trying to figure out where is the Alfvén surface for many different observations. So it's a histogram with a median value around 15 solar radii or so. Of course, now the gold standard, the red histogram, of course, is Parker Solar Probe, because Parker Solar Probe has been there, right? It's crossed the Alfvén surface a couple times. April 2021, I think, was the first time it did it, and it's done it several times since. The upper plot up there shows my attempt to gather as much Parker Solar Probe data as possible and plot the ratio of the solar wind speed to the Alfvén speed. And there are some data points where it goes below 1, indicating it's crossed the Alfvén surface. And then the lower plot is that attempt to do the extrapolation to figure out, so the y-axis, the y-axis on the lower one is the extrapolated guess for where is the Alfvén surface as a function of where Parker Solar Probe was when it was making the measurement. And the fact that there's not much of a radial trend in those points means that the extrapolation is probably not doing too bad in terms of locating it. So yeah, if we're in a fascinating new era where we can actually explore below the Alfvén surface. But the imaging can do it too. That's what we really care about for Punch. And we want to trace these little blobs that we've seen plenty of talks about, tracing, flow tracking things that are going out, but then there's also flow tracking things that are going in, right? If we're below the alphane surface, we can follow things that are falling back to the sun, and the upper limit of radius where you see that is a good guess for where the alphane surface is. Just a plot of height versus time. You've seen these J plots for a while. This is sort of a combination of models and some observations from Craig's 2014 paper. You can see things flowing out in, say, at the wind speed or at the alphane speed. The solid red curves tell you how things flow if they're flowing inward with the alphane speed. Of course, above the alphane surface, they're still being dragged out, so they go out. But below, they come back down to the sun. And Craig saw some stuff between about 12 and 7 solar radii that was also coming in, but it doesn't quite match what we thought should be happening for the alphane, for something flowing at the alphane speed, right? If it's flowing at the alphane speed's getting bigger as you go in, so it should be accelerating as it's heading down to the sun, but what Craig saw was decelerating. So there's been lots of theoretical studies of this, and many of the ideas sort of are revolving around the idea that these blobs coming down to the sun are sort of snow plowing into the plasma in front of them, so they're sort of gaining inertia, so they're slowing down, they're being decelerated, and that's what's causing what you see here. But are they nonlinear? Are they coming from magnetic reconnection in the outer corona? Are they these Kelvin-Helmholtz vortices? All sorts of things they could be. Thanks. We need more examples. That's what punch is going to give us, right? And that's the segue to how will punch help improve our understanding, right? You've seen the trifoil before, so we know that we really just want to measure many, many more examples of inflows in the NIFI field of view, for example, using these flow tracking algorithms. Also applying this spatiotemporal Fourier filtering that's used to separate outflows from inflows, because sometimes the inflows might get swamped by the outflows, and possibly also use the polarization. And yes, we in Working Group 1C are very grateful to the people in Working Group 1A who are developing these flow tracking algorithms. We're not worthy. We're gonna make very good use of them, and we're thankful for them being developed. But there's a lot of questions, of course, we can answer. Maybe we'll be seeing many more lower contrast features than what Craig saw in 2014. Maybe the deceleration is only happening for the biggest features. Maybe these lowest ones might be more linear, and they might accelerate as you get closer to the sun. Well, what are their lifetimes? Well, what does that tell us about the solar wind and turbulence, for example? One final example is that there is another way we can think about the crossover between turbulence and the alphane surface, right? If the alphane speed and the radial outflow speed have sort of turbulent variations in them, then as a parcel is flowing either passively out or passively in, it's going to encounter different places where the wind speed and the alphane speed cross. So maybe one parcel that wants to move inward on the inward alphane wave characteristics, as they're called, might actually be bobbing up and down a little bit before it flows down to the sun. And in the bottom, there's some example trajectories in this sort of simple realization of turbulent variations that we put together. And it basically what shows it might what might happen is that as flows bob up and down, that is another way that they could possibly be decelerated for a while before they flow down to the sun. So that green dashed line is, again, the observed kinematic trajectory that Craig saw in 2014. And maybe some of these bobbing up and down flows keep you on that trajectory longer rather than going down just without bobbing up and down at all. So yeah, a lot of things we can study, and maybe with punch we'll be able to actually see individual blobs that are bobbing up and down. We might be able to actually track them to that level of detail. Yeah, that's the conclusion. We really want to probe the dynamics of turbulent parcels and the solar wind in the vicinity of the alphane surface. That's going to improve our understanding of all sorts of aspects of the coronal heating and the solar wind acceleration. And what I'm highlighting here is that I think coordination with other instruments and other programs is going to actually be, as I say, the secret sauce that's really going to help give us a more global picture of how these things all come together. All right, thanks.
Of an extended and fragmented Alfvén zone in the young solar wind. Thank you. Is it going to come up on here? Or do I need to do something?
Apologies, I'm just trying to get it pull up back here.
I did upload the most recent version about an hour back, so if you could upload that one.
Okay, I might need to re-download it. I'm having issues with the current version, so just give me 30 seconds.
Interpretive dance. You can just look at that beautiful. Okay, so I've got a pointer, but I'm going ahead in my talk. And that's it. Right, so this it's follows very naturally from Steve's talk, just diving a little bit deeper into some properties of this fragmented Alfvén zone, fragmented, frothy, extended Alfvén zone, and hopefully trying to think about some implications for punch observations and also flow tracking efforts related to punch. So I don't need an introduction because of Steve's excellent introduction. And there'll be a little bit of an overlap, so I apologize for that. But I'll start off with a quick review of this, how we use a solar wind model to generate a fragmented Alfvén zone in 3 dimensions. And then I'll talk about some properties of this Alfvén zone which might be of interest to punch. So first you've got these spatial scales of the sub-alphenic blobs that you might see. And then what kind of motions might be associated with the Alfvén zone and how they might help punch in localizing the Alfvén zone and mapping it out. Okay, so we've known for a while that there's going to be a fair degree of variability in the shape of the Alfvén surface, right? We know this from 3D MHD models because if you use realistic magnetogram boundary conditions for these MHD models and you look at the Alfvén surface in a meridional plane, then you see that during solar minimum, the Alfvén surface has this kind of somewhat symmetric shape, which does dip down a bit at the heliospheric current sheet. And if you look at solar maximum conditions where the magnetic field of the sun is more complex, then you get a more complex Alfvén surface over here. But what I want to emphasize is that this variability that you're seeing is large-scale variability that is associated with structures at the sun and solar activity. However, recent observations have suggested that you might have variability in the Alfvén surface at much smaller scales. And I don't think I need to play this movie over here on the left where you see these variations in the density and also flow differentials, right, in the stereo image. But in addition to that, there's also been in situ work where you use extrapolations from in situ observations, in this case Ulysses observations, and trace these observations back toward the sun to localize the Alfvén surface, and you see this kind of corrugated structure as a function of latitude. So this is basically if you have ubiquitous fluctuations in the solar wind, and you can have them in the velocity, in the magnetic field, and the density, all 3 will produce fluctuations in the Alfvén Mach number, right? And so this produces this kind of small-scale variability in structure. Okay, I think you've seen that movie enough. So the way we wanted to do this was using our, to try and produce this kind of variability in an MHD model. Obviously, we don't have, Francesco also spoke about this, we can't do a full turbulence simulation of the solar wind, right? Which explicitly resolves the turbulence. So we saw Francesco's very interesting and innovative approach,
But a more traditional approach is to focus on the large scales by means of this Reynolds decomposition, where you split physical fields into a mean part and a fluctuating part. And then with this decomposition, you can derive a set of equations that explicitly resolve the large scales, and another set of equations which describes the statistical properties of the fluctuations. So you can have equations which describe the distributions of the turbulence energy, the average turbulence energy, the cross velocidity, which is the correlation between velocity and magnetic fluctuations, and the characteristic correlation scales of the turbulence, right? So with this coupled system of equations, you can have turbulence accelerating and heating the wind, and also turbulence being driven by gradients in the large scale field. So a very quick, I've presented this work at earlier Punch meetings, so a very quick sort of an overview of how we get this fragmented alphane zone in our model. If you just consider the mean fields that the model gives you in a meridional plane, and this is a tilted dipole type of simulation, then you get this distribution of alphane Mach numbers, right? And if it's green and darker shades, then that's subalphanic. Red and brighter shades are superalphanic, and the boundary separating the two is your nominal alphane surface. But if we use the turbulence information that we have in our model to add a realization of turbulent fluctuations to the mean magnetic field, then you can get a alphane velocity or a speed which includes the turbulence. And then you get this distribution of the Mach number, where you see this instead of a well-separated boundary, you have this region where you start seeing superalphanic patches below the nominal alphane surface, right? And then the density of these superalphanic patches increases as you go away from the sun until eventually it becomes fully superalphanic. Another way to look at this is this, simply color the grid points in the simulation based on whether they're subalphanic or superalphanic. And once again, you see this transitional zone where you have these subalphanic blobs in beige and the superalphanic regions in this teal color. So this is work that was published last year. And now what I want to do here is try and get some more properties of these structures. So the first thing obviously you can talk about is the spatial scales of these subalphanic patches, or also the superalphanic, but we'll focus on subalphanic over here. And the way I do this is in a coarse-grained sense. So in this meridional plane, I look at bins, which are 5 solar radius in the radial direction and 15 degrees in the latitude direction. And within that, I estimate the radial extent of these white blobs. And that gives me this distribution of spatial scales of the subalphanic patches. And you see that there's a very clear trend where it increases with, as you approach the sun. And this is obviously because more of the wind becomes subalphanic as you approach the sun. So we are seeing a transition from about 200,000 kilometers at the outer boundary of the alphane zone, reaching more than 1 million kilometers at the inner boundary of this alphane zone. And just to remind you, the punch spatial resolution does lie below the lower limit over here. So it should be very easy to observe these structures. A caveat here is that the minimum scale of these blobs is constrained by the numerical resolution of the code. So you won't see structures which are smaller than the code size, code resolution. There's some variability in this distribution if you look at different longitudes. But overall, the range of sizes that you see doesn't change by much. But there's some longitudinal variability. And if you look at the probability density of the spatial scales of subalphanic blobs, averaging over all longitudes, then you see this kind of distribution. Much more likely to see scales at the smaller size, but there is a radial trend here, right? Like you have this large circumferential sort of area far from the sun where you have the small size structures. So there's a radial trend that's kind of baked into this histogram. So punch obviously cannot measure the magnetic fields, but the way it can, one of the ways it can try to map out the alphane surface or the alphane zone is by looking at flows, as Steve was talking about. So you have this very elementary slide over here, which shows a mean magnetic field close to the sun, it's going to be in the radial direction. You've got a radial solar wind flow, and we know that the alphanic signals are going to propagate either sunward or anti-sunward, right, along the mean magnetic field. So in the alphane zone and below the alphane zone, you're going to have the possibility of sunward propagation at this speed, the alphane speed minus the mean solar wind, or minus the solar wind speed. And obviously you cannot have this above the alphane zone because the solar wind speed is larger than the alphane speed. So you're going to have these sunward modes advected away from the sun by the bulk flow. But below the alphane zone and in the alphane zone, you can have these sunward motions. So here's a distribution of the alphane speeds for subalphanic and superalphanic blobs separately in a meridional plane again. And you see that obviously close to the sun, the alphane speeds are much larger. The magnetic field is strong. In the low latitude region close to the current sheet, also the alphane speed is small because the magnetic field is small. And as you go away from the sun, the alphane speed decreases, right? Because as the magnetic field decreases in strength. So this is for the subalphanic blobs that you see in this figure. If you look at superalphanic blobs, and this is the distribution of speeds that you get. Much smaller than the subalphanic blobs, mainly because you don't have any superalphanic blobs close to the sun where the alphane speeds are larger. But if you look at the distributions of the alphane speeds for both subalphanic and superalphanic blobs, then they are concentrated at about a couple hundred kilometers per second. So this is the speed at which you might see these motions, these signals propagate in the frame of the mean solar wind, right? If you somehow subtracted out the mean flow, then these are the speeds of the motions that you might see. But another way, and maybe more interesting, is to look at the actual speeds that you would see just in the punch field of view, say, in the meridional plane. So this is the speed at which, if you have sunward propagating modes, in the subalphanic domain, you would have a propagation toward the sun at this speed, right? And that's what I've plotted over here. And once again, close to the sun, it's mainly just the alphane speed. You've got very large propagation speeds toward the sun. And far from the sun, at the outer boundary of the alphane zone, you've got these really small propagation speeds toward the sun. And this figure is not saying that you'll have these sunward propagating blobs distributed throughout. They're going to be rare because we know that a preponderance of the alphanic modes propagate away from the sun, right? So, but in case you're lucky enough to catch subalphanic motions toward the sun, this is what the distribution of speeds might look like. And here's a histogram, again showing that it peaks at about 100 kilometers per second, a little bit below that. And so there's this issue of, Raphael was talking about in the flow tracking session this morning in the talk, that the inward modes, their speeds might be within the error bars of the flow tracking methods, right? But you see that the speed of inward propagation does increase as by the time you're at 10 solar radii, the inward propagation speed is almost 1,000 kilometers per second. But away at the upper end of this alphane zone, you might have trouble resolving these very small speeds at about 10 kilometers per second. So now, inspired by Steve's results using his Zephyr code, I did the same kind of trajectories for inward motions in the 3D model that we use to generate the alphane zone. And this is looking at the trajectories of sunward propagating signals. So these are signals which propagate at speed, at a velocity u solar wind minus the alphane velocity, right? And if you're subalphanic, then this velocity is negative. Otherwise, it's positive, and you have an anti-sunward motion. So if you start tracking these parcels at about 18 solar radii, which is kind of the location of the mean alphane surface in this model, then just looking at the mean velocities, if you just compute the trajectory using the mean velocity, then you get this red curve. So you have this drop-off in height as a function of time. But because of the presence of all these fluctuations, You get some trajectories which drop off in half the amount of time. And also you have, as Steve was saying again, that you have this prolonged motion where you can get sort of like a trapping of these parcels in the alphane zone, where you're bouncing back and forth between subalphanic and superalphanic regimes, and they take a longer time to eventually drop down to the sun. These trajectories are sensitive to the initial, where you start tracking them. If you track well below the mean alphane surface, then most of the trajectories fall to the sun pretty rapidly, right? If you track above at the upper edge of the alphane zone, then very few of the trajectories actually make it back to the sun. Most of the trajectories are going to go anti-sunward. But the ones that do, they have this prolonged trapping period once again, and they take a long time to drop down to the sun. So to conclude, you've got, we saw that there's a range of spatial scales that the subalphanic blobs can have. All of these should be resolvable by punch, and you have this effect where the scales should increase approaching the sun. There's also a wide range of flow speeds of the alphanic signals, and you can have sunward motions which are prolonged, take a long time to reach the sun because of trapping in the fragmented alphane zone. Once again, punch could map the alphane zone by tracking such motions. This is kind of a higher order effort that would be done by the flow tracking people, hopefully. It'll give us something that we can use with punch. There's a number of some caveats which we can maybe discuss in the discussion, but I just want to very quickly mention that this is a very crude and simplistic model of adding turbulence on top of the global solar wind model. I've only included magnetic fluctuations. We can add velocity fluctuations. This would introduce correlation effects between velocity and magnetic fluctuations, which could produce more homogeneous distributions. Then there's the question of whether these sunward modes can stay persistent for a long period of time, because you can have reflection where the sunward modes are reflected into anti-sunward modes, right? So there's a question of how long these stochastic trajectories can survive and whether you can trace them all the way to the sun. Future work we want to do is use solar max magnetograms, because that's when punch will be launched. And this is very preliminary work. Any suggestions for more analysis of this alphane zone are welcome. And that's it. Thank you.
For the discussion is going to be Bill Matthews talking to us about some of his ideas about the origin of the solar wind and its turbulence.
See if I can figure this out here. Okay, so the title sort of speaks for itself on observations, but somewhat informed by theory. And I'm going to use the punch logo without commenting on it all the time, just to highlight parts of the talk where I think that punch can tell us more about what's on the slide. So we know that the corona is structured. I have this nice picture from Steve that he lent me a while ago. The picture on the right is from Noor, and I forgot to put Noor's name on it. But obviously the corona is structured, and punch can tell us about that. That's what I'm going to do. This is an outline of the talk, but I think rather than going through this now, I'm going to repeat this at the end to save a little bit of time. But 1/f noise, differential flows, subalphanic, stuff like that I'm going to talk about. So the first thing I want to talk about is the 1/f noise issue, because we know that from the magnetograms, we know that the corona in the photosphere is structured in an interesting kind of way. But long ago, Nakagawa and Levine showed that if you look at azimuthal wave number spectra, you get 1/k behavior, which is kind of interesting. And if you imagine that the 1/k signal kind of peels off the photosphere and gets accelerated into the solar wind, you can convince yourself that that should give something like a 1/f spectrum in the solar wind. And in fact, one does see that. Let's see here, I push here again. Oh, yeah. And we sort of redid this in 2007 and found that, in fact, this is a compensated spectrum in frequency unraveling
the signal the way I just described. And in fact, you see this, at least at higher latitudes, you see this very flat part in the compensated spectrum. And I've assigned a frequency there, which happens to be a frequency band, which is approximately the same frequency band that you see from this analysis at 1AU of something like 600 days of, I think it was IC3 data. And you see the solar rotation peaks and some harmonics, but then between a couple times 10 to the minus 6 hertz and a few times 10 to the minus 5, you see this very, very nice 1 over F signal in the components of the magnetic field. And the frequency band matches up. We did this for UVCS as well with Alessandro Bemperot. I'm not going to show that, but it appears that at least nominally you expect to see 1 over F behavior from a couple 10 to the minus 5 up to nearly 10 to the minus 4 hertz. And I think that this probably points to a source in the solar dynamo, in my opinion. There are some papers recently that argue that it's generated in situ. There's a controversy there, but I think Punch is going to be able to observe this signal in at least two-dimensional plane, if not three. So we resolve the issue. We resolve that issue with Punch. The other thing is the issue of heating and acceleration, origin of the solar wind. This is supposed to be a question that Parker is supposed to resolve. Personally, I'm sorry to say this, Dora, I doubt that Parker is going to resolve it because there are already several different ideas that people think are consistent with what we're seeing. But just in very general terms, one expects to see when you have turbulence and a cascade that heats plasma. I mean, that can be driven by reconnection. It can be driven by magnetic gradients, then it would be driven by reconnection. It can be driven by wave input, fluctuation input at the boundary. That's kind of the more traditional photospheric field line stirring. But it can also be driven by velocity shears. It's just really a question of what the structure of the energy-containing eddies might be. The canonical wave reflection quasi-2D turbulence-driven model posits that the field lines are shaken at the base in the photosphere. Some percent or two gets through the transition region. They reflect from density alphane speed gradients in the corona, which then produces transverse strong alphanic, so-called alphanic turbulence, heats the plasma, and you get the solar wind from that. And in fact, we know from a lot of spacecraft observations that turbulence transfer, which would be implied by any kind of driven turbulence and described by the Politano-Pouquet relation, which I wrote here. I don't need to explain it. But it's a way to measure the cascade rate directly from the Elsasser variables. That's been looked at, for example, by Bandyopadhyay et al. And Zhao et al. Recently in Parker. And here at 36 solar radii, you see you have evidence for 100 times more rapid cascade rate than you see at 1AU, and presumably that gets even stronger as you get closer to the sun. Here's how the estimated cascade rate depends on heliocentric distance, and it should peaks near perihelion at, well, that's 10 to the 5th joules per kilogram per second there, comparable with this number here. And I want to remind people that if you look even at WKB theory, but also non-WKB transport, the fluctuation energy in this corona is supposed to peak somewhere about where you expect the alphane zone to be. And I should also recall for you that if you look at the Litova observations from scintillations a long time ago, the scattering measure has this interesting feature at about the same heliocentric radial distance, which implies the presence of scattering centers or density fluctuations near there. And people have yet to look as to whether there are enhanced density fluctuations, I think, near or just outside the alphane critical region. So that is something else I think that I should have put a punch there, because punch can look for that too. Anyway, all of these different things, whether you're stirring with fluctuations propagating upwards, or you're driving with quasi-2D turbulence associated with the reflection of those upward traveling fluctuations, hold on. Yeah. Well, such a process, whether it's driven by neutral point interchange, which is a new idea that has come along recently. It's actually an old idea that was discounted, but it's reviving now due to interpretations of Parker data. But either of these processes would be expected to have an imprint of supergranulation scales on them, which would then produce differential flows where these processes were stronger and less flows in places where the plasma wasn't heated as much. So I myself don't see any reason to distinguish between these two just because you see that there's an imprint of supergranulation on the system. Now, more on supergranulation, I think we really do know that supergranulation sets the scale for a lot of these processes. Here's high latitude Ulysses observations, and there's these kind of, not periodic, but modulated speed changes, which were called microstreams by Neugebauer back in '95 and others. And similarly, wave and cyclotron-driven models based on observations by Marsh et al. Were invoking modulation of the heating mechanism at controlled by the supergranulation scale. Now, it happens to be that in most of the global MHD models, like for example the Usmanov model, the ones that have turbulence in them, you have to put a correlation scale in. And pretty much as far as I know, everybody puts the supergranulation scale in at the base as the scale of the energy-containing eddies when the turbulence is excited, no matter how it's excited. Now, so this is not PSO, this is PSP, observations of clusters of switchbacks. Stuart Bale et al. Have sort of rediscovered this by looking at the clustering of switchbacks. That was a new observation, but they're associating also that with the supergranulation scale, which I think follows from what was known already, really. Interestingly enough, at the SolarWind meeting, Rahul Sharma and Richard Morton showed these COMP and UCOMP data sets where they looked around the solar disk, but at like 1 1/4 solar radii, and they computed the correlation scale all the way around, and they found that it varied like between around 8 to 9 megameters at 1.03 to 1.3 solar radii, which is a lot closer than it's ever been measured before, as far as I know. I mean, other people might know better. So I think, anyway, supergranulation sets the scale for every known heating mechanism that I'm aware of for the solar wind, heating and acceleration. So anyway, you've seen these pictures a lot, and it looks like the solar wind does, I think, unless I misunderstood the talk earlier today, I think there is this transition. Does it still survive? I think it does. I believe it does. Anyway, so you've also got, how do I get over here? Oh, yeah. So you've got these differential flows, and you've got this transition. Now, the differential flows, I think, come from this imprint of the supergranulation scale on question mark, whatever mechanism does this. I think it's the reflection-driven turbulence. Some people think it's neutral point interchange. But, you know, be that as it may, supergranulation survives one way or the other. But what happens that causes this conversion from striation to flocculation? And, of course, punch is all over that problem, right? That's why we have the indicator up here. Well, our idea on that back in 2020 was that these differential flows that Craig very nicely described in that earlier paper in 2018, that the different flow tubes and flux tubes have different speeds. And, of course, as long as they're magnetically controlled, which means that that you're below the alphane critical region or surface, they really can't do too much. They can wiggle the tubes around. But if you look at a white light coronagraph, you can see that they're not wiggling very much. Right? Probably on the microscopic scale they are. But after the flows exit these kind of pipes and they become more free, there's all this energy in these flows that's available to derive whatever dynamics you like. And when you exceed the Chandrasekhar condition, which means the flow differential is greater than the alphane speed, then you can do mixing layers, you can do Kelvin-Helmholtz, you can do fun things. And here, going all the way back to E1 of PSP, here you see your switchbacks, and never mind all the details here. But if you go over here on the right, this is a plot I think made by Rohit originally that shows the speed differential in the radial direction normalized to the local alphane speed. And I don't know if you can see it that well, but it exceeds 1 sporadically even at E1. So you'd expect that energy becomes available and you get roll-ups, mixing layers. This is very well studied in engineering topics. Here's some, how do I make this work? Let me see. Nope. Oh, I don't know how to make a movie start on here since I don't have a mouse. Oh, this is how I do it. Nope. Can you control that back there? Okay, so let this one run for a minute. On the top we have, this is the vorticity. The flow is going fast, I think, on the top to the right and fast to the left. This is super alphanic, supersonic, and high cross-helicity. So there's a lot of competing forces at work here. But as you can see, because the alphane Mach number is greater than 1 of the flows, you get roll-ups. And now can you start the bottom one because it's going to stop the top one. You see, you get all these roll-ups. Oh, you also get these interesting contact surfaces. And in the density, which is, again, I have the punch icon here indicating that we can, punch is going to say something about this. Can you start the bottom one for me, please? Yeah. It takes a minute for it to start up. And of course, punch doesn't see, is it running? Yeah. Oh, punch doesn't see vorticity, but punch does see density fluctuations. And here's a picture of what that density, well, the roll-up pattern is going to look like. And it's very interesting. You get actually evacuations of plasma up here on the fast flow side, and where it's blue. And you get these interesting high density patches on the bottom, and these kind of shocklets that come off the places where the curvature of the flow streams go through a sharp angle. And you can actually look up in Landau and Lifshitz that that's supposed to happen, which is kind of interesting. But I think there's something there that hasn't been discussed that much, that punch might be able to detect vorticity-driven density fluctuations. So anyway, we've started to enter the coronal plasma. Things are quieter there, but they're also more anisotropic. They're more like reduced MHD, generally speaking. There's less or actually no switchbacks. Has anybody seen a switchback yet in the subalphanic period? I haven't seen it yet. You have to show me. I haven't seen none. I mean, deep in the corona, yes. Way down at the bottom, but not near Parker, I don't think. Anyway, we can talk about it. I don't think there's any there, but we can argue with Nor about that. So in the subalphanic corona, we're going to really start to see coronal plasma, and there could be lots of interesting differences, some of which the punch can be able to tell us about. In particular, the statistically lower fluctuation level for the density, I think, it should be found in the subalphanic periods. Flow tracking, well, we actually, Craig, with a tiny bit of help from me a few years ago, we actually did some flow tracking from Encke. And I think we need to do more of this with punch. And the interesting thing was that the statistics of these ejecta from Comet Encke actually obeyed a kind of Langevin equation, which is sort of prima facie evidence for the existence of turbulence, I would say. So anyway, punch obviously can say a lot about that, but even tracking, I mean, these brilliant people who are doing this impossible programming for punch, but successfully, are going to be able to track lots of features like this just in the gas itself. So that's pretty awesome, I think. And anyway, my summary, we have 1/F noise. Punch can tell us about that. We have the confirmation of the supergranulation scale having an imprint on everything. The differential flows can be studied in much greater details. The low beta subalphanic corona can be studied in an interesting kind of way. Steve and Rohit talked about the alphane zone, which I think is great stuff. And I think, have we made progress on understanding how the corona is heated and solar wind accelerated? Yes and no. I think there are now, I'll come up, you're supposed to kick me off. Anyway, turbulence is strong. How about neutral point interchange reconnection? I doubt it, but what Nor says, that's it. Anyway, something that hasn't been discussed that much is that punch can reveal space-time structure, and I really think we need to do a lot more on that, differentiating between, say, K spectra and omega spectra. So I'll stop there. Thank you. Now what do? We go there?
Forward to answer questions. Looks like the one of the most popular comments is from Craig to Francesco about you need to correct your resolution numbers on slide 3. Overstate punch roughly by 3 times, threefold.
It's because you put 3 times, it's because your simulation is 3 times the punch resolution. Right, probably that. Yeah, it's because you did that on purpose.
Yeah.
That's a good story, you should stick to it.
Well, the next question, it's not specified, but I guess it's for everyone. The question is from Elena. To what extent do we expect CMEs to distort the alphenic surface?
By a lot.
What we've seen from Parker Solar Probe so far, the exception of encounter 14, all the subalvenic periods were all associated with CMEs. CMEs will clean everything in front of them and basically leave it back. Wait for the solar wind to come and fill that vacuum.
So you said the subalfanic periods are associated with CMEs during, before, after?
After the CME.
After the CME, there's a subalfanic period. Okay, interesting. Mhm.
Matt would like some clarification, mostly from Steve, I guess. The question disappeared, but on what you mean by up and down within the.
Oh yeah, what I mean is radially in and out, right? Basically, yeah, there was only a one-dimensional thing that, and similar to what Rohit did in terms of those jaggedy things that were coming down. It was just, when I say bobbing up and down, I mean radially up and radially down. Yeah.
And the magnetic field is pretty radial at those distances.
There might be other back and forth motions too, but that's going to be small, that close to the sun.
Mm-hmm.
The next question is from Craig for Steve and Rohit. So punch will see electron density only, either physical objects or fast mode fronts. Bright blobs will bright blobs have a lower bright blobs will have lower alphenic velocity. How does this bias punch relative to theory? The answer is yes.
Well, yeah, I mean, what we saw with Core 2 was probably the tip of the iceberg, right? It was the brightest, densest things that we could see, and punch is going to start to eat away at that upper limit and see things with lower and lower contrast to the background. So hopefully when we get low enough in contrast that we'll see things that behave more linearly than flow at the Alfvén speed. But everything above that point is either snow plowing or being ablated or something nonlinear. Yeah.
If I can make a comment on that, there's another, there are several phenomena. Obviously, you guys both were saying that there's more to add into the picture of the characteristics that you're investigating. But when you have the upwards and downwards propagating Alfvén waves along a magnetic field, in places where they interact with one another nonlinearly, you have an enhanced MHD Reynolds stress, and you expect higher density fluctuations there. So it could be that some blobs might be regions of interaction of up and down waves, and that's kind of a higher order consideration, I think, but there's a lot going on maybe. But I think it's very interesting what you guys are doing.
I think another thing that can be done is maybe, like I said, so far I've only added fluctuations to the magnetic field, right? You can add it to the velocity, but you can also add fluctuations to the density and then see what kind of, what the density fluctuations, the impact they have on the Alfvén zone or Alfvén surface. So that's possibly something that we can test in some way. So, yeah.
So it looks like there's some questions here for Bill about if we're doing a good job of identifying diagnostics of critical turbulent processes that can be found with punch, or is there more work?
I think we're moving in a good direction, but there's a lot more to do. So.
Yeah, Nikki has a related question, I guess, about the types of space-time disambiguation that punch should be looking for.
Well, we need the flow tracking people to figure out how to flow track turbulence, because then you can follow given features and not only from a given snapshot see what their spatial correlations are, but you can also follow individual features and find out how their time decorrelation works. And then the holy grail is to understand how all the scales decorrelate at different rates. That's really the essence of turbulence, really. So that's what I mean by space-time disambiguation. In other words, don't assume Taylor hypothesis, but look for interesting corrections.
Yeah, I also think another hidden piece of information in the flow tracking will be the lifetimes of the features that are identified, right? They might just be used as, you know, as instantaneous things, but if we can actually look at distributions of lifetimes, and if it's a real thing, that'll help compare to, you know, correlation times and things.
So this is kind of an interesting question that was posed, and I'm wondering, so what you are measuring with the instrument is column density, right? So how do you actually really know where the blobs are? I mean, you are already kind of making assumption of velocity flow, all of that. And I know Borny is doing some tomography. So kind of curious how that is being pulled out from the data.
I guess it's brand new, unexplored territory, right? I mean, the zeroth order thing is if you see a small structure in terms of image size, it's probably going to be small in the direction along the line of sight too. And if it's small in that direction, then maybe the polarization can help tell us where it is. But is that always true? Probably not.
Can I answer Eva Cairns' question? Was that all right? Eva, I don't know where you are, Eva, but hi. I guess you're in Australia. But yeah, I mean, delta V greater than V alphane should give rise to shocks as well. And in the movie that I showed, you could see these kind of shock-like structures coming off downwards from the mixing layer. So I think you're absolutely right. And that means that if those are generated in a mixing region in the corona or solar wind, then Punch should be able to see them.
There are a few more comments in this corner.
Comment regarding what Steve said. You were talking about the lifetimes of things. It is actually one of the output of the magnetic ball tracking. I didn't mention that, but it is intrinsic to the algorithm to calculate the lifetimes of things.
I'd like to comment in general how we interpret the moving features in the outflow. We kind of mainly talk about a bulk plasma transport most of the times, as far as I noticed. But of course, there are waves. There are compressional waves, like slow mode waves. Are those expected as well in the Punch observations? And if so, can they actually be used to find the alpha zone? Because it's one way the information can propagate backward or forward, right? Can we use the wave signatures as opposed to just bulk flow signatures to find out the place where there is no way back?
Did you say wave signatures? You mean the transverse motions? Slow mode. Well, I think what these guys were showing in both of their presentations were the characteristic trajectories of the inward propagating, I guess, alphane modes. So you're saying they should look at what alphane what?
The alphane waves are not visible. Like sheer alphane wave is not.
Well,
couples are compressible.
Well, yeah, when they overlap with the other wave mode, which is everywhere, they do generate density fluctuations. But did you guys think of doing what you're doing for like other wave modes? I guess you can, right?
Sure.
Yeah, anything, right.
Use the mic.
So that's it.
Yeah, I agree.
Use the mic.
Whatever.
Can't hear you. People online can't hear you.
Anything that goes downwards back towards the sun, whether it's a wave, a slow mode wave, any density perturbation, any blob, anything will be the alphane surface. And you don't even actually have to know ahead of time which one it is. to know where the alphane surface is.
Yeah, I anticipate a richness of phenomena to appear when we start to apply Craig's Fourier filtering to separate the upward and downward modes in punch images. There's going to be a lot of cool stuff that we discover.
A follow-up for Bill on the shock question. So in order for that to be seen, it has to have a density large enough. And did those shocks that you were showing us have a large enough density fluctuation for them to be detected in punch?
I think they had pretty large, at least say 50% to 100 to double the density, but I'm not sure how big the contrast has to be for punch to see it. That's a question for the PI. How big does the density contrast have to be for punch to see it?
Sort of depends on where you're looking and how big the feature is, but punch ought to see things that are about a factor of 2
so
at these mesoscales.
At least marginal, yeah.
So we have a couple of questions about the bobbing up and down. Number one, what are the anticipated spatial and temporal scales for bobbing up and down? And then number two, there was a question about will the features grow or will they decay as they bob up and down?
Well, but it's a battle between growth and decay. I'm not sure which piece of physics will dominate. The other models that we did show that when they were going down and they were growing like hailstones, right, accreting mass, they decelerated in very much the way that Craig found in the 2014 Core 2 inflow detection. A model where all they did was become ablated and lose their mass never was able to match that kind of a trajectory. But if they bob up and down, that's another alternate way that they could be decelerated to match what we've seen so far. But again, what we've seen so far is one example. We need lots more with punch.
I think I would add that at least in the models, the scales of the up and down motion, both in time and in distance or spatial scales, they are probably model and numerical resolution dependent and like time stepping dependent and so on. But it might be possible to use these models to find some kind of characteristic like RMS displacement from the initial trajectory or something like that as a function of time. So something can be done with the models to estimate those scales, I think.
But Rohit, do you think they're resolvable by punch? The individual bobs up and down.
I think anything that's happening in the model that I'm using, which has a spatial resolution comparable to the correlation scale, is kind of at the lower limit of the punch resolution. So I think it's possible, at least in some cases. As far as I'm not very familiar with the time resolution of punch, so that's a question for the flow trackers, maybe 5 minutes.
4 minutes.
Okay.
For the flow tracking itself,
yeah.
I mean, currently with Core 2, I mean, I can get something accurate of over about 10, 15 minutes. You get already something. Averaged over some azimuthal bins, so that means maybe 10, 20 degrees.
Yeah.
And over.
So I think at least in my calculations, the speeds are such that the time scales over which this happens up and down is definitely larger than 5 minutes. So there is a coherent motion which is happening at much larger time scales. So in that case, it is in principle resolvable.
Okay, so the next question is from Ivor. I'm not sure if I'm pronouncing it right. I apologize if I'm not pronouncing it right. Oh, and by the way, there's a comment from Barbara that, in the Society of Flat Earthers, they believe that we're on top of the pancake, and what's underneath the pancake? Underneath the pancake, there's a depth of the pancake. Well, apparently underneath the depth, there is Bill, because he's in Sydney, and we should yell. Hi, Ivor. Sorry, not Bill, Ivor. So There's a question from Iver that delta V is bigger than alphenic velocity, can lead also to shocks, not just Kelvin-Helmholtz. Do we expect the in-out blobs to satisfy this constraint? If so, heating and so on might be interesting.
I actually think we answered that a little while ago. But I think that, yes, we're seeing variations of density near the mixing layer and shock-like features. So I don't know if you could see the movie, Ivor, but they kind of look like some kind of shock structure or contact surface or something, but there's density changes.
Okay.
But we could ask the top question, which is the Taz, Neem, and Karen's work shows that the alphane surface should vary with helial longitude as the underlying magnetic field changes. Steve, any thoughts on this?
Yeah, I managed to reply on Slido to that, but also it's great. It would be great to have some time-dependent predictions for the location of the alphane surface, and we can compare that with what we get from Punch. The big difference, though, of course, is that those predictions are going to be point-wise, right? Those were designed for confirmation by in situ detection at one point, so we'll have to figure out some way of performing some kind of line of sight, equivalent line of sight integration to convert those to something Punch would see, or to convert the Punch things to a more 3D thing. But yeah, no, it's great to have more predictions, and maybe if their algorithm is running, every Carrington rotation, we can build up a database of those too. Yeah.
So one comment and one question. One comment from Whisper and Parker Solar Pro. What we've seen, the amount of collisions between blobs is a lot. We've never seen it before, and I expect that will be happening elsewhere in the corona as well. So that actually might change the interpretation of some interpretation. We have to be careful with that. So if that is occurring, we have to take it into account. The question for Bill, for the KH simulation you showed, I'm curious why KH, the simulation of Kelvin-Helmholtz you showed, why the instability only shows up on the upper half and not on the lower half?
Because the way we set it up was that the different flow tubes, if you like, have different magnetic field strength and different density. So when you have the faster side tends to penetrate into the slower side, especially if the slower side has lower density. So you can make it do different things, but the shocks were on the other side. The place where the roll-ups were on the fast side, and the shocks were on the slow side, which is, you'd have to do a whole bunch of simulations to figure out what controls that. What's that? Yeah, sure, let's do it. Let's do it. Also some Punch data when we get it.
Let's see, so I put some snark on the board. Is it a point, a surface, or a zone we should standardize?
Come on, Craig, it's a zone.
It's a zone.
It's definitely not a
point. The alphane zone whenever we mention it.
I've got a whole paragraph on that in our draft of the Working Group 1C white paper, and based on feedback from the authors, it's going to turn into like 3 or 4 paragraphs, I think.
Sweet. Let's see. I'll bloviate for a moment about open flux, because if we're dealing with the alphane zone, we need to think about open flux. In Craig's republic, open flux is anything that penetrates the alphane zone, right? That's the natural division. But in situ people have a different definition, and that's not going to change. So we need to be sensitive to calling things alphane open, alphane closed, if that's what we mean. If for other types of open and closed, we're going to need to start thinking about that. And that's sort of tangential to what we're on. But in the absence, as Barbara says, we have 4 competing standards. We have to just be really clear in our diction. So in all our papers, we got to remember to define our terms very carefully. That's all.
Just want to say on the point versus surface, I think PSP has shown that's like ground truth, right? That it's crossed into the alphane surface or zone at different heights. So it's definitely not a point. It's at different longitudes, it's different heights, yeah.
I guess we are approaching the end of the session, and let's thank all the speakers again.
Thanks, Eva. Thanks for joining us.
Indeed. Okay, thank you guys. Tonight we're done with today, and it was a wonderful day. Really impressed. Wonderful group of talks. I appreciate it. So I think we're going to put up this is our carpool that we've started to put together for the Fiske event. And again, this is at Fiske Planetarium on CU campus. We're arranging for people to get rides there. Afterwards, you're kind of on your own. You can go walk to dinner. Hopefully it's not pouring rain, etc., and get home. Okay, so this is where we are. We actually have 2 other rides that were offered, Noordine Rafi and Dave Dooling. I think if you see your name up there as a driver, if you don't mind kind of standing up and maybe gathering people to you at one side of the room. And then, and you too, Noor, because you're a driver, if you guys go over there. And then if you're listed already as a rider with this person, go join your driver. And if you haven't told anybody yet, and you still need a ride, just walk over and find a driver who has space, because there's several. Sound good? Yeah. Parking on campus. What a good question. Does anybody know the answer?
All right, so there is parking along Regents Road next to Fiske Planetarium. There are a very limited number of spaces right next to Fiske. It is pay to park, but I think because we're after hours, you may not have to, but do check because I don't want you all to get parking tickets.
There are other lots around as well, just a little bit further walk. If you drive past the planetarium, curl around to the left up to the top of that hill, there's some parking up there as well. You should be able to find something.
And Ever should head to bed now and not try to park at Fiske.